Oh, nice. Sounds good. Can everybody hear me okay? Good? Perfect. 2 minutes? Perfect. All right, welcome everybody. This is going to be Demystifying Ethereum Assembly, a practical 0 to 1 guide. So my name is Joshua, or JT Riley. I'm an EVM smart contract engineer. And so a little bit about why I'm here giving this presentation. There's a really big gap between the intermediate Solidity developer and the wizards that can do the assembly black magic, right, that we see in some popular GitHub repos. So I kind of went through this the hard way, reading through as much documentation and as many papers as I could, and hopefully I've condensed this down enough that everybody here can kind of pick this up a little bit faster. Or maybe if you already know this, maybe this will kind of reinforce, or you can learn new things. So this workshop is going to be pretty interactive. So if anybody has questions, if I go over something and maybe it's not clear, feel free to stop me, raise your hand, ask questions. We're going to get to the bottom of pretty much anything you guys have questions on today. So as we get started, section 1, obviously, understanding the Ethereum virtual machine. Here is a link tree. It's going to be the link tree / EVM assembly. And so this is going to have some useful links throughout this presentation. The most important one, for you to be able to follow along and kind of play with these things is called evm.codes. So I'm going to be using that as well periodically throughout. Basically what this is a fantastic resource. It's got everything you need to know about instructions, and then it also has a playground, and that's where we're going to be demoing some of these things so we can really visualize and internalize what's going on. So first up, we're going to talk about the instruction set. So the EVM is a stack-based virtual machine with a relatively small instruction set. And these instructions can be categorized by one of the following, roughly. First is stack instructions. So these are things that have to do with the stack, the values that are on the stack, and swapping, duplicating, things like this. Arithmetic instructions are addition, subtraction, pretty basic stuff. Comparison instructions tend to compare two values and then push 0 if it's false or 1 if it's true. Bitwise instructions has to do with like bit shifting and other really cool stuff. Memory instructions are going to be interacting with the memory in the EVM, which we'll get into a little bit more on that page, and then contextual instructions. So these are like reading and writing to the environment, to storage, and other things like that. So first we have stack instructions. So stack instructions involve manipulating the position of a value on the stack, or values on the stack. So push in value basically pushes a value to the top of the stack where in is the byte size of that value. Pop will pop a value off the top of the stack. Swap in will swap a value on the stack with another. And then dupe in will actually duplicate a value based on the index. So as an example here, this is mnemonic bytecode. Basically, it's just a human-readable format of what the actual EVM bytecode is. So this is at the lowest level. So first we have push 1, right? So we're pushing a value of size 1 byte. The value is going to be 1. And over here, these orange bits here, this is actually just comments to kind of represent exactly what the stack should look like after any given instruction. This next one, it's going to push 1, and that value of 1 byte is going to be 2. So now we have 2 and 1 on the stack. We can do swap 1, which will swap. We have dupe 1, which can duplicate the first value on the stack. And then from there, we just do pop until we run out of values on the stack. So if you guys want to open up the evm.codes website, this is evm.codes/playground. You can also find it in the link tree. So first we're going to do basically pushing the number 1 to the stack, right? So we push of size 1, the value is going to be 1. We'll do the same thing with the number 2. We can do it with 3. And then we can start playing with this, right? So let's say we want to swap the top instruction, or sorry, the top stack item with one that's 2 items down from that. So we can do swap 2. And whenever we run this, we can basically step through every instruction here. So the first one pushes the 1 to the stack. The second pushes the 2 to the stack. You can see the stack represented down here in the bottom right. We'll do the same for 3. And then swap 2 should swap the number 3 with the item 2 items down from it. And there we go, and it swaps. So from stack instructions, we're going to go to arithmetic instructions. So of course, add will add 2 values. Sub will subtract 2 values. Mul will multiply 2 values. Smul does the same thing, but it treats the number as a signed integer. And so what this means is that the number can be represented as positive or negative. Same thing with div. Div is divide, and then sdiv treats them as signed integers. Mod will actually do the modulus, so the remainder after division. exp does exponentiation. And then we actually have some instructions, add mod and mul mod, that will consume 3 items and basically do addition, then modulo, and then multiplication, then modulo. And so here's our arithmetic example. We push a 1 to the stack, we push a 2 to the stack, and then we call the add instruction. It consumes the 2 and the 1, adds them together, and pushes a 3 to the stack. Next, we'll push the number 2 to the stack. We'll duplicate it. We'll duplicate the second item on the stack, right? So now we have 3, 2, 3. And then we'll multiply, which will give us 3. We'll multiply, it'll give us 6. And so now the stack is 6 and then 3. And then we'll divide those, which will give us 2. So hopping over to the playground again. So we'll push 2, push 3, multiply, and let's push, let's say 5, and then add. So as we step through this, we'll see the 2 is pushed to the stack, then the 3. Those are multiplied, so the 2 and 3 are consumed. There's the 6. We push the 5, we add it together, and that'll give us 11. Now this looks like B because this is actually an hexadecimal representation. So instead of going 1 to 9, then rolling over, it actually goes 1 to 9, then A to F, and then it rolls over to the next. So next up, we have comparison instructions. So what this will do is pop 1 or 2 values from the stack, perform a comparison, and then based on the result, it'll either return true or false. Those are actually reversed. If it pushes true, it's going to be 1. If it pushes false, it's going to be 0. So LT will push if the top value is less than the second value. SLT, of course, is with signed integers. Greater than, or GT does greater than. So if the top value is greater than the second value, then we push 1. EQ will compare and see if the top 2 items on the stack are equal. And then is 0 will push a true to the top it'll push true if the top value is 0. Now, something to note about is 0, you're going to see this a lot in YUL files and other like low-level assembly stuff. Is 0 is commonly used as a sort of inverse operator, right? So it's same as the exclamation point in front of a Boolean. So as a comparison example, we push 1, and then we push 2. We'll check equal. Of course, this is going to push false. That's going to be 0. And then we can use is 0 to invert that if we need to for whatever reason. So it'll invert it to true. And then at the end, we pop there. Next up, we have bitwise instructions. So bitwise instructions pop 1 or more values from the stack and perform some bitwise operation on them. Now, AND performs a bitwise AND on the top 2 stack values. So what this means is that every bit, or every 1 or 0 within this number, if you compare 2 values, the result is only 1 if both bits are 1, right? So if, actually, I think we'll have a bitwise example in a second, but basically, it's only a 1 if the 2 bits are 1. An OR operation will be 1 if either of the 2 values are 1. XOR is exclusive OR, so basically it will only push a 1 if one of the 2 values is 1, but not both. NOT will invert it, so whatever the value is, it'll invert that if it's 0, 1, if it's 1, 0. And then SHR and SHL will perform bit shift operations where we can shift the bits left and right. So as an example, over here on the left, there's a little bit of encoding here just showing you, basically what these numbers look like in binary format. And then on the right, we have push 1, push 2, you're familiar with this. But the SHL operation is going to shift the number 1 by 2 bits, right? So it's going to move it over 2, so we can see here, it starts at 0, 0, 0, 1, but after it moves over 2, it's going to be 0, 1, 0, 0. And then we can do the same thing to shift it right. So we push another 2 to the stack. SHR is going to shift it back to where it was. And then the NOT instruction, as you can see, it's going to flip every bit. So 0, 0, 0, 1 becomes 1, 1, 1, 0. So memory instructions can read and write to a chunk of memory. Now, memory is this linear data that can be read and written to during the execution of a program. So it's a different place in the stack. It's good for storing things like arbitrarily sized values and things like that. So mstore will store a 32-byte or 256-bit word to memory. Everything in the EVM operates on these 32-byte words. So we can store a full 32-byte word. We can actually also store a single byte or 8-bit word to memory. And we can also mload. So what this does is loads a 32-byte word from memory given some index in that memory. So here, we're going to push the number 1, then the number 0 to the stack. And what mstore is going to do is consume these 2, and it's going to say, at position 0, we're going to store the number 1. And it's going to be padded out to the full 32 bytes. And so if we, basically, after we've written to memory, if we push a 0 to the stack, or if we push any index in memory to the stack, we can call mload. It's going to consume that index and then return to us the value there. So in this case, pushing 0, and mload is actually going to pull out this 1. We'll go ahead and do an example for this one. Zoom in. Is that better? Cool. So we'll push the number 1 to the stack. Wait. Right. We'll push 1 to the stack, then we'll push 0 to the stack, and mstore is going to treat the 0 as the index and the 1 as the value. And when we want to retrieve this later, we can push 1. Oh, sorry, push 0, and then mload. And so if we step through this, we'll see the stack has a 1, then a 0. mstore is going to put in memory that first word is a 1. And whenever we want to load from this, we start at index 0, mload, and it's going to push that value back onto the stack. Now getting into context instructions, specifically the ones that read from the local context. And this is not a comprehensive list, there are actually quite a few, but some of the important ones, caller pushes the address that called the current context. So if you're familiar with Solidity, this is the same thing as message.sender. We have timestamp, which pushes the current block's timestamp. Again, same thing as block.timestamp. Then we have other things like static call, which can make a read-only call to another contract. So if there's a function that sits on another contract, we can call that through static call, and as long as it doesn't write to persistent storage or doesn't update the state of the EVM, then we can read from that. Call data load can load a chunk of call data into the current context. And so what the call data is basically the data that is sent to your contract to tell you a little bit about what function to execute, what arguments it has, and things similar to this. So call data load can actually pull some of that data for you. sload can read a piece of data from persistent storage on the current contract. So contracts can only read their own storage, but basically we can read any slot using sload. So as a quick context example, we can use the caller instruction, and it'll push that message sender to the stack. We can, for example, let's say we want to see if the caller is an owner of a contract, right? And let's say the owner is stored at slot 0 in storage. What we can do then is we can use push 0 and then sload, and that's going to load from the first slot whatever data is there. In this case, it's our owner, and then we can compare them by using equal, right? So this is like the simplest representation of how to check if a contract is owned by somebody. Next, we have the context instructions that can write. And again, non-comprehensive, lots of stuff going on here, but some of the really important ones. store can store data to persistent storage. Login can append data to the current transaction's logs, where n is the number of special indexed values in the log, right? So if you've written Solidity, you see the events, you see sometimes that keyword indexed. All of these are actual indexed topics within this event. Now, something to note here is in Solidity, you can only have 3 indexed arguments in an event, but you can actually have up to log 4. And the reason for this is the very first topic in any log is actually the signature of an event, right? So it's basically just a SHA-3 hash of this event's signature, which we'll get into a little bit more in a moment, and then the rest are the index topics that you specify. Next is going to be call. So it makes a call to an external contract or to external code, but this actually can update the global state, right? So there's no restrictions on solely reading or anything like that. And then finally, we have create and create to. And so what these can do is actually deploy code to a new address, creating a new contract. So it's just a quick example of what you can write. For example, maybe we want to store the last timestamp that some specific thing happened, right? So we can use timestamp to push the block's timestamp to the stack. We can push a 0 and then store, and what that's going to do is store that timestamp at slot 0. So as a quick review, again, the EVM has a fairly simple instruction set. Most of what we've gone through, this is the bulk of what's actually going on under the hood. Of course, this section didn't cover every instruction, but it serves as a foundational understanding for Yule in the following sections. And so to the left, there's a simple contract that will store the caller's address in persistent storage and then return true to indicate success, right? So stepping through this, we have the caller. We're pushing slot 0. We're calling store, so that's going to store the caller address in storage. Next, we want to store true or 1 in memory, and we can store that in the very first slot. So we'll push 1, which is true. We'll push 0, which is a slot in memory. We'll call mstore, which puts that in the memory. And then to return, we actually have to give it 2 arguments. 1 is the offset in memory, where we want to return data from, and then the second is the word size, or the memory size that we want to return. In this case, it's actually just going to be a single 32-byte word. So we'll push OX20, push 0, and then return. So any questions so far on the instruction set?
Can you give an overview of what the cipher code for your code? Like, right? What would they show?
Right here?
Yeah,
Yeah, so these are the representation of the instructions here. So here, we have like push one, and store, etc. Whenever we run this, we can actually step through. We can step through the instructions, and this is just a representation here. So we can. Right. So memory is here. Anything that's written to memory goes into here. Anything on the stack is going to be here. And then persistent storage, if any, is going to be down there. And then return value, if any. The stack can be 1,024 items. Now you'll notice in Solidity, you'll get the stack too deep error. And actually the reason for this is you can only swap and duplicate items 16 deep, right? So there's like a limit to how many local variables you can have because Solidity actually stores these variables on the stack. So once it gets beyond that, Solidity doesn't have like an easy way to access that without losing information. So that's why you see that a lot. But yeah, it actually can technically go like way, way, way deeper.
The memory is frame dependent, right? Like when you do a static call or
We want to store that in memory and basically we'll just go ahead and I'll just go ahead and answer some of these quick questions right now while they're getting set back up. So you mentioned like return data, right? Okay, so there are actually special instructions to handle return data. You have return data size and return data copy. And so what you can do is whenever you actually make a call, you're not actually getting all that stuff back. Solidity kind of does a little bit of magic for you there. But basically what you can do is use the return data size instruction. It's going to give you the size of whatever was returned, and then you can use that to copy in the memory.
there's like a special place of memory for return data that you can access in your frame. Basically, it's like this buffer in between the frames.
Yeah, so it's not stored in memory per se. Like it's only stored in memory whenever you explicitly do it. But yeah. Of log 0. Oh, I guess we have the spec now. Yeah, actually, I don't want to get too far ahead of myself because we are going to do some more logging stuff, but I will go ahead and let you know. So basically, every log instruction, it takes up to the number of topics which are on the stack, and then it actually also takes a memory pointer and size. So even if we don't log any topics per se, we can actually just log like a big chunk of memory, and so that's one way that we can push data to that as an anonymous event. It should be within the event logs. I'm not exactly sure how the client libraries decode anonymous events. Obviously, it's a little unusual to see those nowadays, but yeah, we can, if we have time at the end, we can actually probably just break open a remix, see how it works. Are we good?
You mentioned there were two opcodes for the previous platform. What
Yes, so Create 2, one, it's, I believe, a bit more gas efficient. And there's actually a way to deterministically deploy to specific addresses from on-chain using Create 2. So it's just kind of choosing the utility of exactly which one you want to do. I hope this wasn't being live streamed. Are we good? Okay, cool. Sorry, I didn't want to go too far and then we have to go back. Great. So the hardest part is over. That was all the really like in-depth stuff that will kind of give you this foundational knowledge for how to write Yule. Yule, thankfully, has a much higher level syntax. So what Yule is it's a low-level language that can be written in inline Solidity, or as a standalone language. You can write Yule files by themselves, but you can also use it as a compilation target. So it also acts as an intermediate language that you can compile other high-level languages to. Built into the language are most EVM instructions. These are callable as functions. There's basic control flow support and functions, well, user-defined functions. Now you'll notice whenever we start looking at Yule code that the stack is largely abstracted away, with the exception of a built-in pop function. So if there's some value that maybe you don't need that's returned from a function, you can just pop that immediately. So here we have the syntax overview. Now note that the keywords object and code are actually only used in standalone Yule files, so chances are you're not going to be touching this if you're just writing inline assembly. One other thing to note here before we start stepping through, Yule does have the if statement, but it does not have the else statement. So to handle multiple cases, we can actually just use a switch. And then the for loop functions very similar to what you see in other high-level languages. Obviously, the syntax is a little bit more funky, but it still does the same thing. So stepping through, starting at the top, we have the assignment syntax. So notice we have a colon and equal sign. So anything on the right side is assigned to the left side variable. If the variable is being newly declared, if we're not reassigning, then we need to use the keyword let. For the function syntax, we have the keyword function, the name of your function, any arguments, and then return variables from that. And so inside this function, you can see the letter C is already declared as a variable implicitly by saying this is a return value. And then colon equals will assign the sum of A and B, right? So you can see this is a lot simpler to read than just pushing things and adding and things like this. Another thing to note about these internal functions is that the return is implicit, because return itself is actually an instruction that returns to the caller itself. That's not what this is doing. This is actually just manipulating some items, leaving an item on the stack, and then jumping back from wherever this function was called. So here we have the if statement. In this case, we're checking if A is equal to 0. And if this is true, then we can execute some code inside of that. In this case, we're just doing a revert. Below this, we have the switch. So the switch, we have a value that we want to compare against, and then each case is going to have the value that this variable could be, right? So case 1 means if A is equal to 1, then we'll handle that. Yeah, comments are wrong here. Case 2 is if A is equal to 2, and then default is our fallback, right? So if nothing else matches, if we need to just do some logic to handle the rest, we use default. And then finally, we have the for loop, right? So first we have let I, we're assigning it 0. So this is your I equals 0 part. In the middle, we have that comparison. So it's less than I and A. So as long as I is less than A, we're going to continue iterating. And then next we have I being assigned basically the sum of itself and 1, right? So we're basically incrementing it. And then inside of there, we can iterate and do our looping logic. So as a quick comparison to mnemonic bytecode, over here on the left, that was the code that we wrote a moment ago to store the caller in storage, store true in memory, and then return that from memory. And then over on the right side is how we do it in Yule. So a lot less verbose. And so now we're going to jump into Yule in Solidity. And this is really important because not very many people write standalone assembly files these days. Most of the time, you're going to be operating within the bounds of a Solidity file. So you need to understand what standards and abstractions Solidity has created. So some of these include the call data layout, which is a layout of that data that gets sent to your contract, the memory layout, the storage layout, event logging, and errors. So call data layout, per the application binary interface or ABI standard, the call data layout is as follows. So first, the first 4 bytes are the selector of a function. And basically this is the SHA-3 hash of a function signature. And that includes the name and then any argument types within that. Next, after the first 4 bytes, Each argument is padded to 32 bytes no matter what. Even if it's a UN8, it's always up to 32 bytes. If an argument is of dynamic size, then the slot where it should be is actually going to hold a pointer to a place in call data where the rest of the data is. So if we have, let's say, a string that's over 32 characters, it's not going to fit in a single slot. What we have is a pointer that says, okay, after everything else, here's where the string starts, and it's just going to go, and there are other ways to determine how long the string is. So as a quick visual representation, here we have the transfer function, which this comes from the ERC20 standard. So first up, we have the signature. So that's transfer. It has address, uint256. Now all we're actually hashing here is transfer, parentheses, address, uint256. That's the only part that we're hashing here. So we can see the hash, full hash digest here. We're actually going to clip that to the leftmost 4 bytes. And then the actual call data layout of one of these is going to be those 4 bytes followed by an address. In this case, it's going to be the target to whom we're sending the ERC20. And then the next is going to be the value, right? So even though these, like an address is not a full 32 bytes, we're still padding it all the way. Next is going to be the memory layout. Now this one is really, really important because per the Solidity documentation, the first 4 slots of memory are reserved. Now slot 0 and slot OX20 or slot 32, these are actually scratch space. So you can use these, whenever you're doing things in inline assembly. The OX40, though, is the free memory pointer. So basically what this does is as memory is expanding, Solidity will actually track how big memory is and when you can start adding new things to memory. And so what we'll actually do in some of this YOL code is we'll actually load from that to figure out where we can start storing things in memory. So it's really important, if this does get overwritten, you have to make sure that you have that variable on hand, right? So you can increment it if you store more things in memory, et cetera, et cetera. And then OX60 is the 0 slot. So the 0 slot is reserved specifically for whenever you're allocating new arrays, I believe. This is like basically a big no-no zone anytime people start overriding this. It's not a very good security practice. You have to be very, very careful about it. So I'm not going to recommend it, but we have seen it before. We'll probably take a look at somebody who does that a little bit later. Now, dynamically sized arrays will occupy 1 slot, which holds that pointer to where the actual value is in memory. There's another slot that indicates the length, and then every slot after that is reserved for a single element. So if you have 5 elements, even if they're small values, they're going to occupy 5 full slots. Now, byte arrays and strings are similar, with the exception that their elements are tightly packed and aligned to the left. So for strings, you're basically using a single byte value to represent a character. So in this case, on the byte level, it is equivalent to byte arrays. We're going to pack those as tightly as possible. So as a quick memory example, we're going to step through this. Now, it's a function. It's pure. It's going to return some bytes, right? And so what we're going to do in here is first load the free memory pointer. So again, we're going to load from OX40. We're going to declare this or assign this variable data, because remember, anything that's declared bytes memory. Okay. Zoom in? Oh, yeah. Oh, I thought so. It is not letting me zoom in. Yeah, sorry, this is not going to let me zoom in here. But I'll go over basically every line, so we'll step through here. So yeah, the data, basically what we're doing is storing that pointer to where the bytes are going to be. We're storing that. Next, we're going to store the length, the length of the byte array at this pointer. So at the free memory pointer, we're going to store bytes length. In this case, we're just going to store 4 bytes. It's going to be 1, 1, 2, 2, 3, 3, 4, 4. We're going to store that. Then in the next slot, we're going to, first we're going to increment the free memory pointer, right? So we're keeping track of this. We're keeping track of how much, how much memory is being used here, how much memory is being written to. So we're going to increment that by 32 bytes or by a single word. Then we're going to store at this new location the bytes that are going to be padded. They're going to be packed to the left. After this, we're going to increment the free memory pointer one more time, and we're going to store the basically in the free memory pointer slot, we're going to store this updated free memory pointer, right? So basically, as we're incrementing this, we're keeping track of where the new free memory is. And then once we're finished with all of this, we're going to store it at the OX40 slot. Any questions?
Question. When you have solidity, when you resize the dynamic array, it moves in memory to the location essentially?
Right, so it's going to, again, let's say you append an extra byte to the end of this. It's going to store that extra byte at the end. It's going to keep it packed, and then it's going to increase the...
Let's say you have allocated something else in memory before pushing. That's what I meant. Like if you know there's something at the slot right after that array, and then you push, it will move essentially, right? All of it.
It should. I haven't tried that. We can actually try that as well. We can hop over to Remix and try that. Yeah, it would make sense if it would, right? Because then it would just get really, really confusing, right? Right, you're right. Sorry, thank you. Storage.
Yes.
Right, so in Solidity, you do have to specify the length ahead of time. Thank you.
You have said that the dynamic size array like and one slot for each element, right?
Right.
What if I have some kind of the structure that I want to create the arrays of them, and they don't fit on one slot?
So like a struct, like a memory struct. So memory struct. So struct actually acts similar to a dynamically sized value. So it's actually going to be a pointer to that as well.
Okay.
Right. Right. So whenever we store, so the first one we're storing the byte's length, right? We're storing the number 4. Even though it's just a single value, that's actually occupying a full 32 bytes. So we want to increment it by the full 32. Any other questions? Great. So next, we're going to have storage. Now, storage is actually going to be a few different cases here. First, we'll start with statically sized variables. So per Solidity's documentation, storage layout starts at slot 0. The data is stored in the rightmost bytes of that slot. Now, if the next value can fit into the same slot, obviously this is determined by type and the maximum value, it will actually be right aligned into the same slot. So you can actually pack variables into storage. You can do the same thing with storage structs. And then immutable and constant values that you see in the contracts, they're actually not stored in storage at all. So basically what these are is they're replaced at compile time with the exception of immutables. So if you have an immutable that can only be determined at deploy time whenever it runs to the constructor, it'll actually replace every instance of that in the bytecode. So as a quick example, we have a contract. It's got 5 values in it. First is going to be a full uint 256. So we want to occupy an entire 32-byte slot with this. Next, we have 2 values of 128 bits, so basically 16 bytes each. So these can actually be packed into a single slot, and we'll see that they are. So B is 2. It's here in the rightmost bit. And C is packed in the next rightmost place in that slot. And then we have, finally, 2 uint 8s, which are stored here. All right, so everything is packed as tightly as possible in storage whenever we're doing this layout. Next, for dynamically sized variables, again, per the documentation in Solidity, a mapping slot is the hash of the key value concatenated with the storage slot, right? So let's say, for example, in a balance mapping in an ERC20, it maps an address to a uint 256. Let's say it's in slot 0. What it's going to do is whenever you need to read or write to this, we're going to take that address, pad it to 32 bytes, concatenate that with another 32 bytes, which is the slot. It's going to be 0. And then we hash all of that, and that's where the actual value is stored. Now, dynamically sized arrays, it stores the current length in whatever slot it occupies, and then its elements are stored sequentially starting at the SHA-3 hash of that slot number. Byte arrays and strings are stored the same way as other dynamic arrays unless the length is 31 or less. If this is the case, then what's going to happen is all of that's going to be packed into a single slot. left aligned, and then the length of that is going to be packed, or is going to be placed at the rightmost byte. And it's going to be 2x the length. So looking at this one, we have 3 storage variables. We have a string, a array, and a mapping. So looking to the storage layout, first, over to the left, we have 61, 61, 61, 61. These are the 4 A's. And then over on the right, we have 8, which is 2 times the length. In the next slot, we're going to store the length of this data value. It's going to store 1 and 2, right? So what's going to happen here is whenever the code is executed, it's going to see that the length is 2 here at slot 1, and whenever it wants to access these values, it's going to hash slot 1, and that's going to point down here to OXB1, et cetera, et cetera. And then we can see here's the first value, and here's the second value. And then finally, we have the mapping. It's mapping an address to a uint256. The actual storage slot of a mapping is always 0. That doesn't mean that it's not incremented. The storage is still incremented, but this slot is always going to be 0. And then any addresses that are mapped to, of course, will be that hash, right? So OXE9, et cetera, et cetera. So one more thing to mention, something that's really important to note, is storage in regards to inheritance. So Solidity uses C3 linearization. So basically, in the context of storage, what this means is storage slots in a parent contract precede the child contract storage. When a child has multiple parents, the order of the parent's storage is set by the order of inheritance. And this process is repeated recursively, and storage packing rules are still in play when applicable. So here we have a basic inheritance example. We have parent 0, it's going to store A, it's going to be 1. Parent 1 is going to store B at a value of 2. And then finally, we have child, which is going to inherit parent 0 and parent 1, and it's going to have its own value C, and that's going to be 3. And looking through the storage layout, first we have parent 0's storage, then parent 1's storage, then child storage. This is really important to note, especially with things like proxy contracts. You'll see in some of the Open Zeppelin implementations these storage paddings and things like this for upgradability. So next up, we have event logs. So per the standardization, event logs follow the following rules. They can have up to 4 topics. The first topic is always that hash of the event signature. So it's going to be the event name, parentheses, and any types. And then non-indexed topics are logged by storing them in memory and then passing to that log instruction a pointer to where that memory starts and how big that memory is. So as an event log example, at the top we have a hash, and that's going to be the event signature hash. Next, we're just going to have A and B, simple constants. Now in Solidity, this first function is how we'll log this, right? We say emit, the name of the event, and then any arguments that go to that event. Next, we have log in YUL. So this is actually what's happening under the hood whenever you do this in Solidity. So first, we want to store, note that B is not indexed, so we want to store that in memory. And then A is indexed, so we're going to have that on the stack, right? It doesn't have to go into memory. So first thing we do is we're going to store B. We can just store it at slot 0. We're not going to be dealing with memory after this, right? The function's going to end. So we store at slot 0 B, and then we call the log2 instruction, and what we're going to pass to it is a memory pointer, in this case, slot 0 of memory, the size of memory, which is going to be 32 bytes, the event hash, which is going to be topic 1, and then the index topic A, which is going to be topic 2. So next we have errors. So per the standardization, an error consists of a 4-byte selector and some error data. Now Solidity actually has 2 predefined errors. This is error and panic. But since Solidity 0.8.4, developers can actually define custom error types where you can have names and arguments, and it's actually a bit more efficient than the standard require Boolean string. The reason for this is the Solidity defined errors. First is panic, and it's got a uint256. So this is things like divide by 0, overflow, underflow. That's when the panic comes into play. Each one has its own code. It's in the documentation. And then next is the actual error. This takes a string in memory, and you can see. So first is a panic code. So we have these 4 bytes, which is the panic selector. and then the next 32 bytes is going to be the actual panic code. In this case, it's 1. Then the next one is going to be require, or what is standard with require. We pass it a Boolean. If it's false, it's going to throw this error with a string in it. Now note this actually takes up a lot more memory because we have the error selector. And remember, per the standards of strings, we first have to have a pointer to the string and then the actual string itself, right? So that's going to occupy extra data. Right, so basically because the error selector is only an offset of 4 bytes, that's actually not padded to the full 32. So right after those 4 bytes, we're going to start putting other data. Any other questions? Great. All right, so next we're going to do applied Yule plus solidity. So we're actually going to hop over to Remix. And that's remix.ethereum.org. And from that link tree earlier, we actually have some boilerplate code here. Let me make sure this is big enough to see. So you might want to just copy paste this from that link if you're going to be following along, because lots of already pre-encoded data and all that kind of stuff. So I'll give you guys a minute to get that pulled up, copy pasted, all that good stuff. Okay, we'll give it just another second.
Is that you using Canita so is on the remix link that is part of the link?
Right. Yep, so that's going to have the code. It's going to be in a gist, but you can just copy paste that.
The remix link, there's a GitHub link. Yeah, you have to copy from the GitHub to the remix. It doesn't load automatically to the next version.
Yes, one moment. Maybe not. I'm going to write it right here. So it's going to be the link, linktr.ee/Ethereum assembly. Hopefully internet doesn't rug pull us here. All right, we'll go ahead and jump into it. So everything here that's predefined, this is just for the sake of us not having to go and encode stuff in hexadecimal and all of that, right in the middle of the workshop. So just looking through these constants really quick, we have the length of the name. In this case, the name is actually going to be Yule token. So the length is going to be 9 characters, and then in here we have padded over to the left the string. Next we have the symbol. That's going to just be Yule, Y-U-L, all caps. And so here we can see the length is 3, and these are the 3 characters for that string. After this, I went ahead and hashed the selectors for two custom errors that we're defining here. One is going to be insufficient balance, and the other is going to be insufficient allowance. Now, no insufficient allowance, we're actually going to pass an address of the owner and the spender in here, and this is going to give better error messages for client libraries and for users. So hopping into this, first thing we're going to do is we're going to define the name function. And we're going to make this pure. We're not storing anything in storage. We're actually just going to return a constant. I'm just going to return a string in memory. Okay. Now, what we're going to do, if we remember the standard for storing strings in memory, first is going to be the pointer. Then the next slot is going to be the length, and then the slot after that is going to be the actual data itself. So we're going to do 3 memory writes, and then we're going to return from that. So first we're going to mstore at slot 0. We're going to store OX20. And that's where the actual data is going to be. It's going to be a 32-byte offset. Next, we're going to store, oh, no, hold on, safety. Memory pointer, we want to load from memory. So we load that. Now, this actually should be fine in this case. Like we know exactly where it is because nothing's been written to memory, but it is good practice as often as possible to use this free memory pointer. So we're going to load from OX40. Sure, yeah, so let's say, so I mean, if you just start writing to the 0 slot, and in this case, we're going to occupy 3 slots, that's going to take slot 0, OX20, and OX40. So it's actually going to overwrite the free memory pointer. Now, in this case, we're actually returning from assembly, so we are safe here. But the problem is, if we're doing some assembly, let's say within a function, and maybe there's stuff that's happening after that, Solidity is going to trust that whatever value is in OX40 is the right value. So if we overwrite this to something strange, in this case, it would be the string padded over to the left, which is actually technically a massive number. This would actually consume a massive amount of gas and realistically probably revert. But yeah, so basically, as much as possible, we want to use, basically load whatever is at OX40 that's going to point. Normally it starts at OX80, so that's after the 4 reserve slots. But again, for the sake of keeping it safe, we're going to do it like this. So we mstore at the mem pointer. We're going to store the length, or sorry, not the length, the OX20 pointer. After this, we're going to store 32 bytes later, we're going to store the actual length. So we're going to add the mem pointer and OX20. So we're increasing by a single word size. We're going to store the name length. Next, we're going to store at an OX40 byte offset.
The first mstore shouldn't be storing mem plus 32.
You mean like after the first mstore?
In the first mstore, instead of 0x20, shouldn't we be storing the next slot after mem pointer?
No, so this is actually an offset from this value itself. So yeah, so the OX20 offset is just pointing to the actual length itself. So we stored the pointer, we're storing the length, and now finally we're actually going to store the data. And so what memory should look like right now is starting at the free memory pointer, we have the string pointer, the string length, and then the actual string. And so this is going to occupy 3 slots, which is OX60. So what we can do is return, starting at the mem pointer, we can return OX60 bytes. So very quickly, we're going to compile this. I'm on Solidity 0.8.17. We'll check that the compiler is 0.8.17. Everything's all good. So now we're just going to deploy this to a local virtual machine. And here we have the name function. Whenever we hit it, it's going to return Yule token for us. All right, so next we have the symbol function. It's going to do basically the same thing. The only difference being we need to store the symbol length and the symbol data. First, we load our mem pointer. Then we store in memory at the mem pointer the string pointer at an offset of 0x20. We'll store the symbol length. And at an offset of 0x40, we'll store the symbol data. And then same thing as before, it occupies the same number of slots because everything is padded. We'll return mem pointer 0x60. Now note in this case, we're actually not incrementing the free memory pointer, and that's because we actually are returning from the assembly itself. If we were to break out and continue doing things, we would actually want to actually store what the new free memory pointer is. In this case, we would increment it by 0x60. Next up, we're going to do decimals. It's going to return a uint8. So first, now in this case, we're actually not occupying very much memory at all. We're actually only occupying a single slot. So we can't actually just write to the very first slot, right? It's mostly whenever you need to write 3 or more slots that you want to actually do it at the memory pointer. In this case, we're going to do a little bit of a hack there to keep that in the lowest slot. So we mstore at 0, the number 18, because we're not bad people and use 6 as decimals. And then from there, we're going to return from slot 0 in memory. We're going to return 0x20. Even though it's a uint8, it's stored at the rightmost bytes, so we need to return that full 32-byte word. All right. Now that we're done with all of that basic boilerplate stuff, let's go ahead and set up a mapping. This is going to be mapping an address to uint256. We're going to make this internal in this case because I want us to actually do it in assembly and see exactly what's happening. Obviously, we can just make this public and make it a lot easier, but we'll say internal underscore balances. Next storage slot we're going to need after that is going to be the allowances. So we're going to map an address to a nested mapping, which maps an address to a uint256. I'm just going to comment here what this is actually mapping to. Great. All right, so next we're going to do the balance of function. It's going to take an address. And we're actually not going to name this variable because we're going to manually load it from call data so we can see how call data is working, but it is going to take an address. It's going to be a public view function because we are going to read from state, and it's going to return a uint256. All right, a quick time check. Great. Okay, so this is where it's going to get weird. Remember, we're mapping an address to a balance. And per the standard, what we need to do is we need to hash the address and then the slot in memory, or a slot in storage. In this case, it's 0, so we're going to pad an address, and then we're going to put 0, and then we're going to hash it. But the hashing function actually reads from memory, so we're going to need to use some memory to do this. So first thing we do is we're going to mstore. Actually, no. We're going to assign this variable for readability. We'll optimize a little bit in a moment. So first thing we want to do is get the, let's say, account. And so what we need to do is load the address from call data. Now, if you remember, the first 4 bytes are the function selector, and then the next 32 bytes are the first argument, in this case, our address. So what we'll do is we'll call data load, and we're going to do that at an index of 4. So it's going to take the next 32 bytes and put that into the account variable. Next, we're going to store this in memory. At slot 0, we're going to store account. And then at slot OX20, or at the 32-byte slot, we're going to store just 0. Next, we're going to get the hash, which is going to be kekak 256. And what this is going to take in assembly, now in high-level Solidity, what this is going to take is like a string or bytes, but in low-level Yule, it's actually going to take a pointer in memory and the size in memory. So in this case, we're going to start at slot 0, and we're going to consume 2 different slots, right? So OX40. So this should actually be the key to this person's balance. So what we can do from here is we'll say balance, and that's going to be sload. Oh, no, balance is a reserved word. Hold on. There we go. Account balance is going to be sload at that hash, right? So we're loading from persistent storage this slot. Next thing we want to do from here is we want to mstore. Now at this point, we're not actually going to need what's in slot 0 and slot slot 1, like 0 and 32 here. So we can actually just overwrite that with the account balance. Okay, and then finally, we're going to return. And so that's going to start at slot 0, and it's going to be OX20 bytes. So this is kind of like a more verbose version, so we can see exactly what's going on with variable names and things like that. But let's go ahead and do just a little bit of optimization and seeing like what you might actually see in production, right? So account is only used once, and that's loading here from call data, so we can actually just remove that and put that here, right? So we're storing in memory at slot 0, whatever's in call data starting at 4. Here we have this hash. Instead of declaring a new variable, we can actually just load that straight from storage. And then instead of declaring an account balance variable, we can actually just replace that as well. Right, and so now it should be functionally exactly the same. We're storing the first argument in memory at slot 0. We're storing the slot number in slot OX20. And then we're hashing that, loading from storage, putting that value into memory, and then returning from memory. And so this is the full process of what a balance of function is doing.
What is the body in the hashing function?
That's the length of memory so far. So these 2 slots. Sorry?
Because you have 2 slots, right?
Exactly, yeah.
The second half of
Exactly, because it's in the first storage slot. We can do that at 0. Actually, something else we can do here, since this is already implicitly 0, we could remove that, but again, for the sake of safety, we'll just leave that for now.
I think I've seen that the assembly are just empty, it will not give an error. What then will be returned? 0?
Return with like just parentheses?
Yeah, it's without any code.
Right, so in this case, it's actually going to give us an error because it actually is.
The whole assembly code. Oh, it's empty. So yeah, it's just the object. It's like basically, if you will not give a return statement, what will happen? What will be returned?
Oh, right. So like basically, if we don't say like return down here.
No return enter.
Oh. Yeah, so in that case, it's actually not going to return anything. Like if we did this, it would actually like load from call data, load from storage, put it in the memory, but it wouldn't actually return anything to the caller.
But the function itself, this declare will return something. I guess it would be new value of 0.
Right, so I mean, you can see here it gives us compiler warning. Let's see, unnamed return variable can remain unassigned. That's actually a weird one. Let's try that. It's going to give us a warning, but we're going to try it anyway. By the way, this is using Remix is a fantastic way to try out these little edge cases. If you're ever not certain how something works, this has been an invaluable resource to try these things out. So let's go ahead and give it a try. Balance of, we're going to need an address. We'll just copy this one. It returns a 0. Okay, so I guess in that case, if you don't explicitly return, then Solidity will actually insert a return statement for you, and it's just going to return, nothing at all.
Okay, and the next question: what if I want to load from the call data only 1 byte, not all 32 bytes, but only 1 byte?
So call data only loads, using call data load, it only loads 32 bytes. So in the case of, like, for example, if you need to figure out what the function selector is, right, you can only grab the full 32 bytes. So in this case, you would actually use bit shifting. You would want to, those 4 leftmost bytes, you want to shift them all the way to the right.
And the rest will be still the same. It will not be like the carousel like this.
Right, it does not wrap around, they'll all be zeros.
So yeah,
So just adding this alone shouldn't add any extra opcodes. This is just like a abstraction for the high-level language. But I believe we could actually just access it like this. So this and what we were doing a moment ago is actually functionally identical, right? So either we can like manually load from call data, or if we name the argument, we can actually just put that in there. Right. Yeah, because the function selector will be the same, and then if it's not actually used, it shouldn't consume. And I mean, of course, there will still be a place in the call data for it, but if we're not explicitly using that variable, then there's no point in which that's going to be loaded from call data by Solidity.
we are storing the length, storing the data in there, then returning the basic to that variable.
No, so what this actually does is, so the mem pointer tells you obviously where in memory to get the value, and then OX60 is the length. But what this is actually going to do, in this contract, it's going to finish executing, it's going to stop executing, and then whoever called this contract, whether it's an EOA or another contract, it'll actually return that data. So it'll take that chunk of memory, in this case, 60 byte or OX60 bytes from free mem pointer, and that's actually going to be returned, into it's going to be returned either to the client library, like Ethers or Web3.js, or it's going to be returned to another contract encoded as a string. Right. As soon as we call return, it's actually going to stop execution from there. So even if we put in anything after that, as long as it always returns, we'll never go there.
So each function has its own memory and stack when you execute, or they share across, like if you go, I don't know, in decimal, you go symbol, they share the same memory, or each like execution?
Right, great question. So anytime that you call a contract, it's going to create what's called a context. And so this context is going to have a clean stack, a clean memory. It's going to be able to access the storage at whatever address is there, right? And then other contextual information. So basically, anytime a function is called on this, everything is a clean slate. So it's going to read and write from that same clean slate. And then once the function finishes, it stops and the memory is gone, right? So in this case, like, they're technically writing to the same storage slots, but they're never executing at the same time, so we don't have to worry about any kind of like memory overwrites or anything.
But it's an internal function shares, right? Because the internal function gets in line. Like if you're calling in the same contract, the internal function of that contract.
So if you call an internal, yes. So if you call an internal function, actually at compile time, this is a little bit confusing about Solidity, is that you have like public and internal functions. Public functions explicitly, take some information from the caller, and then it's going to return some information based on that. Whereas internal functions, there's actually what it does is it takes a number of items on the stack. Let's say your internal function takes 3 arguments. It's going to expect 3 values on the stack, and then it's going to operate on that. And if it returns anything, it's actually just leaving values on the stack. So inside of internal functions, whenever you return from that, it's not actually using the return instruction. It's actually just leaving it on the stack and jumping back to where it came from.
memory pointer gets compressed? Is that like a bolded state assembly order?
Right. So the first thing that happens during the execution of a contract, at least per Solidity, is we're actually going to store a free memory pointer. So like the first two slots, 0 and OX20, these are always going to start out as 0. OX40 is going to have that free memory pointer, and then the next slot after that, of course, is the 0 slot. So we don't put anything there. We can actually take a look briefly. If we compile this and we look at compilation details, so you'll notice the first few opcodes here, we're going to push OX80, then we're going to push OX40, and then we're going to mstore. And what that's doing is storing OX80, which is the first free memory pointer. We're storing that at slot OX40. And this is actually like a big telltale sign that a contract was written in Solidity. This always happens first. Every Solidity contract starts with 60, 80, 60, 40, 52.
You keep on feeding the memory, and I mean, keep on the memory, putting all these like, further things, beginning of all that sort of stuff, right? Maybe, for example, instead of ketchup each memory be able to operate on, if I use ketchup in another function and then ketchup in another function, and the span function, if it was one function, actually, you wouldn't need to like extend memory. It could be used as, storage, obviously, because storage is ketchup.
So you mean like when you have multiple internal functions, or right? Yeah, exactly. So what Solidity actually does is those first two slots, the reason that they're kind of reserved is that's actually normally used as a sort of scratch space for hashing. So normally you're hashing two values together, so that's where we'll put that and then hash that together. Right. So per the standard of how strings are stored in memory, it's always a pointer to the string, and then the length of the string, and then the actual string itself. So in this case, it's kind of a formality, but it's really important to have that OX20 there because whenever we return it, the client libraries expect it to be encoded as. Actually, no, it does that return that. We're going to try it. So let's call name. And what we can do here, this is another great way to look through transactions and find things you might not be sure about. Let's break this out. It's not going to let me make it bigger. Okay. Right. So what we'll do right here at the very end, let's take a look. So we have some memory laid out here, mostly zeros. It looks like, hold on. Let's step through this really quick. I really wish this would let me make it a little bit bigger here. But so here's the state of the stack, right? In this case, we're going to push the free memory pointer, which is OX80. We're going to push the length, which is OX60. And what that's going to do is point to slot OX80 in memory, which is going to be here. And it's going to go for OX60 bytes. So here's the first, here's the second, and then here is the third. Right, so because this actually gets returned with it, client libraries are going to use this to actually decode strings. So if we didn't return this properly, it would actually throw an error. Like it wouldn't know how to decode it. It would just give you a bunch of bytes back, right? So in that case, it is sort of a formality, but it is important, to make sure that the client libraries know how to decode. I think there was one more question. Right.
So it's what you bring compatible with that. I mean, memory. Like you can call the name.
Call it internally. Oh, you mean like if I say like this dot name?
It's a function here. Put it on the stack. And then just seeing memory instead.
Right. So we wouldn't want to use the return instruction inside of an internal function, like if it's being called internally. I mean, you can use that, but just know that that's going to stop execution at that point, which is not what you want, right? Because that'll actually return back to the caller. So if you're trying to like return from an internal function, you're actually just jumping back to the main function, and then that's where the actual return instruction is going to be.
In the line 36, the ATM store like 20. Yes, that's an offset.
Right.
Okay, so where you're storing the data. Okay, so if you store the data, I don't know, the 16, for example, I don't. Okay.
Yeah. So what that actually is it's OX20 from that place in memory. Right. So balance. Let's go ahead and put that return back. Okay. Next, we're going to do the transfer. And this is where it's going to get weird. We're going to have basically some conditional logic in here. Remember that overflow and underflow checks only happen in Solidity 0.8 and after. So basically anything before that and then anything assembly is unchecked, which means if somebody tries to transfer out more than they actually have, the EVM is not going to stop that from happening. It will actually underflow, roll back over to the very top, and then they're going to have some obscenely massive amount of tokens. So we want to make sure to check beforehand that the sender has enough tokens before they transfer out. So per the standard, it's going to be a non-payable. So we're actually just going to call it public, and it's going to return a Boolean. So first thing we want to do is load the caller's balance, right? So what we need to do is hash, that information that we did before. So let's say, we're going to mstore. One more time. So we're going to get the mem pointer by loading from memory. From the mem pointer, we're going to store the caller's address. In this case, we can get that by calling caller with parentheses. At the next slot, so mem pointer plus OX20, we're going to store the balance slot, which is actually going to be 0. Then we're going to hash. And let's say caller balance. So we hash these two starting at mem pointer with a size of OX40. And we're going to take that hash and use it to load from storage. So now we want to check and make sure that the caller's balance is at least as big as the amount. Now that we've done the call data loading, we're actually just going to do this for the sake of time. We'll say value and receiver, just to keep things succinct. So we want to check and say if less than, so if caller balance is less than the value to transfer, we're actually going to do some revert logic. So we're going to take insufficient balance selector. Now this actually isn't going to take any arguments, so all we really need to do is actually just store this one value. Again, at this point, we're reverting, we're about to stop execution, so we can basically just write to the 0 slot. This can't cause any harm. So mstore at 0, the insufficient balance selector, that's going to be that 4-byte selector padded to 32 bytes, and then we're going to revert. And revert actually functions the same way as the return instruction. So we're going to give it a pointer and a size in memory. In this case, we're doing the full OX20. I guess we could also just do OX04. And so that's going to revert with that. And this is good because whenever we revert with the selector, client libraries are going to have access to this ABI. It's going to see that there is this error called insufficient balance, and that's the selector. And then we can actually do some better error handling on the client side. Sometimes you'll see people revert with 0, 0, and that actually just reverts with nothing. And obviously this isn't super helpful. So As often as possible, even though it does take a long time and it is annoying, make sure to store proper error information. Okay, so from here, we know that the caller balance, like if we're at this point in the code, we know the caller balance is sufficient. So what we'll do is we'll deduct the value from the caller balance, and then we'll add it to the receiver's balance. Oh, just one moment. Perfect, just double checking. Okay, so we add these two together, and then we'll say, let's say receiver balance. Right, oh, right, vice versa, thank you, sub. Okay, so next we want to get the receiver balance, and so we'll do this in a similar way. New caller balance, thank you. Sweet. Okay, so to get the receiver balance, we're going to do the same thing, except we're actually going to use the receiver as opposed to the caller. Again, we're not going to need these 2 slots of memory anymore, so we can actually just overwrite these. Okay. And OXOO. So the receiver balance is going to be what we load from storage, which is going to be the hash starting at mem pointer and of size OX40. So this is where we get the receiver balance. Actually, let's do this. Caller balance slot, because we're going to need this later. So let's take this, and we're basically just going to create a variable with this, right? Same thing. Great. So functionally identical, but now we can actually access the slots a little bit later whenever we need it. So now we want to get the new receiver balance. Again, we'll optimize a little bit later. New receiver balance is going to be sub. Sorry? Thank you. There we go. Okay, so subtract from caller balance, add to receiver balance, the value. Okay, so now we have our new balances set up. We've done the addition, the subtraction, so now we just need to store these back into storage. So we'll say store. We need the key and the value. In this case, the key is going to be the caller balance slot, and the value is going to be new caller balance. And same thing, receiver balance slot. New receiver balance. All good. Cool. Yeah, so just as a quick review of what we're doing with this transfer, loading the free memory pointer, we're going to store at that memory pointer the caller, then 0, because that's the slot of the balance mapping. We're going to hash that to get the slot. We're going to load from it to get the caller balance, assert that it actually does have the balance that it needs. If not, we're going to revert. Then we're going to decrement or decrease the new caller to the new caller balance. Then we're going to do the same thing for the receiver. Obviously, we don't need to check for the overflow. We're going to check that a little bit later. But we can be certain that this is not going to overflow. So we'll increase the receiver balance to give us our new receiver balance, and then we'll store that in storage here. So last thing we need to do after all of this is we need to return to the caller a Boolean. In this case, we're going to return true. So the way we do that, again, doesn't matter now, we're at the end of the execution, so we'll store at slot 0 OX1, which will be our true value, and then you can return those 32 bytes. The log? Yes, the log. Thank you. Okay, so we're going to have a transfer event. Probably should have hashed this as well, but we'll get those hashes in just a moment. So it's going to be a transfer event. We're going to have an indexed sender, an indexed receiver, and an amount. Great. So per the rules that we mentioned earlier, we're going to have, so this is going to actually be log 3, right? We're going to log the event signature, the event hash. Then we're going to log the sender as a topic, the receiver as a topic, and then the amount, because it's not an indexed topic, we're going to put that in memory and then basically pass the pointers to that, to the log instruction. So I'm going to quickly, oh wow, so small. Great. So another place that you can do this if you want to get this stuff online and you might not have, if you might not have Cast installed on your local machine, what you can do is go to this online hashing tool and you can basically punch in this stuff. I think internet is going to rug me once again, but oh no, there we go. Cool, cool. So we can just say transfer. And then same thing, right? So OX, DD, F2, et cetera, et cetera. All right, so we're going to set that as a constant. All right, I'm going to add some comments in here. Just a moment. Okay, we're going to store and now log. Okay, so before we do any of the logging, remember we have to store the amount into memory. So in this case, again, execution is about to end, so we don't have to be too careful about where we put things in memory. So let's go ahead and mstore at slot 0 the amount. I think in this case we called it the value, right? So we're storing that in memory, and now we want to call log, but remember we want to have the 2 indexed arguments and we want the event signature, so that's going to be log 3. First thing we want to pass is the pointer in memory. It's going to start at 0. The size is just going to be this one value, right? Everything else is going to come from the stack. We just need these 32 bytes at the beginning. Then we're going to say transfer hash. The next topic is going to be the caller. And then the final topic is going to be the receiver. Great. So at this point, we handle the balances, update the storage, log the event, and return.
The values parameter I need to
The values in the log, only the non-indexed. So the actual indexed arguments are on the stack, and then the non-indexed are in memory. Which also, I believe this is also in the link tree, the full like Yule documentation, basically everything you need to know about this. It's also going to have our log instructions in here, right? So log 0, 1, 2, 3, and 4.
Add another statement and check the receiver the caller that there will be no bug where you can give yourself a lot of fun, because when you will see you're storing the value of the receiver after you are storing the value of the caller. So basically I will give myself 100 more ethers or any kind of graph here. I can just add to myself a lot of money. I would say. Because you are adding the new value based on another adding to greater than.
So if it's the same, it uses the same slot. It first increases, right? No. So whatever the value is at that slot, it will decrease. Then it loads, increases. Oh, yes. Okay. Right. Right. Great catch. Thank you.
Well, but now I can only lose money. I will do this. So you will give the reverse statement. So you check if you will
Right. Yeah. So let's do that as well. So let's just say equals if the caller is equal to the receiver.
Why do you lose money? Become 0?
No, because at first you will
Subtract, load, add.
Subtract, store, load, add, store.
Yeah, so
Right. Oh, yeah. So it evens out.
Yeah, I mean, it's better to check for sure, but I was curious if I don't understand it right.
Right.
Yeah.
Yeah. Great. Yeah, for the sake of time, we're going to be bad developers, and we're just going to revert with 0, 0. And we're just not going to tell anybody about that, all right? All right, great. Good catch. Thank you. So after transfer, let's do allowance. No. Yeah, let's do allowance. Great. Okay. So in this case, what we need to do is, all right. So we're going to take the owner, we're going to map that to a spender, which then we map to a number. So the way that this works in storage is we're going to hash the owner and slot. Make sure I get this right. Owner and slot, and then the result of this will hash again. So owner, slot, hash, then the final key. Let's double check the documentation, make sure we get that right. Great, so here is the standard function, and then nesting that would be right. Right idea, wrong order. So the mapping rules are applied then recursively. So we're going to bring that down here so we can remember. Okay, so first we're going to do the inner hash. So we're going to mstore the owner. Yep. We're going to mstore the owner at slot 0. We're going to mstore at the next slot, the slot, which is going to be 0. Inner hash is going to be SHA-3 hash of the first 2 slots. And then we're basically going to do the same thing again with the inner hash. Wait. Slot 1, thank you. Okay, and then spender. Okay, the allowance slot then is going to be the hash of these once again. Okay, and so now what we want to do is load from storage. And then we want to store this in memory and return that back to the caller. Oh, whoops, not caller, owner. There we go. Okay, so we hash together to form the first slot, and then we hash again to form the second slot, this mapping. We load from that slot, put that in memory, and then we return it from memory to the caller. So next thing we want to do is going to be approve. Okay. So in the interest of time, we're going to copy paste, as all good developers do. Okay, so we're going to do the same thing. So the hashing, figure out the slot, and then from here, we want to set the value at this slot to the new amount. So store at allowance slot the amount. Next thing we want to do before we return is we want to create a log, and that's going to be the approve event. It's going to have an owner, a spender, and an amount. And so functionally, this is going to be the same as the transfer. We have 2 indexed arguments, so it's going to be log3, and we'll have to store the amount into memory. Great. Is it approve or approval? It's just approve? Just a moment. Approval, great. So that's going to be approval. So from here, we'll take this hash. Make sure that's hex. Okay, so before we log the event, again, we want to store the amount in storage, and then we want to log 3. We'll start at slot 0. It's going to be of size OX20 because it's just the amount. First topic is going to be the approval hash. Next one is going to be the owner. In this case, that's going to be our caller. And the final one is going to be the spender, the person who can spend on their behalf. Okay, now that we've logged the event, last thing we want to do is store 1, which for true. Then we want to return that full amount. Great. Easy.
That's like the function returns like satisfied by returning an amount.
Right. So on the lowest level, a Boolean is actually represented as basically a uint8 that can only be 0 or 1. So it just occupies a single byte. But in this case, we're returning the OX20, just returning the full word. Okay, we're going to do transfer from. So this is going to have a sender, a receiver, and an amount. All right, so we're going to do a very similar thing to the transfer from function. We're actually going to just copy paste most of this with an exception. Oh, I don't know if I'm going to be able to do this with this tiny mouse. Hold on. Nice. Okay, no, we're just going to do it from scratch. We'll do it live. Okay, so we'll load the mem pointer. We want to generate the slot first for the approval. So we'll do the same thing as here. Just a moment. Owner, it's going to be... Okay, so the owner in this case is going to be the sender, and then the spender in this case is going to be the caller, right? So basically we want to check, what we're trying to load here, and what we're trying to see is the spender's permissions on behalf of the sender. We'll call that caller allowance. Okay, we're going to load from that slot. And so basically we want to do the same thing. We want to check and make sure that caller allowance is not less than the amount, right? So if it is less than, then we're going to revert. In this case, we're going to be storing the insufficient allowance error. So notice this is going to take 2 arguments. That's going to be the owner and the spender. Since we're going to be storing a bit more information here, even though it is going to end execution, again, formalities. Mem pointer. So we're going to store the insufficient allowance selector. So that's going to be the first 4 bytes. Now remember, it's only 4 bytes in memory that we're occupying here. We actually want to write, after this, the next 32 bytes. So instead of adding a full OX20, we're actually just going to add OX04, right? So it's going to be the 4 bytes, then the next 32 bytes, and then the next 32 bytes after that. So storing at this slot, it's going to be the owner. In this case, that's going to be the sender. And then the next one is going to be one second. So the next one is going to be the actual caller. So notice we're still increasing by OX20 at this point, but because it is at an offset of 4, first slot is going to be the mem pointer. The next one is going to be mem pointer plus 4, and then the next one is going to be the mem pointer plus 4 plus 32. And so this is our entire chunk in memory where the error is. So we're going to revert starting at the mem pointer, and then it's going to be OX, let's see, 4, 24, and then 44. So OX 44. And so that's going to basically assert that they actually have the allowance to spend there. So now that we've done that, let's go ahead and, oh, come on. Great. So next thing we want to do is we want to get the balance slot from the sender. Balance, thank you. There we go. Okay, so doing the same thing. My God, hold on. This compiler is being obnoxious. We're just going to do this. This is not actually important. I'm actually just doing this so the compiler doesn't give us all this yellow text everywhere. We're going to get rid of that in a moment. Okay, so we're going to load the sender's balance. Basically, again, we're storing the sender, storing the actual pointer in memory where this, or pointer in storage where this is going to come from. We're going to hash that to get the slot. From the slot, we load the balance. Then we want to assert that it is at least that amount, otherwise we'll revert with insufficient balance. Then we will store at the sender balance slot the sum of sender balance and amount. Great. Next, we'll do the receiver. So basically the same thing. Okay. And then we will store, whoops, inverse. Great. So same thing as before. Basically, once we pass this approval check, we're going to check the balances, make sure that it's all good, send all this stuff through. Last thing we want to do before we return is we want to do the log. So again, mstore at 0, the amounts, log, come on, 3. It's going to start at slot 0, offset of OX20. Transfer hash is going to be the first, second is going to be the sender, and final is going to be the receiver. Oh, and one last thing before we do this, before we return, is we want to make sure we decrease the allowance if it is not the max UNT 256 value. So if it is less than, we're checking, I'm not sure of a good way to get this max value in assembly. 1 second. No, we're going to have to log that or something. Sorry? OX, sorry? Right, yeah. I didn't want to have to do it that way, but it looks like I'm going to have to. You could underflow, which that is one thing that works, but also that does add, like that is computation at runtime. Best way. All right. And the reason that we actually can't just use, so normally you could do something like type unt256.max, but this actually is disallowed in assembly because this is a higher level functionality. So we'll just do that. Great. So if the caller allowance is less than this enormous value, what we want to do then is decrease the caller allowance, and we'll store that back in the allowance slot. And again, since we already checked to make sure that they have sufficient allowance, this should never underflow. Okay, then finally, we're going to store true. And then we're going to return it.
That if they just wrote max value less something, but when is that or when is that not true?
Right. So there's a common pattern. It's not part of the standard, but this is something that I'm seeing increasingly. Basically, to give like an infinite approval, you could just set it to the max uint256 value. And so instead of actually having to do like math on that, right, we can just check that. Right. So if less than, then we store. So that's all good. All right. So just reviewing this one function one last time, we're going to generate the allowance slot. Check the allowance, make sure it's sufficient. If not, we revert. If it's less than the max value, we're actually going to decrease the caller allowance. Next, we want to make sure the sender balance is sufficient. If not, we revert. Then we want to subtract from the sender balance this amount. Then we want to add to the receiver balance this amount. Then finally, we're going to log and then return true.
165 and 201 at slots are reversed.
165.
At 0, the center slot 0.
Right. So this is to generate the hash. So we're storing at slot 0 the sender. And you said the other was 205? 201? Yeah, same thing, right? So at the memory pointer and then at the memory pointer plus OX20. Right. Okay, so we have transfer from, we have approve, we have allowance, we have transfer, balance of, total supply. And again, we're just going to keep this internal just so we can, for the sake of the exercise, write this out. Now, of course, all of this that we're doing here is like very much over abusing assembly. And in general, you don't want to use it this much. This is just to give like a good picture as to like what's actually happening under the hood here. So total supply is going to be a public view function. Okay. Now this one's actually going to be really easy. Basically what we want to do is store the value at this slot. Now this is slot number 3, or slot OX02. This is OX00, OX01, OX02. So we can mstore at slot 0 the value that is loaded from OX02. Then from there, return OX00, OX20.
Do you need a mint?
A mint? Right. So I was actually going to do that in the constructor. But if we want to do a mint function, we could. Well, actually, are we short on time? Oh. Right. Yeah. So it's always 0. Best token. Was there another question? Transfer from? Hash 3 slots are the same. Oh, right. So if you want to hash 3 slots, then the first argument would be where in memory it is, and then you would just say OX60. So that's 3 slots. In this case, we're only ever hashing 2. That's just per the Solidity standard. But you could hash bigger stuff. Not quite. So the reason that we did the separate hashing here is because the second time we hash, we're actually concatenating the caller and the first hash, like digest. So it has to be two different hashes. All right, so in our constructor, we will once again abuse assembly. So basically, what we'll do here is we'll just do a static total supply for the sake of simplicity. We're going to store into the caller slot the initial supply. So first thing we want to do, mstore the caller. Next is going to be the slot for balances. And we're going to store at the slot total supply. What do we want to call this? Max int. Yeah, I like it. Cool. All right, so we'll do that. Now, since this is kind of technically a transfer from the 0 address, we'll go ahead and log an event for this as well. So mount, we're going to store into memory. And then from there, we're going to call log3, transfer hash, no. Log3, memory pointer, it's going to be 0. Memory size, it's going to be OX20 to store that value. Transfer hash, 0 address, we can just say 0 here. Then receiver, and all 3 topics, perfect. Now from here, we're not going to return because in the constructor of a contract, the way that a contract is actually deployed to the chain is we take the entire contract's bytecode and then some, and basically what we're doing is returning the entire contract's bytecode. Like we're putting the whole bytecode in memory and then calling return on that. That's how the actual deployment process works. And part of the reason why deployments get so obscenely expensive because memory memory expansion gas costs scale quadratically. So it gets very, very expensive. But the reason that I bring this up is we're not going to call return here because a constructor needs to do its job and return the bytecode at the end of this constructor's execution. So everything compiles. Moment of truth. Whoops, hold on. All right, so first let's check decimals. Should be 18. Name should be Yule token. Symbol should be Yule. Total supply. We did not increase the total supply. Lol. So store, that's going to be slot OX02, and it's going to be max UNT 256. Great. Good coin. Great tokenomics. All right. Total supply. Now it's this enormous number. And let's do a quick transfer. We're just going to transfer to some random address. Who cares? No. First, let's call balance of on this address just for the sake of seeing what's what. So balance of, this should be the deployer's address. Is it not? Just a moment. Interesting. Caller OX00. Caller OX00. Ah, that's it. Okay. There we go. One more try. So balance of here, our enormous number. And then finally, we'll just make a quick transfer here for, let's say 10, because we're stingy. And then we call, and the balance is now 10. And that's an ERC20 token written purely in Yule. And that concludes today's workshop. So really quick, these are some other resources that you guys can check out. Educational resources, EVM codes, obviously the yellow paper if you're degenerate and you're into that kind of thing. Developer tooling and languages, Huff language. This is basically a low-level assembly language that will teach you a lot about the EVM. The Foundry development environment, really good for testing and trying things. And the Remix browser IDE for that local testing in the browser. You had a question?
Transfer from can be used simply to know why it was called, like not called it. For example, call the ruler as a user. Can we know if it's add liquidity or if it's a swap that causes the transfer from? Can you get called it?
Add liquidity or swap. So that's not possible now. Right, because all it has access to is like the message sender, right? Now maybe. Right, right. Any other questions?
The compiler is smart now, so I will, let's say, use the well-checked open settling implementation, what we will do as the Solidity developer. Is the compiler smart enough to declose the gas use as this implementation?
So, right, so some things are trivial, but some things you can actually like very heavily optimize, and that's actually why a lot of people tend to use assembly. Like for example, take abi.encode. So this is actually like fairly gas intensive, especially like let's say you want to loop a number of external calls. It's actually ABI encoding every time, right? And there's like a lot of gas that's being consumed there. Whereas like maybe you're calling the same function over this entire loop. Instead, maybe what you could do in assembly is you run that loop, but let's say instead of doing this encoding the entire time, every single time, you just store it once and you kind of like cache that, right? And so things like that will actually give you massive improvements in gas efficiency.
Okay, so compiler is not always, it's not that well written, so it will do this kind of thing every month.
Right, it is improving. So a little bit about the state of the Solidity compiler. Originally, Solidity used its own pipeline, so it would go from Solidity to intermediate representation to bytecode. Now there's actually a migration happening where basically Solidity will compile to Yule, and then we can actually use Yule's pipeline to optimize because the Yule optimizer is very well developed. This was actually sort of the original reason of using Yule, is that like many high-level languages could compile to Yule and have the same, basically intermediate representation where everybody can take advantage of the same optimizer.
Okay, thank you very much.
You're welcome.
You're going to share your kind of source code that I need to graph that.
The Yule source code?
Yeah. That your study stuff that you did on the ID.
Oh, this one?
Yeah.
Yeah, I can share this.
Of course.
We'll just copy pasta this into little GitHub gist. No internet. Okay. Well, I'll definitely do that, and I'll be in touch.
Okay, thank you.
The question I want to ask is so do you work specifically
Just know that it's right. It's one in a lifetime. For the first time in my life, I'm right on the edge now. I'm looking down. No matter how hard I try, can feel the ground. I'm on the edge now, taking the lead, taking a chance. 'Cause you just touch me when I fall for you. All I need for you, I just listen to your heart. 'Cause all I need from you, I just touch me when I fall for you. All I need from you, I just listen to your Well, give it all I've got. I'm losing control tonight. But I hope you'll do us right. I'm right on the edge now, I'm looking down. No matter how hard I try, can see the ground. I'm on the edge now, taking the lead, taking a chance. 'Cause my angel just touch me when I fall for you. All I need from you, my angel, just listen to your heart. 'Cause all I need from you, my angel, just touch me when I fall for you. All I need from you, my angel, just listen to your heart.
Check.
All right. Hello, guys. Welcome to our workshop about building the apps like a pro. And my name is Justyna Broniszewska, and I work for TrueFIDA. And these are my colleagues, Michał, Bartek, and Przemek. They will help me today. So if you have any questions or problems, let them know. They will help you for sure. All right. So maybe let's start from what the app is. Anyone wants to answer this question? What is the app? Decentralized application? Okay, can we have second mic so we can handle questions? Where is it? Second one? Yeah. Where? Oh, thanks.
A DApp is an application that rather runs on a centralized server, runs on a decentralized network like Ethereum or an L2.
Yeah, kinda. So is it like UI for decentralized system? Maybe application that uses the centralized system, or maybe application that uses smart contracts on blockchain, and maybe an application that has no central server. So like it's hard to define, like find one simple definition of decentralized application, but apparently it's very easy to build. We've used that, of course. So let's see first how to build decentralized application, the app. We have different Ethereum API providers like Alchemy and Infura, and we can connect to them, right? So we can get this connection to blockchain by them. And we have different blockchain calls, two of them actually. Read, that are totally free, and you only read the state of the blockchain, while the second one are write type of calls, and it costs gas fee. It requires wallet connection. Additionally, it changes the state of the blockchain. That's why it needs private key and wallet. So these are the examples of such blockchain calls. First is read, and here we just check the balance of this address. And the second one, write call, we just send transaction to the address. So that's why we need private key and the wallet. Let's talk about blockchain state for a second. It's all about mining blocks, right? And each new block is from 10 to 20 seconds. So each new block is like around 15 seconds or something like that. And the state might change. So each time we need to check whether the new block didn't change our state. So our application needs to be updated very often. Ideally, each new block, we should update our state in the application, right? I hope you agree with me. Additionally, the app is very complex. Like typical application interacts with a lot of smart contracts, a lot, which is, let's say X, it might be 50, it might be 100. And it needs to update state very often, frequently. Ideally, each new block. So it's like X calls per 50, 30 seconds. So that's a lot. Let's review leading API provider costs. And you can see that it costs a lot if you want to optimize your application. You can pay up to $1,000 per month if you want to optimize your application, if you have too many smart contracts interactions. But we have something like multi-call, and it helps us aggregate. It's like actually it's smart contract that helps us aggregate all these different calls into one single request. So there is no problems with optimization, right? So we can just use this smart contract. It has this function aggregate, so we can batch all these calls in one request. Additionally, we have guarantee that all these values we get from the blockchain will be from the same block, which then we will have state consistency, which is great. So this is how it looks like without and with multi-call. So without, we have a lot of different requests to different smart contracts, but with multi-call, we have only one call to multi-call, and then multi-call calls all these different smart contracts for us. So let's summarize the app requirements. We should have like requests. We should like update our state, ideally each new block, right? We should have consistent state, so all the data should be taken from the same block. Additionally, we should like optimize our app so we won't spam API with a lot of requests. But don't worry, UseDApp does it all. So you don't have to worry about all these different multi-calls and updating state each new block. It's everything built in UseDApp. So let's go to examples of code, how to use UseDApp. So here we have an example how to connect to a network, because we need to have like a wallet connection to interact with smart contracts, right? So see how simple is that? We have this useIters function that we can get from UseDApp, and it returns us activate browser wallet, which is a function. And when we call this function, we have our UseDApp will ask MetaMask to connect to your application. So it's that easy. In these few lines, you can connect your wallet with MetaMask or any other wallet. And in this case, it's like browser wallet, so it's MetaMask. But yeah, and additionally, this account is just the address that is currently connected. So that's really simple. Ether balance. This is how we can get it. Another function, use ether balance, and it gets account, which is the address you want to check the balance, and then that's it. And the nice thing is that this ether balance you get from use ether balance function will be of course, will be put in the multi-call call, so it will be only one call. Each new hook you use from UseDApp will generate only one call each new block, and the state will be updated on each new block. So that's additionally really cool. Additionally, we have another example of a nice helper function, which is use token balance, and this is how you can use it. You just pass the address of token you would like to check the balance on, and then the account address that you would like to check this balance account. And you get updated on each new block the balance in this case. But you need to remember about one thing that is really important here, because we need to wrap your application with the app provider that we also provide as used app. And it needs configuration. For example, here we just passed read-only chain ID. So the chains that we would like to support in read-only mode, and read-only URLs, for example, our own Infura or Alchemy or any other API provider URL. So we can support anything. And you need to pass this config to the app provider. So that is the only requirement, and only then inside of this app you can use any hook we provide from used app. Additionally, we support multi-layer, multi-chain. So you can, for example, here we have this switching networks function. So you just import switch network, and this function will ask your wallet to switch network. For example, in this case, we want to send transaction, but we want to send this transaction only if we are on mainnet. So in this case, we check whether the current chain ID, current in wallet chain ID, is not mainnet, and if it's not, then we switch. We want to enforce on the user to switch network, and this is how it can be done with used app. And this is how we can check, for example, in read-only mode on different chains. For example, Ether balance. So for each hook we provide, you can add additional parameter, which is chain ID, an object that gets chain ID. And this is how you can get, for example, mainnet, Arbitrum, and ZK Sync balance in one place. And this is super easy to use. All right. So that's it from theory. And now we can go to some practice and practical stuff. We can start coding. So what we are going to do today is we want to create an application that will interact with Girly USDC that is deployed there, and will use used app and all these different features. So these are the requirements that, in my opinion, this app should have. But if you feel like you would like to do something else, feel free to do that. So in my opinion, we should first start with connecting our wallet, right? So we should have like this button, connect, and then connect with MetaMask or any other wallet. Then we would like to display our Ether balance, and to prove you that it can be multi-chain, we can do it on Girly and Girly Optimism. So let's display two different balances. Then let's display Girly USDC balance as well, our balance, of course. Then probably it will be 0, so let's make this application to mint ourselves some USDC, and then transfer this Girly USDC to anyone. Maybe it can be your friend next to you, sitting next to you. Yeah, so that's what, in my opinion, we could do today. So yeah, and we prepared 2 tracks for you. You can scan this QR code and go to Code Sandbox, where is prepared the boilerplate, so you can start coding with us. And we have 2 different tracks. First one is easy track, so we are going to live code with you. So I will be doing all these different steps, and you can follow me. And of course, we have here Bartek, Przemek, and Michał, who will help you if you get lost. And additionally, we have pro track, so you can do it yourself. We have here the requirements displayed, so you will know what to do. Oh, something happened. So okay, now you should see. Great. And yeah, if you get lost, you can switch from one track to the other. So if you go to pro track and you decide, yeah, no, I can't do that, can't do this, and I would like to switch to easy track, someone from my colleagues will help you to get up to speed with us, and then you can continue. Additionally, you can join our Telegram group, and if you don't have a Girly if on your account, we can send you. Michał prepared a script that will send you automatically some Girly if. So yeah, go to this Telegram group if you don't have Girly if, or you can use, of course, Girly Faucet, but yeah, it will be easier for you to just go to this Telegram group, send your address, and we'll send you Girly if. Right, and additionally, we have something super extra for you, because there is a chance to win a Ledger Nano S. So we decided that, okay, so anyone who creates the application with my help or yourself, then there will be a chance, like last 10 minutes of the workshop, we're going to allow you to present your solution and how you did that. And the most interesting application will win a Ledger Nano. Right? How does it sound? I hope cool. Of course, we won't get you the real Ledger. We'll give you a gift card, right? Because it's not safe to get your Ledger from anyone, right? You know that, I hope. All right. So, yeah. Not this one. All right. So let's go back to this slide. Yes. So, any questions so far? Everything's clear. Okay, we have one question there.
I can pass you a mic.
Oh, hello.
Hello.
I suppose not yet, but this work with all the scaffolding tools like Create React App and all that kind of stuff. I mean, it's working automatically with Create React App and.
Yeah.
Okay.
Yeah.
That's all. Thank you.
Sure. Yeah. So for this workshop, we prepared like a code sandbox, but you can use it with Create React App. Yeah. Right. Any other questions, maybe? All right. So if there are no questions, let's go to coding right now. So who chose Pro Track? Raise your hands. 1, 2, 3, 4, 5. Okay, there are some people. All right. And who is going to code with me on Easy Track? Great. Perfect. So let's go to work. All right, let me make it bigger. Yeah, so did you manage to scan the QR code? Are you on the same page as I am? That's important because this is where we are going to work together. Do you have it? All right, so you can scan it again. So this link leads you to Code Sandbox. And there are some ready components that we are going to use. And this is, all right. So are you with me on this page? Did you manage to load it? I know the internet connection is really bad here. And there on the wall, there is like a password to another Wi-Fi password for workshop specifically. So it might be useful for you to use that one. Or maybe your mobile one will be fine as well. All right, guys, so if you have any questions, just raise your hands and we'll help you. All right, so are we ready to start coding? I hope so. All right, so if you are with me, then let's go to app.js. And this is where we are going to start our coding. Actually, let's go to index.js. And this is where we are going to start. All right, so I hope you remember what I said before, but always before we start using UseDApp, we need to start with wrapping our application in the app provider. And in my opinion, index.js is the perfect place to start and to do that. So let's first here import the app provider. And you can do it like this. From UseDApp core. Not like this. Oh, like this.
Can you make the font bigger? That was the question that I heard.
Okay. Is it better now? Question there? Is it better? Can you see it? Great. All right, so we can import the app provider from UseDApp at usedapp/core, and this is the exact name. All right, and now, as you remember, I told you that we need to create configuration file, configuration object for that. So let's name it config as always, and it needs to be an object. And what we need there is like read only chain ID. It might be, for example, let's start maybe with, go early. Let's import chain ID from used up as well. So we can use it. Chain ID dot, as you can see, used up supports a lot of different chains, and girl is one of them. Great, so we have this config file ready for now, I hope so. Yeah, and also, let's add also read-only URLs. And that's another object with, and keys are the chain ID, chain ID. So in this case, let's use curly as well, and then we can use get default provider function from that we can import from Ethers. I hope you know Ethers library. It's a really great library. If you use it, then I hope you like it. And this is how we can create this read-only URL from for configuration. All right, and now we have our config, so we can pass it to the app provider. So first, let's wrap our application. We can do it here with the app provider, like this, and pass their config. Always remember to close tags. All right, so this is how it should look like. Everyone follows? Is everything clear? Nice. So now we have this our app wrapped with the app provider, and now we can go to our app and actually start coding. So as I said before, let's start from connection of our wallet and how we can do that. First, we need to import use ethers function, and we can do it like this. From used up core as well, because this is our core function, and you will see in the future that it returns a lot of different useful helpers functions. And one of it is actually activate browser wallet function. And we of course need to call this function. Right. We can add here button. With onClick function, we'll just call this activate browser wallet function, right? Let's display connect text on this button, and voila, you can see this button. And when we click on it, it should ask our MetaMask to connect. I know the font is really small, but yeah. And as you can see, it works. And that was only one line of code, actually, or 2 lines. But okay, how can I know that it worked, that I'm connected to this application? Of course, I should display my address, right? The address of the account that I connected. So let's import account, and let's display it. And this is how we can do that. We need to make sure that this account exists, because then it will be just undefined. And as you can see, we can see actually the address. So it worked. It worked well. All right, so now let's display my balance. And how we can do that? We can just simply use another great function. So maybe let's first import this function so you won't get lost. Again, we import this function from used up core, so we can do it after comma. Use ether balance, it's called. All right, and now let's just use this function. Let's call this ether balance, and then use this function, and let's pass there my address. And let's display balance. Maybe let's add a new line. All right, we have an error. And do you know how to fix that? Maybe? Any has an idea? Yeah, so yeah, that's just an object. So what's used up, like use iter balance returns in this function? Big number, exactly. That's how we should just pass, like make it, yeah, this string, right? For example, here in this case. Let's start with string. And now it should work. Yeah, let's wait for a second. Yeah, so used up will return big number. So in this case, we can parse it to string, but I prefer to not use like string, and you will see why, because it will display a lot of different zeros. Okay, let's see why it's not working. Let's try to uncomment it, comment it, and then see. Yeah, it's probably the internet. Yeah, I use my own hotspot. Yeah, already. But too many people in one building, and that's how it ends. All right, let's wait for a second. But yeah, so what we will see on the screen when we parse iter balance as a string? We will see some number with 18 zeros, right? Because that's a big number. And that's why we shouldn't display such thing to user, because they will get like, you know, they will see what's happening, why do I have so many iters, right? So normally I really like to use iters functions for that. And this is how you can get this function. So I always use utils, parse iter, not format iter, sorry. I always confuse these two. All right, and this is how I always like to display balance of iter, of course. For different tokens, you would like to use probably format units, and then pass as the second argument a number of decimals that this token uses. All right. Yeah. Workshop Wi-Fi, you suggest. Maybe something is happening. Oh, nice. All right, let's connect again. Again, click, nice. All right. And we display account. And now let's try to display iter balance. But still the internet. All right, can you see it? The balance, nice. All right, so now maybe we could display balance on Optimism Girly, right? Because we can do that as well. But first we would need to add to configuration file, right? All right, so let's not do that right now. Let's go to the next step. And when we have time, we can go back to Optimism Girly. All right, so as I said before, we would like to create an application to interact with USDC that is deployed on Girly. And you can find this address of this USDC in the addresses.js file. And if you are a smart contract developer and you know how to, or maybe not you are a developer, but you know how to read the code of smart contract, you will see that this contract has open mint function, so anyone can mint any amount of token they want. So we are going to use this test USDC for this workshop purposes. All right. But first, let's just display balance of our address in this USDC. Is there any problem and you need maybe help? So anyone needs help?
anyone's coding and
Yeah, if you are coding and you get lost, or you would like some help, or you are, on ProTrack and you need help, Bartek, Michał, could you handle that question? And maybe you see that it's easy, but you haven't started with us and you would like to join us, then also raise your hand and we are going to help you with anything. All right. Yeah, I can see you. Someone will come to you in a second because yeah, index.js. And this is how it looks like. Yeah, anyone needs some help? Raise your hand, and Przemek is free for some help. The person in the back, you need help? Przemek, could you help there? Yeah, the address of the smart contract is in the file addresses.js, and you have it in the sandbox. It's there. So you can find it on the left side. No. Utils is imported from Ethers. Ethers, yeah. Ethers. It's a great library. I love Ethers. Seriously. All right, guys. Can we move on? Okay, I'll wait a few seconds. Bartek, we had a question there. No, it's fine? Okay, address. Okay. Anyone needs help? Raise your hand. Bartek is free and he can help you. Yeah, index.js. Here you have it. So we imported the app provider and chain ID from UseDApp core, and additionally get default provider from Ethers. All right. Perfect. So let's go back to app.js. And now let's display girly USDC balance of my account. It's probably 0, but I would be surprised if it wasn't 0. All right, so no, let's start from importing the function. The function is called use token balance, written like that. All right. And now let's just get it from blockchain. Like this. And we need to, and here, as you can see, there are 2 arguments. First is token address, so we can use the address that I have here. It's called USDC and I export it, so we can just import it like this. Import USDC from addresses. Perfect. So now we have the address of USDC, and we can pass it as a first argument of the use token balance function. And the second argument is my account address, like this. All right, and now let's just simply display this balance on our UI. Let's add another, enter, and let's just display it. But still, this is a big number, so we need to, first let's start with making it string. All right, let's wait a second, and yeah, we have one big 0. All right, so now we can do something more difficult, and we can send a transaction to USDC, and we can mint our some USDC token. All right, and this, I hope I remember the syntax for it, but we'll need to use contract function. All right, and this is how you can import it from UseDApp core as well. All right, and this function is really interesting, and it gets 3 different arguments, and these are more advanced, so I hope you won't get lost, and if you get lost, we'll help you with that. So this function will return send function, like that. So we can get it like that because it's an object, and one of the parameters it returns values is send function, And this is the send function we will call to just send this transaction. And we can use it like that. So use contract function, and you can see that we'll need contract function name, and what else? Options. All right, so let's start with contract because that's tough to create. All right, so contract is an abstract of this contract. So let's name it USDC. And it will be in contract that if you know Ether's library, you will know this contract. Let's import maybe, yeah. Let's import this contract from Ethers first. And we need to create this contract. Again, what it needs. First, it needs this address. So we can just simply pass USDC in the address. And then we need contract interface, and we need to create it. So let's import it from Ethers as well. And this is how you can do that. It's hidden in providers dot interface, no, not providers, but utils, sorry. Utils dot interface, and that's an object, so we need to create it. And let's see what it needs. It needs fragments of ABI. So in this case, for USDC, we are going to need only mint function. So for now, let's just create it by hand. So it's just an array of signatures of these functions. So let's create it like that. It will get address and value, which is uint256. And this is interface we need for this contract. Are you guys following? Is it fine? All right. So what else do we need for this contract? Address, interface, and should be it. All right, so now we can use this USDC contract to get this send function. All right, what is the second argument we need here? It's function name, so we can just use this mint function. So here we just need to pass the name of the function we want to use. So if we want to use more functions, then we can just add more functions to the interface we created before, right? Like send, and like in production, you would probably need to have like, you know, the interface that was the result of compilation of your smart contract. So you won't type each function separately. But for this workshop, we are just like, you know, using this simpler version. All right. And now, actually, that's it. And now we can try to use this function and see if it works. Yeah, give me 1 second, maybe. Let me make this interface like this. All right. Can you see it now? Is it better? Hmm? Oh, okay. That's nice suggestion. Thank you. All right, guys. Any questions so far? Anyone needs help? Raise your hand, and the guys here can help you. All right. So now let's come again. Oh, question. Bartek,
I'll pass you a mic. Here you go, my man.
Is the Ethers provide? I saw you put Ethers providers at import, but
no, it's not necessary.
Okay, it's not necessary.
It's not necessary.
That's all.
Yeah, sorry, that was my bad. All right, we will just need utils from Ethers. All right, and now I hope it works. All right, so now we want to trigger this transaction somehow, and we can do it by adding additional button like this button with text send message, right? All right, so I know this is not the prettiest application you ever seen. All right, so let's create another button. And here, let's add like this. All right, and what we would like to do on click, we want to actually trigger this send. So send this transaction. And let's do it like this because we need to pass argument to this function. If you know ERC20 standards, you know that mint function gets 2 arguments. One of these is address of the address you would like to mint this token to, and the second one is the value, right? So first, maybe let's use the account we are connected to, and let's start with 1, just simply 1. All right. And now, let's test it, if it works. Right. So as you can see, it triggered MetaMask window, and we can see here that something is happening. All right, let's confirm. Random application, confirm MetaMask transactions. All right. And now let's wait a second for this transaction to be minted. And we expect that if we did it correctly, the balance of the USDC should change, right? And voila, it changed. Nice. Cool. So as you can see, UseDApp updates all of that with each new block. So it takes some time. Of course, we have internet here, really poor, but yeah. All right. So are you following? Have you managed to send this transaction with me? Who sent the transaction? Nice. Great. We have three people who did that. All right, guys. So who got lost and needs some help with sending this transaction? Bartek, behind you. All right. Anyone else would like some help with that? We have another question. Would you like to get me, Mike?
I was wondering where we're getting the USDC from.
Yes, so USDC is from addresses. I created this file with this address.
Oh, okay.
So you all have it.
Gotcha.
Okay.
Thank you.
Sure. Yeah, app.js. All right, so I will give you like 1 minute to. Could you pass the mic?
I was just saying, like, there was a link at the beginning to get the girly ethers, right?
This is the link to our Telegram group, and if you send there your address,
okay,
Michał will transfer you some girly ETH.
Yeah, we already funded a bunch of accounts. Please send yours as well.
Question or help? Help. Michał, could you go there?
Where are you?
And there. Could you raise your hand? Oh, thanks. Nice. And guys, so if you need help, just raise your hand. Przemek is there waiting for. Yeah, I'll go back to the app.js. And in the meantime, I'll add some changes to the application so it looks nicer. So here. Look like this. Nice. Better now. Let's do the same with Ether balance. Like this, nice. All right. So who is ready to move on to the next step? Perfect, perfect, we are ready, great. So maybe let's change it because as you can see here, the balance is 1, right? But we know that USDC has more decimals than just 0. Do you know how many decimals do USDC have? 18. No, it's not 19. 6, exactly. Great. All right, so what we need to do here is to first of all, we need to actually mint ourselves not one base unit of USDC. Actually, we would like to mint ourselves 1 USDC, right? 1 full USDC. So let's use utils for that. And it's parse units. And it will need us to parse string. And yeah, and the second argument is the number of decimals. So like that. All right, so as you can see here, instead of just passing simple 1, I'm just using utils.parse units with 6 decimals, so we'll have 1 full USDC minted. All right, so let's try again, mint some USDC, but this time it won't be just 1 unit of USDC, we will go for full USDC. And again, if you have any questions, just raise your hand if you would like to get up speed with us. All right, let's confirm this transaction. And now let's wait a second. And simple question, do we have any volunteer to present in 5 minutes? Nice, perfect. Any other volunteers? Present their solutions. So no, oh, okay, we'll have competition then. Perfect. All right, it takes some time. Nice. So we minted more USDC, but now we need to display it differently, right? Because it's just 1 and a bunch of zeros. So let's use format units similarly to the previous one with 6 decimals. Nice. So we managed to do that. All right, and now our final step of this workshop, which is sending USDC to someone else. So we minted ourselves 1 USDC, and now let's transfer it to someone else. All right, so our first step in this should be adding to interface transfer function, right? Because for now, our application doesn't know that ERC20, like USDC, has this functionality. All right, so let's add function transfer. And do you know what arguments transfer function gets in ERC20? First is address, right? For whom? And the second is value, right? So again, we use address and uint 256. Great. So we have our interface. And now, again, we can use contract function. But this time, we'll need to name this send differently because it won't work. Yeah? It's the same as mint, but the name is different, right? So the arguments are the same. All right, so let's go back to use contract function. Let's name this parameter transfer. Okay, and now we won't have collision. All right, and now here also let's use transfer, right? So we change the name of the function we would like to call, right? All right, so now we can actually use this function. So let's add another button. I know it's not pretty application. And another on-click function. Let's name it send USDC. And now let's call this transfer with arguments. So, all right, so where should we send this USDC? I mean, where? I mean, what account address? What address? Maybe if you are on the Telegram group, you can take different address, not yours, but someone else's, and then send this person some USDC, right? So, yeah. Yeah, so in my case, it will be my second MetaMask account. Right. So I will. So here you can pass just a simple string, right? The address will be just a string. And now we can transfer. So let's start with simple one, or you can change the, actually use different numbers. So because if everyone will send like one way of USDC, then we won't see the change, right? Because everyone will be the same number. All right, so I will send 3 maybe. All right, and anyone needs help? Raise your hand. Bartek is here to help, or Przemek. Okay, we have someone there. Oh. Great, and now, in the meantime, I will try to click send USDC and try to do that action. All right. Let's wait a second. Cool. Up? Yes. Sure. Bartek, would you like to help maybe there? You will find the person in the red shirt. All right, guys, we have 10 minutes till the end of the workshop, so maybe the people that would like to present, get ready and you'll show us your solution. All right, guys, so we managed to send USDC. Okay. So, yeah, that would be it. Guys, I hope you managed to do the same thing as me. And yeah, if we have volunteers, then yeah, maybe let me just tell you thank you for your being here, and thank you for coding with us. And yeah, if you have any questions, just don't hesitate and raise your hand if you have questions. Thank you. All right, and now we have some time for presentations. So if you would like to show us your solution, feel free to come here and get a chance to win a ledger. Yeah. Come. Round of applause for volunteer. C or HDM?
Oh, jeez.
Wait a second. It's ready. Yeah, guys, I hope you enjoyed the workshop and that now you will use that for your application development, because I hope you know right now how easy is that, right? All right.
Okay, so I coded it into my little website, and you can connect with your wallet. And here you see the address. You can disconnect again, and
Yeah, but the app looked amazing.
thanks. Let's see if it comes up again. Okay, and the special feature I can send to myself. It's just the wrong text on the button, I think. And I can send to others by copy pasting an address. And then I can send directly to them.
All right, and
like this.
Can we see the code and how is it used in your step?
Okay. So what I do is that I take an input with the target value and I set a state, and then I use that state in the send for
Nice.
a transfer account.
Nice. Thank you. Great. Any other volunteers? All right. In the meantime, guys, if you have any questions regarding UseDApp, feel free to ask them. Can we, just 2 more presentations, like small, 2 minutes? Just show it.
But
Instead of account, just pass the address. All right, guys, we don't have any more time, but you can show it outside of the room, and then we will get a winner. All right, thank you.
¿Él tiene presentación? ¿Tienes slides? Okay. Para proyectar. Ok. Solo las diapositivas que tenemos ahí descargadas. Listo, entonces ya las tengo. 2 micrófonos de mí. Ok, pues ya estamos listos. Ok, listo, perfecto. Entonces te dejo uno acá y te dejo el otro en la silla, ¿listo? Ya te conectó la
Still have to connect.
Hello, everyone. I'm Fabrizio. This will be a talk about compositionality. It's probably a word that not all of you know, and I'll try to explain what this is about in the course of this workshop. In the last months, probably year or so, we have been hearing a lot about composable things, composable blockchains, composable service. Compositionality is basically just a mathematical structure theory that tells you how to do that in the most principled way possible. I'll start and if you have any question, just feel free to like raise your hand and interrupt me, and I'll try to answer and or clarify. Okay, so first of all, to introduce the concept of compositionality, we need to introduce some basic building blocks that are systems and processes. So compositionality is basically the study of how systems compose to give life to more complex systems. Systems are basically things that can be transformed and acted upon. And processes are exactly the things that act on systems and transform them. A very interesting insight from modern mathematics, so the mathematics developed from 1950 onwards, is that often is way more fruitful to understand something, to describe it by looking at how the thing composes and behaves in a context. So instead of splitting things open and look how they look on the inside, we describe them by saying how they behave and how they interact. Okay, so let's start with something very, very simple. I will use a lot of pictures in this talk and hopefully close to zero mathematics. For people that love mathematics, I can add that there is a soundness and completeness theorem that says that these pictures are formal, which means by doing pictures, we're actually doing mathematics. It's just easier and more beautiful, in my opinion. So in here, we have a very simple process that we depict as a box. It just takes a number in input, adds 1, and spits a number in as output. I mean, for, I guess, everyone acquainted with programming, that's just like, meh, yeah, okay. The point is that when we have a process like that, we can compose it with other processes. So for instance, in here, we take this process, we notice that it needs an input that is a number and spits out an output that is a number. And we realize that, oh, we can actually pipe this process with itself. And if we do that by just concatenating the boxes, you see that these will be equivalent to the process that adds 2 to your input. Now, this seems very naive, but the nice thing about this picture is that it goes both ways. You can start from the top row where you have simple components and you actually abstract away. So add 2 is basically just, you know, the dotted box encompassing the 2, or you can do the opposite. You can start from a process, add 2, and open it up and further specify it with a finer degree of accuracy. And since you have an equal sign, you can basically go both ways. Now, there are very peculiar processes that are called identity processes. These are the processes that don't do anything. In this case, with the number example, we have a process that is add 0, that takes a number in input, does absolutely nothing with it, and spits the same number as output. The good thing about graphical reasoning is that since this thing is not doing absolutely anything, we can just not draw it. And indeed, I'm drawing it as a dotted box down here, just to highlight that there should be something there. But you know, with this very simple trick, we can already start proving some equations that are very simple. So if I add 1 and then I add 0, it's like just adding 1, right? If you adopt the convention of not drawing identity processes, then the picture on the top row just looks like the one in the bottom row, while you have stretched a wire a little bit more. Similarly, I don't have it here on the slides, but you can understand that in this formalism, the composition is associative. We don't use parentheses. If you concatenate 3 boxes, one after the other, it doesn't matter in which order you abstract them. In the end, you only have 3 boxes, so it doesn't matter how you group them. Okay, let's do another example. So for this example, I'm using gravitation. Gravitation that has absolutely nothing to do with crypto, I admit. At least I think, I don't know, maybe. So we have a system that is a sun that is just sit there and does nothing, and there is the Earth that is orbiting around the sun. So during many centuries, people thought a lot about this, and at some point, basically a guy called Newton found out that there is a process that you can call evolve, in which you can feed a state of your system, and then you can say, okay, show me what happens 1 second later. And this is a beautiful predictive power of physics, in this case of dynamical systems, that allows you to start from some experimental evidence and predict what is going to happen in the future. You see that in this example, you also have an identity process that is the process that doesn't evolve for like 0 time. It's just taking the input and is not looking in the future or in the past. It's just giving you the state as it is now. And we see that we have a notion of composition, because if I let evolve the process for, I don't know, 1 second, I go from the position marked T0 to the position marked T1. Again, I can feed T1 to the system another time, let it evolve for another second, and I go to T2, and that would be the same of evolving the system for 2 seconds. So again, I can combine these bricks. Now, the important thing is that everything that matters in this formalism is how things are connected. You can deform the wires, no problem. What you can't do is you cannot make new connections or splitting connections. If you do, you are getting something that has a different meaning. Another important thing is that you can only compose things with matching types. For instance, in here, I have the HUD1 process. We saw that that spits out a number, but the evolve thing wanted something of type sun, earth as an input. So you see that it doesn't really make sense to compose these things because they are apples and pears. Okay, so this tells us that types in this formalism are very important. The way you type your processes changes what you can and cannot compose. Okay, as an example, imagine that you have a car, right? You have the wheel and the shaft and a gas tank. And you could see this as a process that takes some inputs. For instance, I don't know, fuel and human action, and produces heat and motion. But when you look very carefully, you see that you could pour any liquid in your car, right? Like the gas tank won't complain if you fill it with water. Clearly the engine will, though. And basically from this you can, infer that the problem here is that the type of input of our process is too general. And it allows you to fiddle with the process in a way that produces unintended behavior. Another example that I like is, imagine a socket in the wall. You can put a plug into it and use any electronic appliance. But if you have a couple of nails, you can also stick the nails in the socket. And what you get is emerging behavior all over you and very painful. So the important thing here is this is the main message of compositionality. So when you look at this process, like the socket and plug process, you can start asking, what are the properties that are preserved when I compose these processes together? So physically, sticking the nails in the socket makes total sense because they fit. But if you're looking at things through the lens of safety regulations, you see that a nail can be safe, can be certified with whatever standard your country has. Same thing for the socket, but when you compose them, suddenly you have a very, very unsafe system. Compositionality is exactly the art of choosing these types in a way that emergent behavior is averted as much as possible. So that when you compose things, you know precisely what you are going to get. Now, under the hood, compositionality is based on a theory called category theory. This was invented in 1942 and had a monstrous impact on modern mathematics. Essentially, you can see it as a superglue of mathematics that describes how different theories compose and interact. Basically, all the main progress in, big areas of mathematics like algebraic geometry or algebraic topology come from here. And in the last year, people started realizing that this thing can be applied also outside of mathematics. Because again, it embodies this perspective that you can describe things but looking how they behave in a context. So when I show you those diagrams, what I'm really doing, I'm always picking a category that defines the universe I'm working on and working in. Let me just dig a bit deeper into this idea. So if you want to define a category, if you're a mathematician and you want to define it formally, basically you have to specify various entities. You have to specify objects that correspond to systems in the pictures I showed you before. So objects would be the wires in the box and wire pictures. You have to specify morphisms that are the process, the boxes that transform objects into objects. You are required to specify identities. So for each system, you need to have a process that doesn't do anything to it. And then you basically have to specify a composition law, a recipe that tells you what happens when you compose processes together. Let me give you some examples of categories that are probably familiar to, I hope, as many people as possible here. There's a category called set, where your objects are sets and your morphisms, so your processes are functions between sets. There is always a function that doesn't do anything, and you can pipe functions into each other. For programmers, there is another category called data, where your objects are data types and your programs are programs that turn data types into data types. Again, you can compose programs. This is basically functional programming style programming. You can pipe, the output of a program into the input of another program if the data type matches. And you have also a program that just returns the input without doing anything. So what is the difference between these two categories? Well, set offers an extensional perspective. What it means is that, for instance, if I consider the set of integer numbers, I have exactly one function that takes a number and adds n to it. On the contrary, in data, I have multiple ways of either specify what integer numbers are, and I have multiple programs that sum n to your term. In here, I just brought two of them, but in general, you see that in the category data, the formalization, the implementation matters. So these two categories offer very different views on the same phenomenon. In one case, you're saying, I'm only interested about behavior. I'm not interested about the inner workings of these functions. In the other one, you say, no, I do. And I distinguish two processes. They could emit the same output on the same input, but I want to keep them distinguished. Now, the cool thing about category theory is that you can connect these different perspectives. There is a notion called functor that turns a category into another category. In our framework, this would be a box that is a sort of like level 2 box that allows you to change the universe you are working in. So basically what you do to define a functor is you specify a mapping from the object of the category C to the objects of the category D. So you have to say where systems of C go in D. You do the same for the morphisms. So for each process in C, you have to map it to a process in D. And this is the important thing. These mappings have to map identities into identities and compositions into compositions. So what it means is that if I compose two processes in C and then I use the functor, it's the same of using the functors on the components and then composing them in D. Questions or? Sure. Not necessarily. You can have functors that are called full and faithful that allow you to, basically be inverted and go one direction to the other. But no, in general, you can lose information, or you can embed a less expressive universe into a more expressive universe if you want to. Sure. Sorry? Functors as information? Sorry, I don't. Oh, linear transformations. Maybe, I don't know, like there is this very inconvenient thing that in category theory, everything is everything else. Like I'm not going in depth into that, but you can describe a category as a functor and a functor as a category and blah, blah, blah. So it is possible, maybe, to describe a functor as a sort of linear transformation. In general, what I can say is that you can define categories of vector spaces, for instance, and in that case, your morphisms, your systems will be linear applications that respect the linearity of the vector space. Yeah? Yeah, this is exactly what happens, because this thing is basically mapping processes of C to processes of D. So you can see it as an higher level function, and indeed, a functor is a process in the category of categories. So you can do this kind of, level up. Let me give you an example of functor. This is a functor that actually collapses information. We saw two categories, data and set. And we can define a functor that sends a data type into the set it implements and sends every program to the function it implements. So this is exactly what I was saying before, that you can start in the category data and be, very detailed about distinguishing things. And then you say, actually, I don't care. I want to collapse all this information and I want to forget about, these different details. You apply this functor, and that's exactly what you get. All your process compositions now, lose a part of information. Obviously, there are very interesting questions like, how do I invert these things? Is there a procedure to canonically invert a functor and actually go, for instance, from just a specification to, from a behavioral extensional perspective to something more complicated? Sometimes you can, sometimes you can't. Yeah. So imagine that int is a data type that you define, I don't know, in Haskell about integers. That data type is basically modeling the set of integers in a computer, right? So conceptually, you can say I can send that to Z. Similarly, if you have the data type string, you can have a set of all the possible words on an alphabet. And again, you can send string to that set. With this functor, basically, what happens is that these two programs here get mapped to the same function between sets. So I have two different implementations of the same program that maybe, I consider separate as programs. Like if I, for instance, hash the one on the left and the one on the right, the hashes will be different. But they correspond to the same function. They are implementing the same function. So when I go from data to set, I'm deciding willingly to lose that information. Okay, let's try to use what we got up to now to do some process design. That is actually the interesting part of it. This is a very simple example. Imagine that you have a grid and you want to define the process of moving on this grid. So imagine that you can only move of, a kind of fixed amount of things. So it's not like I cannot move like 0.1 steps, but only one step at a time. In this case, you'll see that wherever you are, there will be 4 fundamental processes that are up, down, left, right that allow you to move one step. And now I can basically describe every path as a concatenation of these processes. So for instance, if I move 3 times right and 2 times down, I'm describing the L path I have there. If I feed to this process a couple of coordinates that tell me where I am, then these coordinates will be transformed as in the end of the path, basically. And we see that in this kind of theory, we also have some equations, like if you move right and then down, that's the same of moving down and then right. You are describing a square, you are just walking in like different paths, but you end up in the same place. Let's spice this up and let's do it concurrently. Now we have multiple agents wandering on this grid, and we want to model, how they move. Intuitively, what you do is, well, now we want to consider processes that happen in parallel. Like if I have two agents, for instance, I can have this process here that says agent 1 moves 3 times on the right, and agent 2 moves down and then on the right. And now we see that new equations pop out. So, for instance, I have this equation here called the interchange law that basically says these two threads are separate. You can see the first as saying, I move somewhere and then I do nothing. The other agent does nothing and waits for you to move and then moves. In this setup is the same if you just, swap the things and second agent moves first and first agent moves later. Why? Because intuitively, these two agents are not causally interfering with each other. Agent 1 doesn't care at all about what agent 2 does, and vice versa. And so in this formalization of moving on a grid concurrently, I have these extra equations. Mathematically, we say that the universe we are relying upon is not just a category, but it's something called the monoidal category. That basically means a category where you can do also things in parallel. Okay, let's do a more like programming-oriented example. So let's consider a very simple record. Let's call it person. This record has two fields, name and surname, okay? Now, you can notice that in this record, in this example, person is basically just a couple of terms of type name and surname. Now, we want to be able to, functionally describe the procedure of extracting a subfield of this record. So you give me a person, I give you the name, for instance. And we also want to be able to replace the subfield of a given type with a subfield of a different type. This is a bit more complicated, but what it really means is that, for instance, imagine that I want to edit this person record, I want to strip surname out and put a new field in called age that is of different type. So the point is, how can we do that in an automated and, more importantly, compositional way? So what I mean by compositional is, imagine this example where I have the record person, but one of the fields is itself a record, is a sub-record. And now I say, okay, I want to replace the city thing there, Bogotá, with something else. Intuitively, I want to be able to pipe the process for editing person with the process for editing address and, feed these, compose these two processes in a way so that I don't have to reinvent the wheel every time. The way you do this in functional programming and in compositionality is with something called a lens. That is a particular example of something called an optic. So what is the idea? The idea is that a lens is just a couple of processes, one called get and one called put. And basically get is taking your record and is giving you the subfield, that in this case is S subfield of A. What put does instead, put is taking your record A, is taking something of type T, and intuitively is replacing S with T, and now is spitting out something of type B. You see, the type of A could change because you replace the type of a subfield of this thing. If A was a couple of strings, with this put, I could substitute a string type with an int type, and then the overall type of the record will change. The funny thing about this is that, there is an Haskell library, for instance, that allows you to automatically get these things for every A, S, and T. As soon as you define your type A, this thing will, create the setters and getters automatically for you. So it's a procedure that you can automate. And that's the cool thing, that you don't have to do it manually. The library does it for you. Okay, so how do these things compose? Imagine that I have two lenses. So the first is taking the subfield S from A, and the second one is taking the subfield V from S. The get part is easy because you see you can just telescopically access the records. You can say, I start from A, I pull out S, and I pull out V from S. The put part is a bit more complicated. So what happens here is that imagine that in S, I am replacing the subfield V with a subfield W, and I obtain something of type T. And now I want to replace S with this type B into A. How do I compose these two things? Well, with this sort of like monstrous awful thing here in the bottom, where I basically take A, I copy A, I get S from A. Now you see I can use this put V, and basically substitute V in S with W. I get something of type T, and then I can use put on T and A to get a B. I know that this sounds very cumbersome and difficult to follow, but the good thing is that you can, topologically deform these diagrams and basically express them in a way that makes way more sense. So in here, instead of considering these things as two couple of separate processes, I'm, packaging them as a unique thing. So as you can see, this thing is a bit strange because it has arrows going in opposite directions. So on the top row, A gets processed into an S. So you are extracting S from A. On the bottom row, you are getting this T on the right, and you are rewriting S with T, and you are getting a B on the left. This is an example of a bimodular data accessor. The way you can think about it is as a process that says, if you give me an A, I will read field S and forward the output to you. And if someone else from the future will give me a T, I will replace S in A with it and return you a B. And the good thing about it is now you can compose them exactly as you composed the processes we saw up to now. And when you do this, if you squint your eyes a bit, you see that we are doing something that is basically equivalent to that cumbersome composition we had before, but now is again graphical, like you can just compose these Lego bricks together. Again, and this is the art of compositionality, anything that really changing is the point of view. So you can still deform this thing in another way. I'm just rewriting the top diagram as the bottom diagram. If you see, the interconnectivity of the diagram didn't change, and I can shape it as a comb, basically. And again, it's the same. Like you get A in, you get an S out, then you get a T in, and then you get a B out. This is really interesting because when you look at this comb process, it really looks like something that wants to be a normal function, but it can't because it's waiting for you to do something. Intuitively, if you have an automated way to turn S into T, that thing would just be one of those naive building blocks we saw in the beginning. And, in this framework, the composition will be nested. It would be of this sort. You are basically composing combs by substituting a comb in the whole of the bigger comb. And again, this composition is exactly the same when you follow the processes and the interconnections of this one. This one and this one are the same thing. We just deformed the way we arranged the diagrams. Now, again, as I said, you can see a comb as an incomplete process that basically is waiting for you to do something to turn an S into a T. And that would be that F that you put there. And if you put it there, this thing basically closes up and just becomes a normal process. But what is really interesting about this is that we found a pattern. So we started by modeling record rewriting, but now we found a new pattern of composition that is this kind of nested composition. And indeed, there are a lot of things that compose in this way. If you abstract from details for a second, these two processes are basically representing two different points of view of the same thing, that is bidirectional transformations. Now, let me give you an example of how you can use these things. An example would be escrows. What is an escrow trade? An escrow trade is when I want to give something to someone, but I don't trust that someone, or that someone doesn't trust me. And so what I do is I take my funds, instead of giving them directly, I lock them up in a vault. And then basically, you know, my counterparty will ship me some goods. And when I receive them, I will confirm that I received them. And at that point, my funds are unlocked and forwarded. And that is exactly a comb-looking thing. It's like, I committed my funds, I locked them, and now I'm waiting for confirmation. And as soon as you give me confirmation and you put it in that comb, then this looks like a standard transaction from A to B. Another example, and this will be the main point of the second part that my colleague Philip will do, is game theory. So we can model games in game theory as open processes, basically. In that case, a game will be a process that has, again, 2 inputs and 2 outputs. It will take an input and observation, so it will observe the word. It will spit out an action according to some strategy. It will receive a payoff from the outside world, and it will return a feedback. The feedback is probably the most difficult part to get in this composition method, and you have to imagine it. One of the ways to imagine it is the portion of your payoff that you have to return to someone else. Stupid example, if you take a debt, you place a bet, you win, you get a payoff, but you have to repay the debt. And the debt repayment would be the feedback wire. In this system of compositional game theory, we can recover traditional games as a composition of processes. So this, for instance, is the prisoner dilemma. I guess a game most of you are familiar with. And normally we see it as a payoff matrix. And, you know, like, if player A does this, then this is what happens. If player B does that, blah, blah, blah. In this case, prisoner dilemma is a composition of 3 different processes. Player 1, player 2, and payoff matrix. These 3 things in isolations are games. Player 1 and player 2 are games that do not observe anything, because you don't do any observation in the prisoner dilemma. They just act, they just, you know, express a choice, and they receive a feedback for that choice. The payoff matrix game is a game that doesn't act, it doesn't have any strategic value, but it just observes the players move and returns some feedback. And again, you see that in this setting, the players' payoffs are the payoff matrix feedback, and the players' actions are the payoff matrix observations. So yeah, the cool thing about that is that now we can quickly prototype games by basically creating these blocks and interconnecting them with each other. One thing we're currently working on, and Philip will show a demo of this, is, for instance, a way to lift EVM bytecode to open games automatically. In doing that, you know, if you deploy a smart contract, we can take your smart contract and put it into this framework, and then we can strategically probe it. Your smart contract would become like the payoff matrix in this system, and then we can economically probe it with players that can be honest or untrustworthy and see, you know, which strategies are actually winning strategies or not. And so if your contract is economically sound, economically stable or not, or in within which bounds it operates financially in the way you intended. So this is the theory part that is concluded, and I will leave for the second part everything to Philip. And basically, yeah, in this short tutorial, we saw how we can use these compositionality techniques to guide our intuition in designing processes. We started with something very simple. Then we did a bit more involved examples, and then we found out that those examples were actually modeling a more general pattern, this bidirectional composition. And we were able to basically recycle that pattern to instantiate other things like escrows or open games. And yeah, that's everything for me, and I'll just pass it to Philip. Thank you. you have any questions, yeah, sorry. If you have any questions, we can, in the meantime that Philippe hooks up the computer, feel free to ask. Sure. Define, huh? Yeah. I mean, in here I kind of cheated because I basically just defined an optic as, you know, this box abstracting the details. Indeed, mathematically, you can prove that, I mean, the definition of optic is exactly something that embeds that thing. Mathematically, it's a bit complicated to describe, but graphically, that's exactly what it is. An optic is something that has this sort of nested notion of composition, basically. Sure. Yeah, there are various ways to do that. Philip is the expert in this, and I don't know, maybe you won't answer that.
Yeah, sorry. What's your question? Whether you can also do repeated? Yeah. Yeah, you can do that. So the game that Fabrizio showed is a one-shot game, but you can also think about this as taking that. Let's say you want to iterate it finitely many times. You just stack it on each other. The only qualification you have to make, if you looked at the slide, there were basically the wires were not coming in from the outside. You have the game with wires, and then you can stack it basically. An alternative way to do is also you can turn it into a Markov game, which has a state, and then you can basically think about it as approximating it to be run infinitely. Okay, other questions to the first part? There is a question to the first part. Mm-hmm. Let me do the following. I'm jumping on my slides ahead to show you this. Then I will go back. Sorry. Could you, guys? Sorry, can you switch on the? Okay. Let me go to the. So here, you have to think about it as two dimensions, right? So time flows from left to right, and if you start from the left, there are two things, P1 and P2. They are not connected, which means they happen in parallel. So this is simultaneously happening. Then afterwards, they output a move, which is Y1 and Y2. That move is consumed by U, which is the payoff function. And in that sense, U follows sequentially after these two games, right? You can also think about these two games, P1 and P2, being merged into one. And then it's just two games being stacked on top. Okay, so let me go back to the start. You can already see what is coming. Okay, so what we want to do in this part, in the second part, by the way, hi, I'm Philip. Thank you all for coming. What we want to do in the second part is basically take a deeper look at compositional game theory as one specific instance of how you can think about compositionality and what compositionality possibly can give you as value to, as an approach to thinking about, in that specific context, of strategic interactions. Okay, compositional game theory, what is that actually? So it's at the beginning, actually, this was a research project which was focused on providing a new formal language for game theoretic reasoning. Yeah, you probably have heard about game theory. Many of you probably have already seen it. It's a mathematical language to express the reasoning about agents, and what we provide is just another language in some sense. Now, this language is, as Fabrizio already introduced, based on the categorical framework, and this has several consequences. One is first of all, you get a graphical way of reasoning, but most importantly, you get a way of compositionally approaching the modeling problems that you face. Okay. Now, if you just do the diagrams and you suppose you would be forced of using diagrams for very large systems like a staking protocol or other more complicated systems, that would be limiting. It would not be that much help. It might be a cool new theory, it might be of interest for some academics, but practically, maybe not so much relevant. What, however, is a consequence of what also Fabrizio already said, there is a very close connection to optics, and optics allow more or less these things to be directly implemented, enabled us to also develop on the side a software tool which basically takes the language of category theory for modeling games and turns it into a software framework that you can use that supports your modeling process. And that's the key thing, because if you would be forced to doing things on pen and paper, well, yeah, would not be that practical. Once you have this tooling in the back, then you can actually leverage basically the benefits of compositionality. And the purpose of that, basically second part, is hopefully to convince you that at least this might be interesting, and hopefully even more that this might be really useful. Okay, so a large chunk of the talk will also focus on the implementation. So what does the implementation actually provide? First and foremost, it's just a framework in which you can express and represent strategic interactions, like the prisoner dilemma, but obviously also more complicated stuff. Many times, you're not only interested in representing models, but you naturally are interested in, what kind of behavior may result from these models. So you also want to analyze them in various ways. In the current engine, there are basically 3 ways to do that. One is interactively. So you basically run a session, and then you can query your model. Let's say I'm looking at a staking protocol, and I have some idea what would constitute an honest strategy of the participants. And then I can ask, okay, if I'm feeding in a strategy, is this actually an equilibrium? Or do specific agents have an incentive to deviate? And the way it works is a bit like a proof assistant. It will tell you, your proposition that these strategies make sense, either make sense and then it's good, or the compiler or the engine will tell you, wait, at least one agent basically has an incentive to deviate. And here's the incentive, here's the specific action that this player can take. Now, the interactive part is very useful to explore parts of the model, and for the staking stuff, we will also see an extended example on this. It's quite useful to think about specific vectors of attack, and then you can verify, does this actually work, or what do specific agents actually react to if the strategy of another player changes. You can also think about this, Fabrizio alluded to that, that there is a system A, which is somehow represented as an open game, or several open games. You make changes in that system, these changes propagate in your open games, and then in the back you're running tests on what kind of behavior would you expect from this kind of system. Yeah? So it might be that you have an incentive mechanism and it works, but you make a change to the overall protocol A. How does that actually, then this is translated into the open games framework, and in the back you're running tests on the behavior of the agents. And then maybe things go through, or you get a warning, something is not working anymore as before. And lastly, theoretically, as well as from a practical implementation perspective, there's a very close connection to machine learning frameworks, specifically reinforcement learning. I will say a bit more at the end if I have time. But the idea basically is that you can either leverage reinforcement learning techniques and machine learning techniques more generally for solving and analyzing games. Solving, of course, has limitations because it's very complex. But for some specific games, it's feasible. And on the other hand, you can also turn it around. You can also make learners basically part of the game so that you have an interaction of learning agents, basically. Which is also quite useful because you basically can think about this as institutional players updating, or actually learners themselves as part of the model, for instance, in pricing settings. Okay. What's the key innovation? Well, compositionality, obviously. That's the key point. But what does it actually mean here? If you think about the prisoner dilemma, what is already showed is that you can think about the prisoner dilemma, at least from what you have seen so far, as either one monolithic building block, or at the minimum, you're splitting it up in 3 components. Right? Now, for a prisoner dilemma, that's not that relevant. But the more complex your scenarios become, the more helpful it actually is to say, look, I'm taking that part, I'm zooming in, I'm modeling it, zoom out, take another part, model that, zoom out, and so on and so on. And later on, if you do it right, you have basically systematic ways of composing these things together into a bigger model. Now, this doesn't end at that level. You can also, for programming purposes or because of convenience, you can further modularize your code. Let's say there is a specific thing, a specific way you want to approach it. You can split these up, implement it in different ways. And the key thing about all of this, basically so far, is that all what you're doing will be guaranteed to make game theoretic sense if you follow basically the syntactic descriptions or restrictions of the engine. That means you start out modeling. If you use our language, you can decompose things. Each of these components will make sense from a game theoretic perspective, and the composed thing will also make game theoretic sense. That's compositionality at action. Why is this useful? Well, you get an overall view on your situation that you want to model, and it is sound, and you can ask questions like, okay, what's the equilibrium of that? Or, if we repeat it, is there a deviation strategy? If you think about more like a Markov strategy, for instance, are there ways of deviating that are profitable for specific players? Another perspective basically is that this turns the modeling exercise into a programming exercise. So the idea of zooming in and zooming out, and modeling parts in isolation is more or less just like divide and conquer, a typical pattern that you would apply in any kind of, or in many programming problems. Okay, and the key thing again is you can modularize your code further. We will see this later on. We will have regular Haskell functions that we just lift into that, and you can change these components. But as long as you're staying inside of that system, you are guaranteed that these things are kind of well defined. Now, a warning: the fact that this is game theoretically well defined does of course not mean that your model makes sense. You can model complete garbage. We can't help you with that if you're really intend to do that. But what we can guarantee to you is, or what this kind of helps you is, at least in the process of modeling, you have a scaffold that you can use. All right, so how is this useful? The main thing basically is, I alluded to that, if you can apply divide and conquer, you can easier deal with complex scenarios. It overall also speeds up the process of modeling in several ways. First, division of labor. So in principle, the larger the systems, you can actually very easily collaborate with people. Secondly, if you want to change a component, you can easily do that as long as the rest stays intact. And lastly, because everything is expressed as code, there is obvious reuse for components. And we have had several projects in the past, and we can see that there are some patterns that just emerge that you can use over and over again, which is useful because it speeds up down the road how when you want to model something. Okay, and of course, yeah, I mentioned this already before. You can also think about it as just being part of a larger stack where it's fulfilling a certain service, like testing properties again on the safeness of the system from an economic perspective. Okay, this is kind of the introduction, very roughly what this engine is doing, why it's possibly useful, why it's maybe interesting. What I want to do for the rest of this workshop, and for basically the second part, I will give you an intuition about how to model with this tool, how to represent games, and again, the focus will be on showing that compositionality is actually useful, or hopefully useful. Secondly, I will also give you an intuition of how does an analysis actually work, what does it look like. I will be shorter on that second part. The reason is, in order to make sense of the analysis, you obviously have to have a deep understanding of the model. This is, given the time constraints, not really feasible, but I still will give you an intuition of how does it actually work, how does this look like. Okay, and a leading example that we will converge to is basically a staking protocol. It's a simplified model that illustrates these two components of compositionality and also the kind of analysis you want to run in this system. Good. I start with not code, but directly coming back to what Fabrizio actually did, namely introducing a bit theory. This will be partly repetition, but it doesn't hurt. It will be mostly about diagrams, so not much mathematical content. The reason I do this is the theoretical approach is more or less directly the way that the implementation works, modulo some kind of difficulties in the back, obviously. If you understand how the modeling on the theoretical side works, you basically have a very good idea of how then the syntax actually works and operates. And that means you also basically know how to use that engine, basically. Okay, so you've seen this. This is a bidirectional information transformer from both sides. So X is transformed into Y, and then there's something coming from R to S. Both directions. Again, convention is, if you want to think about this, is that time is on the left, so on the side of X and S, and the future is basically the past is on the X side and the future is on the Y side. Okay, now, in some sense, in the essence of compositional game theory is that what we showed is any kind of game that you want to model has this shape and can be put into this shape. Whether it's just a single player making a decision, which is kind of a non-typical game, or a very large complex system, many players moving and interacting, everything can be modeled in that shape, whether it's very large or very small. Yeah? Now, why is this good or why is this useful? Well, it's useful because you can start out with small components, like one player, maybe just also computation, something very trivial, and you can plug these things together and slowly from the bottom up, like Lego blocks, you can build up a system that is quite complex. And of course, because you're programming, you can also kind of box things and say, well, this is a pattern, maybe two players interacting in a certain way. This is quite useful. I'm giving that a name and I'm going to be reusing that component over again. Okay, so everything is of that shape. So it's a bit like, it's like a closure property in some sense. You start out with a number, you add a number, you end up with a number. It's the same here. You start out with one game, compose another game, you end up with another game. And this is in some sense what I referred to before as this guarantees you that you stay in a formally well-defined framework. Okay, let me come back a bit to the concrete interpretation of this specific box. And for the next few minutes, think about this box as just one player doing something. Now, one way to think about this is essentially the player is just doing some kind of information transformation, right? So there is something coming from the past, a move, information, whatever, X. The player observes this, and internally something happens. He's outputting a move, Y. Okay? Now, the question, of course, is what kind of move will the player make? This depends on what kind of moves he has available. But it also, of course, if it is a game theoretic agent, and assume for now it's a rational agent who wants to maximize something, he needs to think about what's my effect of choosing Y on my utility. And you see that the Y is an open wire, so it doesn't really specify exactly how it is interacting yet with the environment. But what we can say is the player is expecting an R back from the environment. And this openness between my action Y and the payoff that or whatever actually R is, in fact, what I receive from the environment, that openness makes it possible to take it like a building block, put it in specific situations, and then sometimes I might be able to close the loop in a certain way. The most trivial way of closing it would be I have one player and I'm just bending the Y back into R, and then basically my Y, my action that I take, will be directly the thing that I observe and I affect. I have full control, basically. Most interesting scenarios from a game theoretic perspective are obviously not like that, but my Y will not solely determine what my payoff actually is. Like in a prisoner dilemma, there's another agent doing something, and this will also affect my payoff. And of course, this is the idea that at some point we will give a concrete environment which determines how this Y actually is bent back into a specific payoff, whatever result you actually care about as an agent. Okay, so that's the basic structure. Now, as I said before, we are building up from the bottom. What we want is, we want to compose larger games by composing simpler games. And what we need for this are essentially two kind of things. We want some building blocks. Think of it, again, like Lego. You have one specific thing, and from that, if you have it, and you have more of them, you can just build up a wall, for instance. So we need the building blocks, the atomic units, if you like, and then we need operations how to compose stuff. On the atomic building blocks, we have essentially two, which is a decision, a single player making a decision, and a computation. Computation means just some input is observed, some output is basically the result. These computations can have side effects, so it could be actually a deterministic input is turned into a probability distribution, or a probability distribution as an input is turned into another probability distribution. Good. What are the composition operations? For those of you who already followed Fabrizio, you will already guess it. It's parallel and sequential composition. Parallel, in the game theoretic sense, is maybe more easier interpreted as simultaneous. And what this looks like essentially is, again, repeating a bit of what we have seen. You have two games, G1 and G2. If they are in parallel, you can compose them. And then they, again, will have this basic shape of input X crossed X2 in that case, turned into a certain output. Yeah? And at the same time, expecting a certain result and sending some information back into the past. Okay, sequential composition. We have G first, H following. You can stack them on each other so that they look in the following way. Now, what is important, so far I haven't said anything about what these labels X, Y, and actually correspond to. You can think about them as shapes, and only games that actually have the right shape can be stacked on each other. And this is important because, if I say, give me two games and I can compose them, you might wonder, that sounds weird. How can this be possible in generality, right? I can easily come up with two games that are not so easy to, or maybe not at all, composable. The restriction that you have is that these shapes, the labels here, actually have to match up. Only then can you stack games together. Fabrizio already said from a categorical perspective, and then of course also from a programming perspective, these labels will be types. So only if the types match up can you actually stack games together. This is quite useful, and it's actually an important restriction because, if let's say G is outputting a Boolean and H is expecting a numerical value, a numerical type, you can't match them up, basically, right? What is even more important, if you try to do that, the engine, in that case, the Haskell compiler, will loudly complain that this is not feasible, you can't do that. What is more, because you can obviously design your own types, you have also degrees of freedom of being very specific about what kind of input type is actually expected. Yeah, so it's basically also part of the modeling effort that you have control over how easy is it actually to stack these things. Okay, and full circle back to the prisoner dilemma. Again, I already alluded to it. Just very briefly, what is this actually representing? Two compositions, first parallel or simultaneous between P1 and P2, and then sequential, the U. And again, if you go back to the parallel composition, you can basically think I'm first composing the two players in parallel into, again, this shape, and then I'm composing that one sequentially with the utility function or the payoff function. Okay. Questions so far? Yeah.
Can you explain why the utility function is applied sequentially?
Yes, in the sense of the utility function essentially is just a computation, right? So it's waiting there for you, and it's waiting for two actions, one by player 1 and one by player 2. So it has to wait until these actions realize. In that sense, it's sequential. In the implementation that I show you, you will see this directly as variable output of P1 being fed into the U. Okay. Other questions? Okay. Implementation. First, a bit of an overview. So what does the implementation actually look like? It's a domain-specific language embedded in Haskell. You might wonder why Haskell. One of the reasons is that, and Fabrizio already said this as well, the optics and lenses are something that exist, and you can build implementation basically on pre-existing structures in Haskell, which is nice because your theory has a direct correspondence to the elements that you use for the implementation. In other words, it makes it also easier to control that your implementation actually is correct. Okay, another thing which is quite useful, the typing system of Haskell is can be, well, sometimes your enemy, but sometimes also your friend. If you have larger components, larger operations, and you wonder what inputs, if you want to query games, do I actually have to supply? The type system is quite useful because it infers the types, and it can tell you your strategy that you have to supply has the following type, right? It's a tuple of double, bool, or maybe something much more complicated. This sounds at the beginning kind of bit, why do you need that? Why would you need that? But the more complex your scenarios are, the more useful these properties and this functionality actually is. Okay, this is under active development. It's under the active development from two sides, from the programming perspective of things we feel like features that we want and we want to implement, but also the theory is continuously developed. This is something I will come back to at the end if I have time. Okay, we are using it for a couple of things. Staking protocols, a simple example you will see today, token design, and there are also applications outside of crypto. Good. The first thing we want to focus on, how does the engine actually work in the sense of how do we represent games? How does this work? All right, so on the left, you can see again the game with the inputs and outputs. On the right-hand side, you basically see the syntactic expression, which is basically this square bracket open game, and then what follows until the last square bracket. That internally is basically the DSL and telling, here is a game coming with a certain shape. Okay, there is what is called internals of G between the dashed lines. I will say something about this in a minute. First, what you should see is there are 4 fields: inputs, feedback, output, returns, and they exactly correspond to the wires. Yeah, so you can see this as basically a way of expressing a two-dimensional element, a kind of language into the language or the programming syntax within Haskell. So the inputs are just the outside system. Another way to think about this box essentially is each open game is almost like an interface, right? You have something internally happen, but to the outside world is somehow it is connected, or maybe not connected, through its interfaces that it offers. What happens internally? Internally is where the place of where the information is generated. So inside of these dashed lines, there are what we call line blocks. These are 5 lines, basically. There could be many of them. They roughly correspond again or mirror the outside wires. So inputs, feedback, output, returns. And then there is an additional field, which is the operation field. That is essentially where information is created. Now, the first thing to observe is in a simple game, if I'm just talking about one single player making a decision, the input X could be exactly linked to the outside wire X that I showed you before, and it's the wire going out, or actually coming in. Similarly, the output Y will be the result of the information that is created and will be directly pushed outside of the box. However, this is not necessarily the case in the sense of there could be more line blocks, there could be more complicated things, and some of these inputs and output fields and so on could be just totally consumed inside of that game without any exposure to the outside world. Okay, the operation can be two things. Like here, this is the dependent decision, just means this is a decision operation. So one player makes a decision, or alternatively, a computation. These two building blocks. You don't need more. If you have that, you can basically build the most complicated model you want. Okay, here's the prisoner dilemma. Again, the diagram from before. First, you can see, if you look at the left-hand side, the outside fields, the outside interfaces here are empty. This tells you two things. First, you don't always need to supply information. Sometimes the games are not connected to the outside world, or only partly connected. And internally, what you can see is there are three line blocks. The first one, the second one, and the first and the second basically are player 1 and player 2. Again, for both of them, they don't observe anything from the past. There is no input. They output something, which is the decision player 1 and decision player 2. And they also need something from the environment back. This is the payoff player 1, payoff player 2, which are only defined at the third line block, which is the payoffs PD. This is the utility function. And here, coming back to connecting to your question before, this function is expecting basically an input from above, which tells you this is a sequential composition. Right? Keep in mind, the diagrammatic language is two-dimensional. Haskell is not. Okay. Now, the last element, the payoffs PD, is also outputting the payoffs, and these payoffs are then connected back to the players. Yeah? And you can see already, certain elements of Haskell also help because the order of where these things are actually don't matter, and it helps in the evaluation later. Yeah? Okay. Questions so far? Is the syntax roughly clear, at least? The idea. So. Yeah, you have a question.
For the last slide, I wanted to ask about. Oh, thank you. I wanted to ask about the inputs and feedback before and after the internal definitions. Like, are those the inputs going into P1?
You mean outside of? Sorry, on this slide.
Yeah.
Yes.
So the first inputs and feedback, the ones that have a blank.
Yes. Okay, I should have been precise. Thanks for the pointer. So what is actually, the inputs would correspond to an ingoing wire into the overall game.
Mm-hmm.
I could think about the overall game as a box itself, right? So this is just one box with possible ingoing and outgoing wires. What it essentially represents is not an empty box, but a box which is not connected at all to the outside world, right? Okay. It's like I'm cutting just away 4 of these wires. And why is this relevant, actually? If you think about a prisoner dilemma, a one-shot game, it has no past, and it has also no future, right? It's one shot. By definition, there is no need to send information back or send information into the future. Right? And topologically, I can kind of represent these features in the sense that there are wires or there are not wires. It's also useful in the sense that, if you model more complex games, you can see that only when there is a connection through a wire, there is actually an effect happening. Mm-hmm. So sometimes these diagrams can be extremely helpful in kind of understanding what are actually the dependencies.
For sure. Thank you.
Okay, other questions? Okay. So in the last part, I want to look at a staking model. This is a simple model still in the sense that I can mostly explain all the components that are needed in the scope of the workshop. The motivation comes actually, I should actually have said that part of the engine were kind of funded by the Ethereum Foundation, and we were working with the Robust Incentive Group. That was one of the examples that they prompted us to work on, and that's basically what we did. So this is a simplified version of that work. I will focus on compositionality. You can guess it already. Specifically now, what I want to show is how I'm basically not composing things, but I first will actually decompose stuff. I will look at the overall problem, and I will put it in as small parts and bits as possible. I want to also illustrate what we sometimes refer to as a zooming in operation. I said before, all of the components are making game theoretic sense, which means if I'm modeling something complicated, I can, when I want to, obviously look at the overall complex thing and analyze this. But sometimes I might not care about the overall thing, but I might just care, let's say the validators in the staking protocol, what are they actually doing for a specific input? What I can do then is, if I have the model as a specific component, I can just zoom in, look at this specific thing, analyze this specific thing without regard of the rest. It's a bit like unit testing of specific units, if you like, which can be extremely useful. Given time, there are obviously more details that I cannot explain all the details behind it, but this is explicitly based on a blog post that we wrote, which gives much more context also on the relation to where the idea for the model comes from, and also all of the components are explained in detail. Okay, so what's the basic setup here? We have essentially several periods, possibly. In each period, there's one proposer and there are two validators. What are they doing? The proposer basically observes a chain. I will say in a minute or give you a picture of how this actually looks like. And the proposer basically observes that chain and then decides, yeah, I want to extend the chain, and basically says, okay, there are several blocks. On which block am I actually building? Yeah. Again, it's simplified. And what are the validators doing? The validators basically observe the delta between what was the chain before and what was basically the result after the proposer moved. And then they can make a decision. They have to make a decision on a voting decision on what do they think is the legitimate head of that chain. And legitimate, obviously, in the sense if they are trying to be honest and are not malicious. Okay, so this would be one example of how this looks like. What is the underlying data type? In Haskell, we'll be using Haskell, obviously. In Haskell, this will be what is called an algebraic graph. It's just a simple graph here. Each block has two information, namely an ID and then votes. In that specific example here, this would be kind of the ideal world. We started with block 1, build on that block 2, and so on, have a linear chain. The votes are in, everything looks fine. Okay. Now, if you take that as a specific input for one period, let's say this is the, now is period 4 coming, what will be the action of the proposer? The proposer will basically say, yeah, I want to build on that chain. I'm choosing, in that case, I'm choosing ID 3, which is the legitimate head, according to the protocol that we are interested in. At that moment, he makes the decision. That block gets appended, but there are no votes yet. And then the validators come in. They observe the ID, which was proposed, and then they can cast their vote. And in this case here, they will do everything is very nice. Yeah, this is the really nice world here. Okay. However, sometimes things are not so easy. Specifically, if everything would be deterministic, then obviously all the problems would go away. But you have networks issue in reality, which means these staking protocols are hard. You have to think about certain problems. One of the problems could be that what if there is time lag between the proposer and the attester, and what happens if, so this is an example here, there was a proposer in period 4, and he's actually malicious. He's just letting time pass by. At some point, proposer from the next period observes the chain, thinks, okay, the other guy hasn't done anything. I'm building on that chain, and legitimately, he's honest, builds on ID 3. And at that moment, before the validators come in, the proposer from period 4 actually sneaks in and places in his own block on that chain. So he's forking basically. And now the question is, what happens? This is one of the motivating examples. Okay. Do you have questions to the basic setup? More details follow. Okay. If not, let me jump to. That's not really looking nice. Okay. Can you read this? Should I increase the font? Is it okay? Okay. Left-hand side is basically the model. Right-hand side will be just an interactive session that I will be using. Let me start with something first. In order to implement the model, you need a lot of background information, right? I need to actually think about what's the data type of the chain. If there is a new block being proposed, how do I actually add it? This is, for instance, this function here, add to chain. it's just observing a chain, it's observing an ID which was proposed, and it's creating a new chain. So I need a lot of background stuff in order to make this model work, which is just basically Haskell, in that sense, Haskell functions and computations. Another one would be, for instance, determine head. Clearly, in order for the protocol to work, which has a certain goal, I need to be able to at each point say what are the head or the heads if they are non-determinate. And this is basically the second function, what it's doing. And there's a lot of other stuff that I'm not showing you that comes in. So you need for that, in order to kind of use this, you need first this the structure in order to basically, I'll say this is the computational background to which I'm working. Now you might wonder, okay, wouldn't it be nice if this would be coming from the outside world? And indeed, for some problems, you just need to create it. But in other cases, and this is something we'll be working with in the future or towards, is can part of that basic infrastructure that we are interfacing with in the end, and that is actually not that interesting from your modeling perspective, it's just something you want to take as given, can you somehow import it from the outside world? Or can you connect this tooling to the outside world? Okay, for this purpose here, I'm just recreating it. What it actually does is not so important. Just think about it for now, what the behavior is of add chain and so on and so on. Some functionality I will explain on the fly. Good. These are all functions. The first thing we want to do, we want to create basic building blocks that we will be relying on. Yeah, I said before, we will make it here really, really kind of fine-grained in the sense we start at the real bottom of, let's make add to chain actually an open game. Put it into a computational framework so that we have a building block that we can move around if we want to. Similarly, let's do that for determine head. Maybe we need it at different points. And then we kind of have this building block available as an open game. Also note, essentially for the whole system here, the protocol logic is exclusively in determine head. This is this function that you can see here. If you change that, all the rest stays intact. And that's another way of, if you make it, if you try to approach the problem in that way, you will save a lot of redoing if you want to make changes to the protocol. Okay. Let me jump here. Okay, so I showed you the function before. Let me actually put it next to each other. So add block basically is doing nothing else. It's just a computation. It observes the chain old and observes an ID, and then it puts that into the inputs field inside, and it's basically, this is the forward function keyword. Remember, we had the decision and basically computation. This is one instance of the computation, and then it does just the add chain to weight, yeah? Which is similar to what we have on the add to chain. Why the weight I can explain in a minute. Yeah, but it's in principle, it's the same idea. You just take a component, plug it in, and lift it into an open game. It's just a computation. Similarly, determine head of the chain. Here, as you can see, this input here is basically just a function from the right-hand side. I'm lifting it into an open game, just a building block. Good. These are very boring building blocks, so let's move on. What do I need? I have proposer, I have validators. So what makes probably sense is to think about how does the validator actually look like? Okay, let's model the validator. If you think about what the validator is doing, I said before, the action he does is he observes the new chain, he observes the delta, which means he also has an access to the old chain. That's the input here. That's also the input to the line element here. And then there is a decision, and what you can see here in that expression is just basically that's telling internally the dependent decision operator what is the action space, so where does it actually can choose from. Here, this is basically just because we start the IDs of the blocks from 1 until the vertex count, basically how many vertex are there, and then this is basically the choice that the validator can do. Okay, so we have basically a bit of computational background, add to block, we have the determine head of chain, we have the validator. Now we have the proposer. Okay, what is the proposer doing? Well, the proposer observes the chain, also internally. He makes a decision. What decision does he do? Well, he can choose basically on which block to build. That is the outset, this is the decision proposer, which is coming out here. And then you can see this is the first game in that context where we have another line block. There's some kind of additional functionality. This is just basically producing the new chain. This is taking two graphs. This is, as I said, this is a specific library from Haskell, which is algebraic. You can just plug things together, and you get the new chain. And the output, so the wiring of that game is basically chain old and chain new. This is my interface of what the proposer is doing. Okay. Now the thing, I cheated you a bit on two places. Maybe you already spotted it. If you look at, for the validator as well as the proposer, if you look at the return type here, the return field, I'm returning a constant 0, which is kind of weird, right? Because I said before, isn't that where actually the strategic context come from, the environment telling me what to do, blah, 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 blah. And now it's just saying it's 0. Doesn't look really strategic. Now this is an instance, and I will come back to this. This is an instance of where we actually had exactly what I just blah, blah, namely we had the inputs coming from the outside world and plugged them through, but then realized that there is actually a very neat, useful pattern here that we can abstract out and make it much easier to compose later on the payoffs in a different way. Yeah, this is in some sense a bit of Haskell background that made it possible to kind of split this up even further. That is what I meant initially when I said, when you start modeling in this chain, you can of course sometimes realize just programming patterns, classically abstract them out and replace them with something else. Why is this actually happening in a sense? Keep in mind, for the protocol to work, in period T, the decisions of proposer as well as validators are not rewarded. They are only rewarded in the future. That means their reward actually is conditioning on what is coming from the future. And this is a way, and I will show you in a minute, how we actually can deal with this. And the same is true for the validator as well as the proposer. Okay, so here's an example of what you can see, basically how this is done. This is what is called update payoff validator. This is an auxiliary thing. It's taking in a bool. The bool is basically, was the validation correct according to the protocol? That is then determining the payoff. Payoff can also be negative. So if basically the protocol determines what this validator did actually in T plus 1 doesn't actually look good, so we will punish it. Could be a negative value. Okay, that value is feed forward, and then there is this add payoffs construction. This is just another open game. And what internally is happening, internally, this is associating the payoff to the player, which is parameterized by name. So you can put this component in different places, and it will automatically add the payoff at that point to your player. Do you have to do it in that form? No, as I said before, you could also kind of make it more with the wires and so on. But this is a pattern which makes it extremely lightweight of recomposing the payoffs. And again, this is useful for the following reason. If you think about, and for here, I'm assuming the payoffs are evaluated just in one period advanced. The proposer do something, the validators do something, and then in the next period, it gets evaluated what they actually do. Of course, I could have a protocol which actually takes more episodes. What do I do then? I can, of course, kind of take the wires, put them through, which is still okay, but I can also just use it and say, well, the information flows in direction, and I can compose this value add payoffs with the same name, with the same identifier, again at that point, and I'm done. It's not something we planned for, but it's just something which emerged out of working on this. And there are other examples like this. Okay, these are the components that we need. Now we want to take the next step. First, let me also. We have not only one validator. But we have several. What we do here, we are grouping them together, right? So we say, well, there is a chain new, chain old input, and then there is some kind of information. This is just information about past behavior from the other validators from the period before. And then the thing is, what you should observe is the following. Here and here, validator, this is the construct which is on the right-hand side. So we take that and plug in the open game here. Yeah? And this is basically the second step of nesting. We already have one for the proposer, but for the validator, basically we bottle it as an open game, and then we plug it into the group. And now you can also see the structure basically of that component validator's group decision is made that you can also extend the number of players if you want. You just basically add one line here, add functionality, but the overall interfacing of that group of decision-making process is the same, whether it's 100 or just 2. And there are also ways, I should say this, you don't always have to make this explicit if they are symmetric in some sense. There's also convenience patterns such as can say, here are 10 players of the same type, put them there. Good, so this is the validator's group decision. We also need to make the payment for the validators. Again, it's not only one validator, but 2. And again, you could think about this as being extended to more players. The thing to keep in mind and I repeat myself, but it's important, this validation step is in time t for the behavior of t minus 1. Yes, you have a question? Okay. Maybe you ask a question again and everyone hears
Yeah, I was asking, I'd like to know what's operation.
The operation field, basically.
Yeah, the operation field.
Okay. The operation field is, from one perspective, basically where the strategic information is created. If it's a function, it will be just saying, let me give you the example here. I'm filling the operation with basically two keywords, namely either forward function or dependent decision. Yeah. What is the forward function doing? It's just lifting a normal function, a normal Haskell function, into an open game, which means in the simplest case, it's just a deterministic function. That determine head takes a chain and outputs a head, and then I'm interfacing it with the outside world. If you're talking about a decision, it's different. Look at the validator. This is the keyword, dependent decision. The validator, in this case, the decision is the following. The player observes this chain new, chain old. That's his observation, his information. And then he makes a move. He has to pick an element. And this element, in that case, is an index to which of the block elements do I believe to be the head, or I'm choosing to be the head. Yeah? Okay.
Shouldn't there be an operation between returns and feedback?
Sorry, say again?
Like so this is doing the from left to right movement, let's
Correct.
say. And what about the other direction?
Okay, that's a good point. So first, let's take one step back. If you think about the prisoner dilemma, there was also the case where the agents did not send information back into the past. Yeah? Okay, so that explains, and the reasoning is simply here, I don't need to send the information from these players back into the past. And the reason I don't need to do that is there's basically the protocol is moving forward, and I don't need to send this information back. It's like I'm creating a state, and the state will summarize what is going on. Why I'm doing this in this form is the following reason. I will end up with one episode. That episode will be basically a basic game for a Markov game, and then I can stack these again on each other and repeat them if I want to. Now, you are right. If you wanted, let's say you just explicitly wanted to model two episodes, you could say parts of these elements, for instance, what these guys expect here, what the return is actually coming from this returns field over here. And I said before, you can do that. The reason I'm not doing it is exactly for if I want to stack more episodes with payoff still being created for players in, let's say, T-4, I can easier do that. Okay? Maybe it will become clearer when we come to the rest. If not, feel free to ask again. Other questions? Could you tell me the time? I have no idea. 25. Okay, good. Okay, validators payments. Again, this looks like a bit more convenient stuff, but this is the question you should ask if you model it yourself is how can you model it in a way that it's actually really a building block? I said before, one way of doing it is that the interfaces are relatively flexible. So I'm just needing the fee, which is an outside parameter. And then internally, basically, I just need the payoffs. I need to chain new and the head ID, which was chosen. And with that, basically, I have the full picture and that the protocol can evaluate, was the behavior actually correct? Okay. And you can see this is actually happening in a function that I didn't show you. This is attested correct. The attested correct is basically just telling, according to the logic of the protocol, the information I got, yes, made sense, or no, and it's outputting a bool. It's just saying yes or no. And it's doing that for player 1, and it's doing it for player 2. And these then corrected, attested are basically input into this function payoff validator here on the right, which you can also see here. It's just taking, was the validator correct or not, and then it's basically updating. Good. Okay, also what you should see, and this is kind of coming a bit back to this discussion on why is there no information being sent back. This is also, there's also no information sent in the future, right? If I would be doing this again without my way of composing this one player which just magically updates, I would have to explicitly feedback that information. Yeah.
So here you have essentially Boolean values that are the outputs, which is the correct attested 1 and 2. But then in a different block, you had an input and output that was actually called bool. So I'm a little confused whether this is supposed to be like a label or a type.
Okay, this is basically the question of the scope of the environment, basically. So the reason I call this bool here is I'm just telling out basically me for the reader. I know this is a bool, and I basically know what is happening. Why am I doing this here differently? I'm doing the correct attested because I'm giving it information that I can easier pass it, right? If I would be just saying bool, in that specific context, I might know what it is, but I don't know where the bool is coming from, right? So it's like, you might disagree with my, basically with my nomenclatura or with the way I label things, but for me internally, it was just like, I understand what it actually means, and that's the reason, basically. Yeah. The thing to keep in mind, in a categorical framework, because you have these wires going in, basically bound variables come in, the outgoing wires are basically binding new variables to the output. Right? So in case of the correct attested, I'm binding a value that is the outcome of that operation to that specific correct attested, which means if I'm reusing it, it's bound to it. Okay, other questions? All right, let's continue. So we have the validator's payment, and now we have everything assembled for a one-period game, one-episode game. Okay, this is this beast here, just barely makes it on, not completely. What it basically tells you is this is one episode. I'm now putting everything together. There are certain parameterizations. Ignore them for now. They're just details of, how do I call the players, what is the reward, and what is the fee, and so on. You should really think about it again as a diagram with ingoing and outgoing wires. So the ingoing wires are basically chain old, head of chain from the period -2. Validators map, this is just basically summarizing the information of what the validators have done before. And in principle, you should think about is I keep enough information so that the protocol works. In a simple case here, just one episode. If there would be more episodes, it's just a record type, basically. It would contain more records. Okay, what we then have basically is the proposer moves first. He observes the chain. He outputs a new chain. Keep in mind, this is this again. So he's observing the chain, and then internally he's also at the same time creating the new chain. This is a computation taking place here. Okay, proposer moves, new chain is created, then the validators move as a group. They observe the new chain, they observe the old chain. There's also access to the old information. Validators hash map old, and then they make a decision. They create this basically new map containing the updated information. How did all of these validators actually behave? And they also have the chain updated because when they cast their votes, remember the shape of the blocks are basically an ID and a voting value. All right. The thing to remember, and I'm repeating myself, I know, but it's important to understand what is happening, that the payments basically that happen are happening not for the decisions that are made by the players in that episode, but from the episode before. Or if I would be looking at a more longer horizon, from the episodes before. Good. After this is the main things. The decisions are made by the proposer, by the validators. Now I'm basically doing bookkeeping. I'm determining the head of the chain. I do the validators payment. This is from the past. I also check, I didn't explain this, but this is basically also bookkeeping. I just look at what was the old proposer actually doing. Did he actually do something? And then I'm getting that as an input to the proposer payment again for the period before. Now, the complicating thing here is that I'm targeting a model which itself has a structure that if you just look at the output, chain, new updated, head of chain, and so on, validators hash map, and you look above, you can see there's a pattern basically. The input types here, chain old, head of, I mean, you can't see that, but I'm telling you, the input type, chain old, head of chain, and that here are exactly the output types. Which means now I can take the one episode and just say, okay, maybe I want to run it for 3 episodes. I'm taking the same element and I'm just connecting them. Or I'm not doing that here. If I want to run this as a Markov game, I want to approximate it like I'm running this for a long time, I could just basically use a specific operator we developed that you can embed this stage game, and then I'm repeating it. Yeah, so you're initializing the game, you create a one-stage output that is fed back into the next period, and so you go on. Okay, I'm not doing that here. I want to jump for the last part basically a bit and looking into how do you actually analyze these games? I mentioned before in the slide, what I want to do is I want to illustrate a bit of what is the zooming actually, what is the zooming, how does the zooming work? And you can already see, because I'm focusing on the one episode, I'm actually ignoring any kind of repetition. Clearly, if you care about the overall protocol, at some point you have to think about the dynamics and also longer time periods. But for some questions, it might be relevant to see, is it actually working locally? To give you an example, suppose you're interested in honest behavior by proposer as well as validator. And I'm giving you, I'm initializing this with specific inputs. And I'm testing, in that one period, do the players actually have an incentive to work in that way? And if not, if you find out basically just by zooming in on that context, it's not, well, then you just can put everything else aside. You don't have to think about the dynamics. That's enough. Similarly, if you care about, let's say, vectors of attacks, very often it's enough to focus on specific parts in order to evaluate whether the attack is actually working or not. Question? No. Yes. Maybe. Yeah.
Shall I repeat? Okay. I said in the context of like modeling like the domain of like a game, and like a software team working with like a program like this, if they have to liaison with like the product team, which will have an understanding of like the UX, wouldn't it be easier for them if they want to model attack vectors to just model what the agents could do and then use a genetic algorithm, for example?
Might well be, depends on the context, right? The key thing is here, you have both, basically the best of both worlds. You can just look at the one component, but if that is not the only query you want to do, but you also want to look at the more complicated stuff, you have it as well, right? So nothing, I mean, in principle, what you could do is, actually, you can take this component, interface it to the outside world, run some learning algorithm on top, and that's it. And it would be exactly the same thing. But it will be part of the overall consistent framework. And that's an important thing. If you care about the design, for instance, you want to make sure that everything is somehow consistent, obviously, right? And then it's much easier to say, I'm taking an element which is consistent with the rest and just interface it to the outside world and then simulate it. Clearly, I mean, this is also Haskell. I'm not sure how many people will be using it in that form, right? That's another question that is, I think, lurking in the back. So there are, I mean, this is at the moment, actually to work with that, you don't need that much Haskell because you need to understand the syntax of the engine. And most of what I showed you is inside. Clearly, you need some kind of knowledge of Haskell to work with the outside world. But if that also goes away, it's easy to think of this as basically working as you have a domain-specific language, and that's all you need to know, and you have some operators on top. Then parts of the pain hopefully go away. Okay. Other questions? All right. If not, slide one. Shall we start again? maybe afterwards. Okay. Let's jump a bit into the analysis. Okay. Here's a bit more Haskell pain for you, and even more than average. Namely, we're using something which is kind of what is called arrows. If you don't know what it is, for now you should think about this as I'm defining a strategy for proposer as well as for the validator. What is this basically doing is the following. It's creating a function, and the function tells me I'm observing a chain, and what you want me to do is I'm basically sending an ID. Remember, the proposer observes the chain and decides on which element to build. What the rest is basically saying is this is an honest strategy. It does the following. Determine head. This is a functionality from before. So I'm looking into the chain. I'm looking at what is the head of the chain according to the protocol. If it is, play that game, play that strategy. If not, if there are multiple candidates, randomize. This is happening here basically. And this is done uniformly. And the validator does exactly the same. It's basically super honest as well. He's just looking at what's the head. If the head is a single value, play that. If multiple values, randomize among them. Good. And then basically we kind of encapsulate everything in this. So reminder, this is basically referring to the one episode game. I'm plugging in some variables or some parameters, which you can ignore for now. And then what is the thing that I'm doing? Let me actually do it differently. So I'm analyzing the scenario, and then this is, I should have said this is the interactive way. This is the right-hand side is an interactive session with the Haskell compiler. I'm querying that thing, and what I'm getting out basically is simplistic information, namely, the output just tells me everything is fine. You don't have to worry, go home or go to the pub, everything is working. Now, this is a specific thing, what it actually tells you, and in fact, the protocol is inspired by, by one of the biggest, by Ethereum, basically. You can see that this specific assumption is working. No agent has an incentive to deviate. Okay, nice and clean so far. But now we want to do the following. Now we want to come back to this picture here. I said before that, let's suppose in the past period, there's a guy who's actually not so nice, and he's deciding not to propose. He's waiting. At that moment, at some point, after some time threshold, the next proposer, which is the lower one here, basically observes the chain, steps in. He wants to be nice, he's honest, proposes a new head. And at that moment, before the attesters can actually be active, the old proposer steps in and just basically proposes his own head of the chain. Okay, there are various ways of doing this. I could just model explicitly the attack game, and it has actually merit to do that. But here's an alternative way you can do it. And this is, I'm referring to the zooming in that I want to illustrate. I've created another version here, which is doing this one episode attack, which is doing a simple trick. Namely, I'm introducing an additional variable. Because I'm just focused on this one period, I can do that. It's easy. I just add, which is the chain manipulated. All the rest is the same. The proposer observes the old chain, so he's basically still operating under the information from the past. And then what happens is this line block is added. I'm merging the two proposed heads into one chain, so then I have really a fork. And then what is happening, the validators are observing the forked version. So they have to deal with the problem, basically. Right? Now, is this the only way to do it? No, you have multiple ways of doing it. But this is, this is part of what the modeler has to decide. How can this be done in an easy and accessible way? Another way to do this, and on one branch we actually do this, is explicitly keeping track of time, and basically look at a timing game, right? So that time passes, and then the proposer from the first period can, until a certain point, act. The problem is that until a certain threshold, all the other players don't know whether the other guy moved or just they haven't received the signal yet. But this is much more evolved. Here, I'm just cutting into the thing and I'm just focusing on that one aspect that I care about. Namely, what do the validators actually do? Okay, let's jump to this. Attack. Okay, strategy proposer is the same. Then we have what I call the strategy validator random. It's also the same from before. I add two new strategies for validators. One is strategy validator 4 and validator 5. This is something very simple, namely in case of a tie when there are multiple things, I'm just taking here by hand, I'm just taking the fourth element. And for that specific example, I'm just specializing it for that specific thing because it's enough, but you could also easily extend it to a more general version. In other words, when there are multiple candidates, I'm just deterministically choosing one of the elements. Right? And I'm doing the same for 5, but just on the other element. Okay, now I have several scenarios. I have scenario 4 and 5, which is just the same proposer strategy as before, honest, in the manipulated chain, and then the validators are just deterministically voting for ID 4 in case of a tie, or alternatively 5. And lastly, the random is basically, I'm just taking the element, so the honest behavior from before, namely if there is a tie, I'm just randomizing. Which obviously is also debatable whether this is a good idea, but for illustration purposes, that's enough. Okay, let me run through 4. You can see this is nice. This is also nice. This is an equilibrium, and 5 as well. Okay, so far this looks like pretty useless because everything is in equilibrium. But in fact, what it tells you is that subtly we have two equilibria at the same time, and both are kind of either we go with the honest proposer, namely the one who proposed the 4, or we actually go with the 5, which tells you this is not in the interest of the protocol. This one of them should not be in equilibrium. And you see even more, if I'm sticking to the actual behavior of introducing the possibility of random, basically just honestly saying I don't know when I'm randomizing, you get different information, and this is the alternative, namely the system recognizes one of the agents has a deviation. The formatting is horrible, but basically focus on the first part, the player with the name A21 has a deviating property. Its optimal payoff is 2, current payoff is 1. What's the optimal action he should choose is move 1. Why is this the case? You can easily imagine, because basically these players try to coordinate, and if they are diverging, the protocol will punish them. So they actually are better off voting for both, coordinating on the wrong or on the manipulated head of the chain instead of sticking to their honest strategy. So at that moment, you see things fall apart with that relatively simple model. And again, this kind of, it's a simple illustration here, but that kind of structure was actually a motivation from a realistic attack. Good, let me close with one more thing. And this is then more or less the end with kind of some remarks. This is the interactive version. I said before, you can also think about this as being part of a system. So you can basically also run the testing in parallel or as an alternative. So if you do this, basically what will happen is you have some kind of specification test. This includes the equilibria, but it can also be the parts. You know, is the staking protocol working in the right way? And then Haskell is actually quite nice on that end, because it can create a lot of very well-structured arbitrary examples that you care about. And then you will see at the end, hopefully something green like this, which generated, in that case, I think 100 different starting points for the chain, evaluated them, and you get some result. Yeah. And you can see this is basically, you can extend this in all kinds of versions. It can be either on the behavioral level, really thinking about equilibrium, that would be the first test, or if you go down, really just the components. Okay, questions before I conclude? Let me conclude. On 2 levels. First, a bit more concretely, what is the next steps for this engine? And then circling back to where we actually started. So how is this connected to the rest of category theory, or maybe more precisely applied category theory? So one of the things, and some of actually formal verification people are here, one project that we have is, I mentioned this, we want to have more pipeline from, let's say, starting from EVM code into actual open games representation. A lot of work has already been done that we can dock on, and one project is basically to kind of extend this towards the open games framework, so that if you can start with some smart contracts, you basically get an open games representation, and then you can start querying them either automatically or with your maybe you have some ideas of what you want to query in a manual way, or you have some more bigger analysis tools on top. The analytics we have so far, we are extending them permanently. We are also, going into different applications and think about how they, what specific analytics are relevant there. So outside of staking. And I should mention this before, which is actually an important thing. The engine itself, the version that you see here is basically built on theory version, outdated time -3 or so. There have been 3 more iterations, and one of the tasks in the next weeks and months will be basically an update of the engine. The theory itself is also continuously developed. Okay, lastly, compositionality. That was the starting point. You have seen one instance of why compositionality might be useful in the context of open games. What is interesting about this specific example is that when we started out, there is this basic question that Fabrizio raised in the initial slide, or in the initial beginning of his presentation, namely how do systems compose. In the game theory, or in the game theory setting, we have a relatively clear answer. And what was interesting was, in the beginning, the implementation and the way we did it categorically is not at all, doesn't resemble at all the way it looks right now. Because at the beginning, we had a very different way. What we realized actually is the connection to lenses in the categorical framework. What we also realized was actually realizing that the existing deterministic lenses are not enough. And this is quite obvious because games need randomness, right? You need to deal with non-deterministic moves. That actually led also to innovations on the side of the optics implementation. And that itself, Fabrizio alluded to that, is itself now kind of in an area which is almost exploding in all kinds of directions and making connections and extending this framework. This is one of the things which is quite nice actually about all of this work, that it's tying back into other fields within the categorical framework. And examples of that are control theory, reinforcement learning, active inference, others to be developed. And the abstraction here really enables you to see that these patterns are, or that these different instances are actually related to common patterns. And lastly, what is more, you can also make cross combinations. One of the interesting ones is actually thinking about games and learning, right? Which is not new itself, but if you see it in that form and you have this new pattern, it's quite info. I find it quite insightful and quite useful actually to see it in that form. Good. Thank you very much. Questions? Yeah. Or to me or to Fabrizio. Maybe you want to.
Oh, so I'm wondering if we can talk about like a real world attack example and how that would come into such a system. And in particular, I guess on my mind is the Mango attack from a couple days ago, where it was essentially an Oracle exploit. And it seems to me like an Oracle would be inherently outside of a system that you're modeling this way, or is that an incorrect assumption?
Sorry, let me go back here. Just if you think about here, if you think about this, X doesn't have to come from the world. It's from the game itself, right? It can be something from the outside perspective. So I can interface that system with something which is drawn from an outside. Could be from a database or whatever it actually is where it's coming from. Yeah, depending on how I deploy this, it could be continuously updated, and I'm running that basically on a permanent basis. So this is clearly possible. You can also parameterize games. I'm not sure maybe you remember this, or I'll just maybe go there. If you look something like this one episode attack, there are a couple of parameters which are actually exogenous. They are not part of the internal structure. I can make them endogenous, querying them, but I can also just say they're coming from the outside, and I'm fixing them, like the names of the players or feedbacks or fees and rewards. Yeah.
Can you establish bounds on those parameters?
It depends on what you mean with bounds. First of all, keep in mind there is structure to it because they have to be typed, right? So if they have the wrong type, they will not work. What exactly do you mean by bounds in the sense of values, or?
So yeah, I don't mean like a type bound. I mean value bounds.
Well, again, you have limitations in the sense if you're working within the Haskell world, you clearly have boundaries for certain types that you can use. There are also, of course, the question of the computational complexity at some point, right? I haven't talked about this because this is also part of active research. So far, I'm using compositionality exclusively on the level of composing the representation. There are results that show that computing equilibria, for instance, is very hard, and we will not break these results. But in the practice of actually computing concrete games, you might be able to leverage also the compositionality, right? Because some component here might be computed, but it might be independent of that, and then you can compute. Or some component here might compute, but it will only affect another component. Sure, please.
Another thing to keep in mind is that, as Philip said, you can have that a game can just have a function as internals, or it can have strategies. So in the case of an oracle, you can either treat it as a parameter that basically comes from the outside world, or you can model it as a stupid function that has no agency whatsoever, or you can model it as, I don't know, a protocol that has its own set of economic incentives to work in the right way. I guess that would be the case of like the centralized oracles where, people are incentivized to not to lie and whatever. The cool thing about this is that then you can start from a scenario where the oracle is honest. The very cool thing that practice teaches us is that usually when people design a protocol, they have already an intuitive notion of what is the equilibrium where everyone is honest. So you say, okay, you test that you have an equilibrium, and now you can basically start bribing the oracle. So you can start basically, adding incentives to the oracle to lie. And one thing that you can do very efficiently computationally is finding a bound that is basically the cost of breaking your equilibrium. So you say, how much do I have to bribe the oracle to break the equilibrium? And then this is super useful because now you can find parameters. And since you are starting from equilibrium that you already knew, you don't have to do equilibrium search. It's just equilibrium checking. You just like linearly increment this parameter and you say, okay, this is how much we are protected. And then, yeah, that would be a sort of bound between your model of how expensive would be to fuck it up, basically.
Oh, hi. I have a few questions because I've been really listening so intently, and I've written some things down, so it's okay. The first one was, could you perhaps optimize a compiler by modeling it with category theory and with your tools?
Maybe I'll save it.
Oh, sorry. Was that kind of hard to understand? Could you perhaps model a compiler and optimize a compiler using your tools and with category theory?
Okay.
Is that hard to understand?
There are actually people doing this here. I think at least trying. But honestly, this is definitely outside of my expertise. I can't say that.
You can probably check the research of this professor called Dan Gika that is using category theory to do compiler optimization. So yeah, that would be probably the closest thing.
Okay.
And that's exactly where my knowledge of it ends.
Oh, thanks. And then another question, and I'm going to speed run it so nobody gets offended that we're taking a long time. Could you model perhaps an iterated prisoner's dilemma with a variable number of agents and rounds with your tool? Very cool. And will you ever release a function annotated sort of preprocessor language that's maybe syntax agnostic or something that you could add into other code bases that aren't like Haskell based in the future?
Maybe.
Very cool. Okay.
Other questions? Other questions? Thanks for coming.
Can I just put it here? Cool.
Shall we wait maybe?
Yeah, we can wait like 2 or 3 more minutes if you want. Sure. We can like very casually get started. Cool. Welcome everyone. I think this is one of the first ever workshops at Devcon, featuring a really new, exciting space that has evolved over the past, really only over the past year, called DeSci. And DeSci is short for decentralized science. And so the goal today is really, the title of the talk is Smart Contracts and Petri Dishes, essentially merging these two fields together. And then with a goal to who everyone is here today to kind of look at beginning to create a shared technical infrastructure roadmap for what is actually required to make DeSci a success. Cool, so we still have some people coming in. Maybe a few words about myself. Hi everyone, my name is Paul Kohlhaas. I'm the CEO and co-founder of a company and ecosystem protocol called Molecule. And I had the amazing opportunity last year to work with a great group of people to launch one of the first DeSci-centric research organizations called VitaDAO. Maybe to start with that, like maybe a show of hands, who's heard of VitaDAO? Okay, so almost pretty much everyone. It was a little bit hard for me to gauge the audience of this of the talk today, just because there's obviously a lot of well, developers at Devcon. It's a developer-centric conference, and this whole concept of DeSci is still pretty nascent. Whoop. Okay. Back. Cool. Maybe I can share a few words just about myself. I actually don't have a background in science, but rather in economics traditionally. However, science and specifically like biotech has been a huge personal hobby of mine since my teenagers. I spent a lot of time in online biohacking communities as a teenager. And some of you may be familiar with these. There's all of these different subreddits focused on nootropics, for example, or biohacking. And so as a teenager, I spent kind of time in these online communities that were, for example, diabetics, and that were looking at alternative ways of accessing insulin. As many of you probably know, insulin prices in the United States have skyrocketed over the past decade. And so these communities were looking at ways of producing their own insulin kind of in a garage, which sounds super risky, but actually often people are, our current healthcare system really like underserves certain patient population. Similar cases in, for example, in different HIV communities that were kind of collaborating online to develop their own open source gene therapies. Or in other cases, you have communities of psychedelic researchers and enthusiasts that are kind of exploring hundreds of different novel psychedelic compounds. So what happened in these communities, someone would say, hey, here's an interesting chemical structure. I think it could do this, this, and this in the human body. Has someone tested this? And then someone else would say, yeah, I tried it. It did this and this and this. And then essentially people, some of you might know this as trip reports. It's essentially a form of like very anecdotal data collection. But I found this form of like open source drug development really, really fascinating. And at the same time, then I began looking at like the larger macroeconomic landscape of pharma. And because I started asking myself, well, why are these people online in the first place, actually, in many cases, engaging in very dangerous experimental behavior with their own bodies? And it's often out of sheer necessity, because either through lack of access, or because certain medications and therapeutics are fundamentally overpriced. And then I went on and studied economics. And during my time studying economics, I got an interest in trading biotech stocks. And so a biotech stock typically trades around kind of the success of one of the core assets that is being developed. Doing okay? One of the core assets that are being developed. And so if positive data emerges about one of these assets, typically the price goes up. And if negative data emerges, the price goes down. But with yeah, okay, we might have to plug it in then, but I'm sure it's fine. And so within biotech companies, this data is extremely well guarded. It's typically only released like every 2 or 3 months. Typically only released every 2 or 3 months. And when the data is released, positive and negative, the stock typically does then a 5x, or it does minus 80% in a day, which is actually really inefficient if we think about how markets work. It's like this fundamental information asymmetry. But furthermore, most biotech companies actually only have an incentive to share positive data. So a biotech company could be generating 100 studies on a specific compound, and 2 of them were positive, and let's say 8 of them were inconclusive, and 90 of them were negative. They would only show the 2 that are positive, because you typically wouldn't want that other people to know that what you're developing actually isn't working. But in the context of science, this is extremely inefficient. So in science today, there's this problem called the reproducibility crisis, that it's actually quite hard to reproduce other people's data sets that have been generated. Should I just keep going? Okay. And so as I began looking into these companies, it reminded me of my experience as a teenager in being in these much more open online shared communities where people just kind of live share data in real time. And I thought to myself, hey, there's actually there's something there. On the one side, we have a pharmaceutical system that's incredibly inefficient, and on the other side, we have kind of these online open source communities of patients, researchers gathering that could potentially be much more inefficient. And a lot of this reminded me of the way that open source software is done, which is, I think, a really big topic in the crypto space and in the Ethereum space. And so in open source software, you have to remember that really up until the 80s and 90s, open source was not a thing. And actually, famously, Microsoft called open source software a cancer many, many years, actually actively tried to sue the Linux Foundation. And pharma today, or like biotech, and actually much of science still works like open source in the 80s and 90s. You have to imagine like pharma companies are like giant IBMs that are trying to develop everything closed source, and effectively buying a drug from a pharmacy that is kind of licensed through a very, very long, complex closed source process is similar to like in the 90s buying a Windows CD and then going home and writing in your CD key. I don't know how many of you remember doing that, and today that would be unthinkable, right? Be unthinkable to still go into a physical store, buy a CD that is protected, and then enter that CD key. But that's essentially where much of the scientific system is still in today. Still not? We'll get there. And so as I began getting more and more into this, I kind of realized that there's a fundamental opportunity here to create a much more open and shared system through the use of Web3 technologies. Because the fundamental difference often in science and in software is that science is in meat space, it exists in the real world. And so you can't just as easily replicate it as you can in other industries. Sorry, the presentation is not online, it's in here. Are we okay? Okay, no, this is not working anymore. Okay, cool. So what are we here to do today? Oh God. Cool. Day 3 of a conference, like technical difficulties are built in. So here today we're going to look at what are the problems, definition, and goals of the DeSci community and space as a whole. We're going to look a little bit about what we've accomplished so far, specifically by going into one specific use case. We want to look at where the whole space is going and the different Lego blocks that are emerging. And then essentially quickly move into workshop sessions and different breakout groups to explore specific building blocks that have emerged in the DeSci space. So DeSci has actually only existed for around 1 year. It's a very, very new phenomenon. And the goal for this workshop today is also to essentially help define a future roadmap of where the space is going and how we can build technical solutions to essentially enable the next generation of DeSci developers to build permissionless open systems that can really serve future generations. I asked briefly before who knows about VitaDAO, but it would be really interesting actually to know who maybe in the audience actually has a scientific background. Okay, it's actually much more people than expected. Can I maybe ask you what your background is? Social scientist. Okay, cool. And there was a hand up over there. Dentistry. Cool. Anyone else? Yeah? Medicine. Okay, perfect. And there's this, yeah? Can you say that again? Oh, preclinical research. Okay, that's our jam. Also doctor? Used to be a doctor. Now a DSci dev. Gavin? Anatomy and cell biology. Cool. Awesome. What a great crowd. It's just going to keep haunting me. So even though the space has only existed for a year, we've seen almost a Cambrian explosion of DeSci projects. And there's a lot of tinkering and like ongoing development. Big shout out to a team called Ultra Rare Bio. If you want to follow them for like updates around the DeSci space, this overview was actually created I think in May. So I think by now already there's a whole range of new projects, DAOs, and systems that have emerged that are actually not on here. But just to see how quickly the space is moving. And as any kind of new industry emerges, one of the most important things is to avoid redundancy. And maybe some of you remember how the whole DeFi space and DeFi community came into being. It's really through building open interoperable Lego blocks that we can all build on together. And so the biggest thing that you actually want to avoid in the early development of a space like this is, redundancy, and you want to enable permissionless interoperability. Permissionless, for example, means not introducing friction in the use of services. Permissionless means building in an open source way. Permissionless means creating events like this for communities to come together and share, rather than building in silos. Because now that in building out the DeSci space, we should really ensure that we're not kind of making the same mistakes as the industries and people that came before us. And it's tempting to do so. And it's tempting to do so because actually creating friction between systems is the way that most industries actually capture value today. It's by introducing middlemen. And so I represent an organization called Molecule, and this is also something that's really important to us. Like, how can we enable open permissionless systems? How can we enable other people to build together, rather than introducing frictions in systems? Yes, cool. So we have a big opportunity here today to define the roadmap for future builders, and create an open collaborative technical infrastructure in the same way that Ethereum enabled an open collaborative infrastructure. And so DeSci will be most successful, in my view, if really enabled as these interoperable permissionless Lego blocks that we can all put together and build on. So now the question for today's workshop is, what Lego blocks do we need for which types of DeSci applications? Pretty simple. And if we manage to build those Lego blocks in the right way, then I already think in 2 years, we won't have 80 organizations, but we'll probably have like 2,000. This is essentially what happened in the Web3 space when DeFi came around. Probably in 2018, 19, I remember there being like maybe 2, 3, 4, 5 DeFi applications. They were extremely early. But if some of you, for example, remember MakerDAO, who then launched, or not remember, but know MakerDAO, who launched CDPs and DAI. So DAI essentially was a building block that enabled the emergence of a huge amount of DeFi applications. And that's one way to think. So science today is full of problems. Funding in science is incredibly difficult. It's highly competitive. It's very asymmetrically distributed. Often only goes to the best universities. It goes to scientists that have a lot of academic pedigree. It's very political to get funded. And there's a really interesting insight that actually most scientists today would change their topics or their field if funding was not a concern. So almost like scientists today have to be extremely opportunistic They can't often actually work on what they want to work on. They can't actually work on their theses. They often have to just chase the money. So one of the first researchers that we worked with at Molecule, and also one of the first researchers to get funded through VitaDAO, gave us a famous quote, which was that he spends 80% of his time fundraising and 20% of the time doing the research. And so fundraising in this context actually means getting grants from different institutions. Then the second thing is replication. I gave this example earlier with biotech companies, but much of science today is not reproducible. So someone will say, hey, here's a study, I got the following outputs, and then you'll try to run the same experiments and not get the same outputs. So how do we get there? The further thing is competition. So science today has become hyper competitive, and that really creates perverse incentive. Often you have competition for the same grants, and then there's an issue with essentially like scooping each other's work. So it's also, we don't have a system yet today where there's a lot of scientific integrity actually between different scientists. And then a last problem is that science today is still really inaccessible. Much of important scientific literature lives really behind paywalls. It's not open source. And science is often, to many people, still not very accessible. If we think that actually before the whole NFT art craze, I never felt that art was very accessible to me. It's like quite a complex actually process to go into a gallery to figure out what you like. Art wasn't very accessible for NFTs. But so I think Web3 actually has the potential to make science much more accessible to the broader population. For example, if you have a specific disease and you're really interested in maybe funding therapeutics in that area or actually getting much deeper involved in it, it's not that easy for you today. And a lot of these problems that we actually face in the scientific community are the same problems that we have in other industries today. They stem from centralizing authorities. So funding, for example, is largely distributed through governments, or it's largely distributed through very powerful, large private corporations. And these centralizing authorities essentially affect each part of the scientific value flow. Another example is the publishing houses that essentially control much of how what is actually published. So if a publisher doesn't want to publish your research, it may just mean that it actually never gets disseminated to a much broader audience. And so this is what we have to start changing. Move away from these centralizing authorities that actually govern access to science and govern truth, and move into a much more open scientific system. So the question is, and maybe one addition here. How many of you are familiar with the open science movement? Does anyone want to give a definition of open science? Yeah?
Similar to most of the things that you've heard so far, right? They're looking for ways to lower barriers. I remember talking to the Center for Open Science who was working on a replication challenge. And basically trying to find a lot of, I guess you would say, Web2 ways of addressing these problems.
And why do you think open science today, do you think it has succeeded?
It doesn't seem like it's gone as fast as you would have hoped that it'd go, and I think that they don't really have that much money.
Yeah. So funding, huge problem. And funding is often based on incentives. What are the incentives for open science today? Anyone? Goodwill, yeah. Let's build a better planet. Like, yay. Unfortunately, like goodwill doesn't pay, and unfortunately, we live in a very capitalistic and profit-oriented system. So actually, the most interesting application of Web3, I think, to date has really been creating incentive machines that fundamentally alter people's behavior. And so I think a fundamental thesis for us was that the reason open science has not succeeded is because there's no incentives around it. And taking this example that we had earlier with a biotech company that actually only has incentives to publish positive data but not the negative, if we now had open public markets, as we do in the crypto space, for example, you can make an analogy that if I find a bug in a crypto network that's like open source research, so actually crypto networks are relatively open source. So if I discover a bug, that is actually now valuable negative information. So I could be like, this crypto network is flawed, and now I have two options. I could hack it and stand to benefit from that, and through that, actually, I'm revealing that this code was fundamentally flawed, which is actually valuable to society. It's like was actually flawed. Or I could also just ping the team and tell them, hey guys, your code is buggy. You should fix this ASAP. Now imagine if we had the same thing for medicine. If there was an incentive to now create both positive and negative data about an asset, I could be like, hey, there's a drug here that's in development. There's a lot of hype around it, but actually, I as a scientist have a thesis that this drug might actually be toxic in humans in this use case, and now I have an incentive to release that data or actually to create it. And so all of these incentives actually for open science are missing today, and that's what we're going to build together. So what if science is decentralized? Maybe first let's ask the question of why is decentralization so important? In decentralized system, users can participate in a trustless system. So you don't need to trust a middleman. I don't need to trust a publishing house, for example. I can trust other participants in the system. It lowers the risk of systemic failures. I don't know if have some of you recently heard about the big Alzheimer's trial, or Benji, can you maybe quickly, or anyone from the audience? Yeah.
I mean, there's been this whole issue around like the amyloid beta hypothesis in Alzheimer's, and there's been a lot of, I think, career academics who have built their reputation and their laboratories and their funding around Alzheimer's and this particular thesis, and I think they managed to, through political force, lobbying, through the power of the Alzheimer's as an institution and amyloid beta related institution, push through a drug through the approval process that just doesn't work.
Yeah, and it got extremely far just based on a fundamentally flawed hypothesis. And that fundamentally flawed hypothesis was promoted by centralizing authorities. Yeah, and so actually many drugs, I think not just one drug, but many drugs were actually started being developed just based on that thesis.
Yes, the entire field of Alzheimer's is built around this.
Yeah. Another one is just like avoiding censorship resistance. Avoiding censorship resistance fosters a much more open culture. And the last point is really enabling global collaboration. So what is the why, what, and how of DeSci? So why are we doing this? We're doing this to build an open science movement and to make science more collaborative and make it accessible and open to everyone. Like if you're a promising scientist in Nairobi, you should have the same opportunities and chances as a promising scientist at Harvard. Today, that is not the case. In the same way that if you're a developer on Ethereum, I don't really care if you're in Nairobi or in Cape Town or in Boston. It doesn't make a difference. The same thing should apply for science. What are we doing? We're building a global open alternative to the current scientific system that anyone can participate in. So equal access to anyone, equal opportunity. If you have a promising, actually, Vincent, I love that example that you typically give around getting funded by a DAO as a young researcher. You could be a 16-year-old whiz kid sitting somewhere having a great idea, looking for funding. In the current scientific system, you'd never get funding. They have zero credibility, zero trust to actually receive funding from a reputable institution. But with these DAOs that are emerging, like age doesn't really matter anymore. What matters are your ideas, your integrity, and the data that you can produce. And how are we doing this? So Web3 fundamentally as a technology that enables scientists to raise funding, to run experiments, to share data, and distributes their insights much more openly. So what DeSci verticals have emerged? Because the scientific field is extremely broad. So the area that DeSci is currently targeting and attempting to disrupt, one is funding of data, IP, and impact, which is a huge field. So what we're essentially trying to enable is faster and more democratic funding mechanisms that enable communities to form and govern impact or novel forms of IP. Another big vertical is publishing. So having transparent, open access publishing with aligned incentives for all participants. Having incentivized peer review systems, for example. A third one is DAOs and research governance over these research assets. So DAOs present an entirely new way of organizing researcher or patient involvement and, for example, clinical trials. This has never been possible before. If you're a patient today, you have absolutely no choice what lands, what comes onto the market. You have no choice over the price. It might be a life-saving medicine that you need every day to survive. You have no influence on the price, on the access, whether it is actually the right medication. Yeah. And neither do researchers. So we have this very long drug development process, but we've removed the core stakeholders from that process. And another one is identity and reputation systems for academic credentialing. So how do we actually trust scientists in these different systems? Maybe I want to ask into the audience. So these are kind of DeSci verticals that we've seen emerge across the field. Do you feel that anything is actually missing there? Yeah?
Like data and stakeholder management.
Yeah. How would you just, like, in what use case?
So largest use cases like, obviously like a lot of medical data as well as like patient data, very secure.
Yeah.
There are a lot of like kind of ways you can facilitate better interoperable collaboration between the industry by, facilitating like permissionless transfer of basic data.
Yeah, really good point. Yeah?
I feel like also the scientific process, like the collection of data, the hypothesis building, the experimentation, the redoing the experiment, all the things that sort of happen in the lab.
Yeah. So what we're going to do, like, what? Yes.
Oh, I was going to say I don't see too much developments that address replication.
Addressing like the replication or reproducibility of data. That's actually a good point. Well, in publishing actually, but we should add it. That's actually let's note that as a point for the workshop later. It would actually be awesome to like not just consider these areas, but really map out holistically what all the different verticals are. I want to go a little bit into just one of the verticals, which we're working on specifically, but we also don't have to spend too much time on it. There's a lot of other talks that I've given in the past where I kind of go into this. But of all of these areas, where we're currently seeing the most traction is funding and IP. Because it's relatively simple today, I think, to facilitate funding use cases through Web3 technology. I think it's still much harder, for example, to facilitate identity or reputation systems through Web3. So what are now the sub-verticals in funding and IP? So we have retroactive public goods funding. Some of you may have participated or even benefited from the recent DeSci Gitcoin round. So that was a great example of that. The other one is quadratic funding, having a fair, more democratic way to balance, actually allocate funding to projects. A third one is having DAOs and tokenized incentive structures, such as VitaDAO. And a fourth one are IP NFTs, which are a new form of on-chain native IP and data ownership. So actually for each of these verticals as well, something that we could do later, we could start defining all of the different sub-areas in that vertical. I want to quickly maybe ask a question into the audience. So do you want me to go deep into one of these verticals now, or should we actually leave it much more open? Go deep? Okay. Let's go deep. My goal, like, the only thing I want to avoid is that we prime it too much about this one use case because there's so many other use cases. But what is interesting about looking at funding an IP and specifically what we as Molecule have developed, which is the IP NFT, is that it's already very applicable and that's theoretic. But so if we look at one of the fundamental problem spaces of how does innovation and biotech research actually work today. So you have innovation emerging at the fringes of an organization. And then in most organizations, innovation is driven through a funnel. And then essentially you curate ideas as they emerge in systems, and eventually something goes into a market. So you have idea generation, you define the project, and it moves through this funnel. And you can actually map the same process to the entire drug development pipeline. So this process today can take, like industry averages, to take up to 10 years to actually develop a new drug and to drive it through all these cycles. But now one of the biggest problems with that is that like cancer is a global phenomenon, yet every company developing cancer therapeutics is doing it in a silo by themselves. And you could ask, wait, wouldn't it be much more efficient if this was done as an open and public funnel? imagine instead of every company having this funnel by themselves, and like we're essentially investing so many resources on a global scale to try to achieve the same thing. Wouldn't it be much more efficient if we had a giant open funnel? And this is essentially what we could build with Web3. And you can imagine each of these little dots are now individual research projects or individual assets driving through this funnel. And why is it that way? The reason actually behind that everyone is doing their own thing is because we have something that called the patent system that fundamentally uses IP. But patents are really legacy legal physical assets. Patents are literally often still in most organizations boxes of papers, which if you think we're in 2022 is absolutely mind-boggling. It's somewhat ridiculous. We're using an extremely bureaucratic and outdated IP system that makes IP very hard to transact. It's often much too expensive to claim IP in the early stages. It's really hard to get IP out of a university. The patent filing system takes ages. And so what happens actually often that a lot of IP or a lot of promising projects that are in here never see the light of day. And it's not because they're actually not interesting projects. It's actually because the entire innovation system that we built around them is really inefficient. And so there's something called the valley of death, which typically happens here. So actually most of the world's innovation never even enters further stages. Which is, if we think about scientific progress, it's really a shame. It's like there's so much good science that never sees the light of day. And if we think about data and software today is completely virtual. But if you think back 40 years ago, companies literally still had like entire floors with filing cabinets, employing hundreds of people to sort through those data sets. This is an example I really like using. The screenshot was taken about a week ago. This is the current state of the art of the US PTO patent search system. That's literally how it looks in 2022. And the only alternatives to this system are paying really expensive like legal software to essentially search and discover patents. So if I was someone who was like, hey, let me look for interesting cancer research that's been patented, and I'm like trying to find something in here, like this is what I'm supposed to use from the government. Of course, there's better systems than this, but they're typically proprietary. I'd have to pay for them. Yeah. So this is what we want to get away from. Yeah. Yeah. What do you think?
Sure. It looks like a lot of the data is like pretty well developed. It seems like this is like
Mm-hmm. I mean, I think the first thing I would say is it's extremely static. It's impossible for me to actually contact the researcher or the institute that's working on it. It's hard for me to see what's done or if anything has been successful around it. Yeah. No.
I mean, maybe the differentiation here is a very low resolution, like high volume database that the U.S. government is maintaining, and then obviously there's many other people building like interfaces that go over this. So I think this speaks more to the problem about just like fundamental intransparency than the need to like meaningfully extract reason or meaning from a lot of this data.
Mm.
I think also like the scientific data that underlies the IP is also missing from here.
Yeah.
If you go through a scientific patent, usually they'll have some like black and white like line graphs, but you can never like audit the underlying data, understand how experiments were run. More like a scientific paper like that.
I have no idea if someone's actively working on this. I also, yeah, and actually, if someone has patented it, it almost disincentivizes me to work on it because, like, fundamentally, for example, if let's say I'm a researcher at a university and I look at a new interesting molecule that I've kind of come across, and I search whether it's been patented, and I realize it's been patented, like I don't have an incentive to now work on it because I could literally get sued for engaging in that research. So IP monopolies really kill innovation at large, and they also lead to much higher drug prices. So what we have a system today that rather than the best science winning, we really have revenue drivers that dominate medicine. So at Molecule, we've really spent almost the past 4 years asking ourselves what could a better system look like for this, and trying to build towards an open market for IP. So trying to reimagine the system and making it much more open and transparent. And one fundamental thesis that we have is that most of the world's potential scientific talent remains untapped. And so, for example, if we think through what happened in the NFT market for artists and now for music fundamentally has changed how we interact with art and fundamentally has enabled a different creator economy for artists. And so what if we enable a creator economy for scientists to really helping the best innovation across the world rise to the top? So we are building towards an open, transparent marketplace for research funding that is underpinned by a new DeSci primitive. And now the question is really, how do we bring legal IP and data into Web3? And one kind of DeSci Lego block that we've started building on is essentially a concept called an IP NFT. So what is an IP NFT? IP NFT is first, it's a legal contract and a real-world license that is tied to research or data. So it's a legal contract that now takes IP out of an organization or out of a university and attaches that to an NFT. The second is it has a storage layer. So you have a decentralized permanent data storage with public and private data repos. So almost now imagine this NFT is like, simplest way of saying it is like, has like a decentralized Google Drive attached to it, where the owner can now provide read and write permissions to anyone that wants that. It's transactable in the same way that an NFT is transactable. It's discoverable through public metadata around that NFT. So I can now publicly on-chain start searching through the metadata of these assets. And then fundamentally, and I think this is the most exciting part, the IP now becomes programmable and composable. That means you have governance, you have fractionalization. If you're interested in actually IP NFT fractionalization, we have someone from our legal team here, we've developed a new framework that is called the Friends framework. Because fundamentally what you need to avoid is making any of these assets like securities, because then they don't become transactable in Web3 and they don't become Lego blocks, at least for now. You can have programmatic royalties or pay for success models. We also have someone here from the crowdfunding cures team, which pay for success models represent a really new, fascinating way to essentially do repurposing of drugs. What does this kind of look like from an on-chain perspective? So you have a real legal contract that's mapped onto a smart contract that then maps to metadata that is stored in Arweave, and then you have encrypted and private patent data that now fundamentally protects the IP. And this latter part you can open up, you can open source it, or you can keep it private. One big thing that we realize, it's actually really hard to do open science in a field like biotech, because we began working with an organization called the Open Source Pharma Foundation. This was in 2019, and essentially what they do is they create public GitHub repos for open source drug development that they're doing. So they were researching malaria, open source mycetoma, essentially different tropical diseases that are really underserved. And so what they realized though in doing that, as soon as you publish, for example, the structure of a new molecule in a GitHub repo, you open source it, and you say this could be used as a malaria drug, it fundamentally forever becomes unpatentable. And now they were working with the Bill and Melinda Gates Foundation, for example, and then realized about doing that the Gates Foundation essentially said, we'll never be able to fund any of your malaria drugs, even if they work, because they become unpatentable. And because the problem is, if you don't have any patents around drugs, you can't essentially get the asset through late-stage clinical development. No one is going to come and pay, let's say, the $100 million plus that you need for like a stage 2 or stage 3 clinical trial, which is a big shame. It's just how the system works today. Today, it's fundamentally impossible to do open source drug development. However, I think as DAOs and communities, for example, get much larger, you can actually move more into impact-driven development. So to close the session, IP NFTs, in our view, are really a first composable Web3 Lego block. So they can be transacted like NFTs and applied for funding. DAOs can now build portfolios of research of IP NFTs. So we have this new phenomenon, bio DAOs that have been emerging, which are DAOs that are now focused on different therapeutic areas. So since VitaDAO emerged, we now have a DAO focusing on neuroscience. There's a DAO focusing on psychedelic research. There's a DAO focusing on women's reproductive health. There's a DAO focusing on hair loss. There's another DAO focusing on synthetic biology. And all of these DAOs can now use the IP NFT as a basic building block to build an on-chain portfolio of IP. NFTs can also be fractionalized, and be inserted as DeSci Lego blocks. You could imagine an NFT, an IP NFT being fractionalized, and then those fractions going into different on-chain liquidity pools. There's fascinating new mechanisms where the fees that are now being generated through these liquidity pools can actually be used to fund the research as well. So everything that has been built in DeFi for the past 3 years, can now also be cross-applied to DeSci. For example, also data access can now be granted via multi-signature wallets. And we're really only beginning to scratch the surface of what is possible here. One of our core goals in Molecule for the next 3 months, is actually fully open sourcing this first version of the IP NFT protocol to enable anyone to start playing around with it and essentially just tinkering around with it, because we don't actually know yet how many applications this can be used for. So what are the basic DeSci Web3 Lego blocks? So I think we're looking at transaction layers, we're looking at data storage layers, we're looking at compute and execution layers, and then finally we have identity layers or reputation layers. The IP NFT, for example, combines what I would say is a transaction layer and a data storage layer, but it doesn't actually touch any of the other layers yet. And so now we're slowly moving into the workshop part. I think Tyler just left. So the goals for this workshop today is essentially now to look at both what Lego blocks do we have and to look at how are they matched with different DeSci verticals. So we have different Lego blocks that are emerging in Web3. How do we map them into these DeSci verticals to solve fundamental problems in Web3? So the goal of this workshop will be to really explore how decentralized science can improve the process of funding, doing and disseminating science through the use of decentralized systems. So now we're going to look at each of these different elements and yeah, essentially start workshopping them. Vincent? Yeah? So the flow of the workshop will be that we now have a breakout session for about 40 minutes where we can gather around these different topics. We also have multiple members from leading organizations from these different areas in the room with us today. We can then do like breakout pitches where people that have now formed through these different teams can essentially pitch their ideas, and then we can all discuss them together. Vincent?
Yeah, so maybe like basically we'll collect all the outputs or nodes kind of from each table in a shared Google Doc, which also has some of the like links and instructions, so you can scan this link. I think it's also under bit.ly/VSci Bogotá.
Yeah. Tyler, do you want to run? We explained the workshop now. Do you want to run through it again?
When you just know that it's right, it's one in a lifetime. For the first time in my life, I'm right on the edge now, looking down. No matter how hard I try, can't see the ground. I'm on the edge now, taking the lead, taking a chance. You just touch me when I fall for you. I need for you, my angels, listen to your heart. 'Cause I need for you, my angels, touch me when I fall for you.
Schau mal, was der Lifehack ist. Ist hier einfach Kaffee. Ah, okay. Was, echt? Ja, ja. Also das ist jetzt Kaffee. Dann, wie lange bist du hier? Ja, ich habe auch. Ja. Also, kann aber auch einfach deinen Bildschirm ein bisschen unterdrücken. Ja.
Cool. Just everyone, a quick reminder that we have it's about 20 past 5 now. So let's take maybe another 9 minutes to actually start collating outputs and results. And then in about 9 minutes, so this is half past, we want to go into each team kind of pitching what they've come up with. And if you haven't like had a breakthrough, that's okay too. Maybe share all of the kind of the learnings that have come. And then we can go into public discussion of the outputs. Thank you so much.
We were like, it's still early, right? But we're still looking at like recurrence and stuff.
Should we do that order? Otherwise, I mean, we have about half an hour. However, I mean, we don't like we make recommendations. We don't like do like chain neutral. Like if Foresight wanted to deploy on another chain, like that's all. Yeah. I actually think in the long run, these architectures will deploy the multiple chains. So like blockchain.
So the question is like, well, you have a fair launch, and then there's no pre-sale. Well, how do you get tokens? And when we did a beta down, we had load right after launch, open holders, lock tokens, load it, let it allocate retroactive tokens into the health. So that's how you get it.
Not a lot of people remember that. Know that, but it's really powerful. Because essentially, so you could be building this DAO that could. It's some but actually, if you're saying through the DAO kind of launches its auction, and then it's up to the public to provide funding for research of the DAO. And in turn, all of them look at the auction, we see government like but Foresight does it, for example. And then those people that put in money now vote, like how much was that get? And the whole team and everyone votes it. And of course, they make a proposal, and nobody that proposes accepted, but it might be that the community is actually like, maybe you should have some more, or maybe you should have some less, and maybe this should be done. But the really important legal aspect of this is actually the executive now is not you, because you're not in control, but it's not. But the token office is in control. They could also decide to like do nothing, but which would be ludicrous because they just put the money to like fund it, and it would be very negative for the project. But it's a really powerful concept. You put it fully in the hands of the community first step. Yeah.
Then, of course, we're going to channel like all our like fellows researchers, like helping Foresight you know, it's like there are different ways to organize types. So Foresight will funnel all fellows researchers, mentors, and then are there like what are the sort of legal ties or like where are the what can be done, what cannot be done.
So, for example, we have an affiliated nonprofit hospitality health. So when we did now, our contract get live hospitality health. We now also have another nonprofit. But they're just like all that would be it's a related company, but
So
you actually, so like Foresight is not the wrapper of the DAO. It's like you kind of see the DAO as centralizing. You're decentralizing. Like you said, it's like first of all, you want to identify where so you say we are decentralizing tech tree. So you started by decentralizing just a portion of your organization, and then over time you can find that you're LLM progress and communication doubtful, and then by the way, one smaller DAO is like private decentralizing portion of the organization, we're taking the power that we all held as a small group, and we're sending it out to the community and letting they're dominating one thing you want to make is extract funds from the treasury account. You've probably heard like quit function in the Moloch DAO, where like protocol say, I'm quitting, and so I'm taking my portion of the treasury out. And the kind of DAO that we're designing here, we don't allow for that to happen because it also jeopardizes security. Because you're a token holder and you have a so you want to break it up. If the token holders don't have any claim on it, they have the ability to vote on where they might go, but that vote, when they can't vote, we keep it as a non-profit. Then you have another question, like, well, is it right? You said, well, if you're a non-profit, you just have a token, can you take it later? So there's a few different ways to reward them. One is by saying if you vote, you're going to get paid. It's like incentivizing. Also, like in Vita down if you vote with your Vita, you get paid. So that voters who are active get bigger and bigger stakes in the DAO, and therefore like more active. That's one. Another way to reward DAO is to for the treasury. Another way is even more interesting in my opinion. You do it as like you can get paid from the DAO with salary. Like so for example, in the legal work, you have lawyers who will complete tasks and down. So they're not getting paid from the treasury necessarily from the profit, instead they're getting paid like the person from the university now. You know, university they're trying to make money from the endowment. They can support all the academics. So the money that you get paid as a professor, or the scholarship you get as a student, it comes with the endowment. And so it comes from the investments that the university is making. But your pay is more like a reward pay. So you're getting a reward for your consistency now. But it's not like a direct reward for treasury profits as a percentage of profits. It's a reward for your organization. Just like yours. Because the endowment is like the DAO treasury. And just like the university professor or student can't claim assets from the university endowment, the endowment makes a investment, makes money. So you don't have to get that profit. So it's DAO is like deciding where doing DAO even though the DAO is making investments and managing money. properly down some. And is it those proper tokens should be back to the DAO? That's a way to make more salaries. So what we're building now is the idea of maximization, the ability for token assets to help us. Because right now, if you hold Vita or I hold Vita, I don't own the idea of Vita down there. And so, what if I as a user can actually get access to the idea? Maybe there's a project that is funded that actually tested out, like particular. Like there's actually one really cool project
Cool. Time is slowly up. I want to slowly start bringing all of you guys back. Oink, oink. What?
No, why will a pig caught my attention? Like,
I don't know. I was just, yeah, did the pig catch it? Chewbacca? Yeah, now I got your attention. Okay, cool. Hey everyone. So I want to slowly start bringing us back because it would be awesome if each of your groups can now kind of present the specific vertical that you explored and some of the solutions, some of the Lego blocks that maybe emerged around that. So maybe if someone from your team can come up, or do you want to stay in your circle? What do you prefer? Stay in the circle? Okay, but you have to stand up while you're presenting. Who wants, and so maybe take 2 to 3 minutes to walk through the findings of your team and maybe the solutions that you discussed. And then it will be really awesome if someone from your team can actually capture it. And if you haven't already, just write it and put it into this document. If it is already in the document, I'm actually just going to scroll through and check. I lost it. If anyone can see, I think I misplaced the mic somewhere, or maybe the support people took it, but it should be somewhere. Yeah, so just transcribe kind of that main outputs that you're also going to present into this doc so that we can share it with the world and the community after this. That would be really awesome. Okay. Who wants to go first? Cool. Tyler, floor is yours. You have to stand up.
I kind of need to read this while I'm doing it, so I'm not going to stand up. Or I can. Yeah. So we were looking at a scientific reputation system and looking first at how our current scientific reputation system functions. So we first mapped the current system out into 2 verticals. One would be formal credentials and other would be sort of informal reputation. And formal credentials are things that are verifiable, measurable, and somewhat quantifiable. These are things like academic affiliation, degree, impact factor, H-score, pedigree, citations, for example, and funding sources. And then there's more sort of informal, more, let's say, qualitative reputation things. This is like social media and press, collaborators and peers, who you know, political affiliations, hype, your ability to influence others. And we mapped out some pros and cons in each of these. If you want to look at these in detail, you're more than welcome to. They'll be in the doc. But just as like a high-level example, without going into excruciating depth on each of these, things like academic affiliation can demonstrate or attract quality. They could signal trustworthiness. They can be associated with specific areas of expertise. They could act as sort of Schelling points. But on the other side, they can create inequality. They can, for example, foster sort of like certain reinforcement patterns, create like legacy students. There's a bunch of problems in sort of fostering. Sorry, this doc is moving in real time as I'm reading it. I'll just talk through it rather. I think I can do it from memory. There's a bunch of things in the context of this current
let's say, verifiable metrics that still need work. So impact factor is something that I think can be quite positive in terms of it can demonstrate readership and citations, but it can also be heavily gamified and is used to largely sort of reinforce certain popular ideas. Many Nobel laureates, for example, don't publish in high impact journals. Their ideas are initially rejected. So we were basically trying to look at, in the context of all of these different verticals, whether they be like verifiable credentials or sort of informal credentials, what are the sort of things that we want to bring over into DeSci in the context of this, let's say, new reputation system? And so we did a little bit of work thinking about things like credentials, and these could be represented by things like soulbound tokens, for example. So instead of just having academic affiliations, we want to have things like industry affiliations, guild affiliations, DAO affiliations. What are the communities that you're associated with? What are the values of those communities, and how do we measure those? I think we also want to look at, for people who are involved actively in funding, how are they making an impact? What DAOs and organizations are they a part of? What areas have they done research in? What areas have they maybe impacted? And this is also a hard thing to measure, but I think using impact certificates and actually POAPs in some cases, you could begin to use some of those technologies to measure the impact that somebody's having. We could also look at things like GITs and like pull request in the context of like data becoming increasingly, like let's say if you're doing in silico work in the context of biology, you can begin to look more in real time at how somebody is contributing data to a certain research area and begin to measure an impact that way. And there's also things like measuring DAO reputation. So if I'm a contributor in a DAO, am I somebody that people are delegating votes to? Am I somebody who's being rewarded via things like Coordinate? Have I been elected as steward? And then also looking at other factors like value captured, value generated. Am I deploying funding? Have I received funding from certain people? We could also look at like token holdings. We could look at how active I am as a governance contributor in a DAO. But in the end, there's all of these sort of, I would say, new interaction patterns that are happening via the internet that are actually producing a lot of really, really rich data that is quite different from how science works today. And what we want to try to figure out, and where we haven't gotten to actually in the context of this short session, is really thinking about how those things are all weighted, how they're measured. And I think the most interesting question here, if we think about creating like a holistic reputation system that would be akin to something like impact factor, it's really challenging to do because I think the needs of scientific communities are very different. So for example, I might be somebody that from a reputation perspective is a really good developer or is maybe just really good at data collation and data analysis. How is my reputation weighed against somebody who is maybe also publishing and also funding research? And so thinking about dynamically how these systems interact, I think will be a really interesting technical challenge. One of the things that we were thinking about was like, if a DAO has a certain set of needs, so for example, Vita DAO might have a need for longevity researchers that have worked in X or Y fields and have, for example, experience with certain assays and certain data techniques. That is very different from another organization that is maybe just an investment-focused DAO and wants to know if somebody has been particularly good at deploying funding or making good bets. And so I'll cap it here. So like the thing that we're thinking about is like in the context of how can we create dynamic reputation systems where the organizations themselves are specifying what they're looking for, whether it be a series of soulbound tokens and DAO affiliations or specific credentials, and how can we have a system that basically adapts based on the skill sets that individuals have. So sort of like everything we've talked about, taking a dynamic approach to this reputation system that is not one-sided, meaning that it's not just the impact factor of researcher, but the needs of an organization juxtaposed against the specific skill set that someone has. And I think this could be really interesting because, going back to an earlier example that you made, Paul, if there's like a 16-year-old somewhere in the world that ends up being an excellent scientific reviewer because they self-taught themselves, I don't know, like biochemistry, and on the internet, no one knows your age, but they're making like comments on papers or whatever that are really valued by the community. We want a way to measure that is like independent of academic affiliation, for example.
Or what if it was even just an AI bot?
Or a dog.
Or a dog. On the internet, no one knows you're a dog. And in a blockchain network, no one knows you're a fridge. On that note, thank you so much for sharing that, Tyler. Could your group also please upload your doc into the section, and then maybe I'll just go. Sorry, it's a bit buggy here. Cool. We'll go into table where traffic public goods next, just because that's up right now. Who from that group would like to present? Vincent? Okay. Awesome. Woohoo. And we have about 3 minutes at the moment for each topic. I just want to make sure that everyone gets a chance to speak before they kick us out of here. Oh, Sava? Yeah, do you want to come up front? Cool.
There we go. And science is a public good. So the most important thing is to look at, like, how do we value impact? That's the trickiest part. And then once we've got that, essentially the market, we need to find retroactive funding. So in this particular case, we're talking about, we've got this thing called the longevity prize. Vincent's sorting, we did through Gitcoin and sort of raised, say, 250 grand. And so we've got like a source of retroactive funding available. Then the next question is kind of what do we want to, what sort of impact, is going to be in something that can scale. So got a really great idea, raise money basically from investors, where before, like, because it's a public good, essentially, there's no way, like under the traditional IP system, that you can enforce a monopoly price. So yeah, I keep talking about generic drugs and things like that. So that's something I'm interested in. But which is, yeah, basically if you can get an off-patent drug and repurpose it to treat a new disease, like so ketamine to treat depression, let's say, you could actually create like billions of dollars in social value with quite a little bit of investment there, retroactive funding. So yeah. So yeah, basically once you've delivered the impact, whatever that might be, so for instance, improved clinical outcomes versus usual care, then you will get the outcome payment under this from the retroactive funding. And the market basically figures things out. So if it's not enough funding, like if 250K is not enough, you can basically get philanthropy to put in the rest. So it's a little bit like Gitcoin, where like you sort of have little donations creating signals, or little investments creating signals for a philanthropic funder to come in and fund the rest. But yeah.
You maybe name like 2 or 3 Lego blocks that you see that are really important to make this success?
Yep.
Yeah, I think what one could add is basically that every scientist could basically mint this impact certificate, even if they have like other funding, and then could sell it. Like one of our ideas was in a more like crowdfunding sense, that you don't have to buy it for say 100,000, but you can put in $100 or $1,000 and get like almost like a small share in this impact certificate, which could be just like an IP NFT, which could then be basically put into like 1 million pieces, for example, and then it's almost like also like a pulp and kind of like collectible, because you show that you funded research. So it gives you not only potentially like the prize, but also almost like some status as being a science funder. You're doing like impact, so it's kind of like also a bit of philanthropy, and it's almost like a collectible, so you can like collect all the little research you funded. But it's also like a prediction market, because you can potentially sell it. So like as it could hit the price, it could also grow in value. So it's almost like you're signaling what you think is the most likely to hit outcome. So the Lego blocks are like IPNFTs, ERC20s, and kind of like deploying them just like on Uniswap, and then people can create liquidity or short them.
Just one more thing, and like, so for retroactive funders, that's super important. So maybe you could have an open, like impact, impact NFT, scientific impact NFT, to encourage people to become retroactive funders.
Cool, awesome guys, thank you so much. Okay, we have data and process up next.
So I think some of the things we talked about was like so the first thing we went into is like how can we collect data for scientific purposes, and then one of the things one of the problems that we need to solve is like how do we collect how do we gather people, not just for collecting surveys, not just for conducting surveys, but also like how do you gather people to participate in clinical trials, and all that falls under like we need sort of like a database of sorts which can store metadata and allow people to like ask questions to this entire population and narrow them down to specific segments. And so that could be like a distributed database, for example, maybe. And then you have to apply like operations on that distributed database to find your target audience. And so other things we talked about was like how do we, throughout the scientific process, you also need to like before you even start research, you need to identify what is a problem that actually needs to be solved. And so in order to identify a real issue that needs to be solved, you have to make sure that it's the actual problem, and you need to you can't trust majority of the population to know what is an actual problem, because certain populations may have like there may be like groups of people who are healthy and groups of people who aren't, and the healthy people may outvote the unhealthy people. So then how do you address the problems with the unhealthy people? Like maybe yeah, because we do actually need to solve the problem for unhealthy people in a way. Yeah, so what is the right thing to fund is a problem you solve also. And then yeah, more things on yeah, so can you scroll down a bit? Like scroll down. Okay. Oh. Oh my. Never mind. So I think other things are like yeah, like so we talked about cloud labs and how can we conduct how can we have like databases of people or of labs or like facilities that can help conduct research. And then also like even currently and then also another thing is like throughout the scientific process, you also need to make sure your experiments are conducted in a trusted manner. So how can we have chains of trust that go from the ground, maybe like from the individual level all the way to back to the researcher, and then beyond the research actually. Yeah, and I think one final thing we touched on is like how do you deduplicate experiments or studies conducted, and that will usually involve like open source studies and being able to query these studies. So we'll need solutions to like catalog and index studies already conducted in the past. And yeah, there's a lot of problems I think in summary, there's a lot of problems throughout the scientific process that requires individual tools and very specific open tools that are globally accessible. And in order to be able to increase the efficiency of the way the scientific process is conducted. Yeah, I think that's a summary of what we would think.
Thank you so much. Okay. Any questions from anyone? Also, maybe on the previous topic, I would love to give more time for questions and discussion, actually, but we're also quite low on time, and I want everyone to be able to present. Okay, then last but not least, we have publishing. What? Oh, yeah. Sorry. Okay, cool.
Thank you. So we're the publishing team. I guess for us, it's really a question of building connective tissue. Also, before I start, we're also the penguin team because we have a penguin on our little thing here. But the real question we're trying to solve is that of like connective tissue and really linking everything together. And the big question at the top is how do we amplify collective thinking within the context of scientific discovery? And how can we make that process easier for people? And this involves, at the start, we're just asking lots of questions. Who are we designing this for? Are we designing this to replace for publishers or for researchers? And also, is there an incentive for publishers to participate? So what we kind of realized during our discussion is that basically what we're trying to do is replace publicly centralized and equitable for the researchers that are involved. And another big problem that we talked about was actually crypto history, and I think Brewster Kahle had a brilliant talk on this yesterday or the day before from the Internet Archive, how you can just pull publications off of the record, and you really want to avoid that, and you want things to be accountable 50, 100 years down the road. So our solution is really just to use the existing technologies that already are around, like Arweave and content addressing, to build connective tissue for linking between papers and publications. And the big sort of money, or like the Lego here would be for DeSci, would be some sort of publishing standard with the associated metadata that will link these papers together, whether that is like referencing, whether that is like referring to people who built the system, wrote the paper. And I think that's where it kind of plugs into the reputation system that the other team presents earlier. And also we discussed like how can we connect these papers to the IP that resulted from them. And we were talking about how we could plug that in as well. So you could imagine visiting like a Wikipedia site that pulls from an Arweave backend and has like really good user interface. You could click and see what IPs are related to this, how the reputation of the scientists who wrote this is, and like also look at the references by following the Arweave links. And because it's Arweave, it's permanent. You don't have to like worry about the data disappearing at any point in time. We also looked at some other systems here, like Wikipedia is probably a great example for a linked content system that has worked really well for data. Also stuff like DeSci Labs and BioRxiv. We're doing research in adjacent spaces. But yeah, that's about it. Thank you.
Thank you so much. I really like how you essentially already started creating connections between the different, the different topics. Team in the back, Benji. That sounds like a bad excuse. Can you still talk about it? Do you want to come up quick? And we have about 6 minutes left.
Oh, yeah. Mike, okay, I feel powerful now. We talked about decentralized clinical trials. Firstly, why would you decentralize them? How would Web3 work? I think we came to a broad consensus that generally speaking, the things you'd initially want to look at would be clinical trials with things that weren't particularly dangerous and you could get over the counter. And it's okay to ask the general public to do. We talked about data issues in that, whether data should be stored on people's phone, encrypted and put on the blockchain, and the issues that can happen when you've locked data up on people's devices and they get sick or ill or unconscious, and generally decide that in a clinical trial they should probably always consent and those exceptions don't matter too much. We also talked about how you would decide which trials to run and why. I think broadly we agreed there should be some vague oversights from professional people in that, so you don't do something too dangerous. And lastly, we went down a big rabbit hole on incentives, the potential of micropayments, and the pitfalls of people just taking the step counter and attaching it to a piece of string and putting it in front of a fan. Apparently that works quite well. Yeah.
Thank you so much.
Thank you. Okay, so on the legal side, we worked on a practical case, and I presented the problem to Jesse. So I work for Foresight Institute. We are a sort of perfect problem child for DeSci. We are a nonprofit organization that is based in California that has existed for 40 years, doing science
really at the edge, trying to accelerate science that's way too ambitious or too niche for legacy institutions generally to feel comfortable to fund. So we work on neurotech, biotech, trying to push longevity, age reversal, brain-computer interfaces, building Dyson spheres, because we also work on space, AI, crypto, etc. And so we have this organization, it's a nonprofit, and we want to DAOify it. And so there were two main categories of problems that I presented to Jesse. One of them was how do we not jeopardize the existing organization? And the second one was more focused on governance and how to create a DAO structure that is really aligned with the ethics of our organization. And Jesse was very helpful.
Thanks, Lou. So we really have two sets of solutions to these two questions. One is, how do you make a DAO from your nonprofit that doesn't jeopardize the DAO and its existence? And the answer is what we did at VitaNow, a fair launch with no pre-sale. And that may rub some people the wrong way who want to raise money privately from investors before launching the DAO, but it's really the key to prevent an existential risk to your organization is to do a fair launch. And what that means in practice is having a team that's willing to bootstrap and launch this organization and then get retroactively voted for their token-based compensation after the launch of the DAO. Number two is that there should be no direct claim on the treasury, so you can't have a Moloch DAO style rage quit function that allows for the token holders to claim treasury assets. There has to be some kind of break in that chain in order to prevent the token from having a secured interest in the treasury of the DAO. In other words, the token being a security. And in that same vein, no distribution of profits to token holders. And so that leads to the question of like, well, if you can't distribute profits to token holders have no direct claim on the treasury, then what's the token for, right? How do you reward people for participating in this DAO at all? And the answer is, in part, what we do at VitaDAO. And the best example is to look at a university endowment. A university endowment makes investments, right? It makes money. It makes money for the university, and then that money is distributed to university administrators, to students through scholarships, to making buildings, to making the university a better place. No professor or student has a direct claim on profits that are made from the investments in the university endowment, but the university grows and becomes a better place and becomes a higher salaries. Professors get paid more, scholarships are handed out to larger degrees, the more money that the endowment makes. However, again, no professor has any claim on profits that are made from the university endowment. And so I encourage you to think of your biotech DAO and the money that it's making and the treasury that it has like a university endowment, and the structure of the DAO as a nonprofit structured almost like a university. And then later, with our IP NFT 2.0 protocol and the fractionalization that comes with that into friends and fam tokens, which we can talk about at dinner tonight. What you do is you have a really interesting system whereby the token holders of your DAO don't just have the ability to vote in snapshot on governance proposals, which is like, step one of DAO participation, and that's about as far as many DAOs get unless they have this Moloch style rage quit function. What you have with IP NFTs and their fractions is the ability to drive value to token holders and allow them to accumulate portions of the IP and portions of the treasury assets, direct exposure to interesting projects that they want to co-govern, and if they KYC in a credit, that they want to co-own. Yeah.
Okay. Thank you. Just making a final announcement. Wait, don't disconnect. I put on top of the document. So tonight, in partnership with Molecule, Foresight is hosting a Decide dinner at Teatro Ripio. And so we invite you all to join and continue this discussion. I put perfect, thanks. Otherwise, the link is at the top of the document. I put it just under the agenda in the Google Doc. You can directly click there and register and join us. That's it, Paul.
Thank you so much. Yeah, a massive thank you for everyone that participated here. I think we had some really, really cool, exciting insights come out of this. You all have the shared doc. What we'll try to do maybe from our side is like maybe collate this into like a blog post of sorts or just maybe a Twitter thread to share it with the community. If you want to be tagged in it, please feel free to put your Twitter handle into the doc. Yeah, and look forward to maybe seeing some of you at the dinner tonight. And remember, build Lego blocks, build railroads, build roads that other people can use and that can cross-integrate into the community, because we still have such a big opportunity here to set those railways for everyone to interoperate, which is what open science and DeSci should all be about. Thank you so much.